Let's solve this question. What you need to do here? You need to do x equals to a plus b you need to do, right? So a is represented as 0 0 1 0 1 0 and this is given in ones complement representation. Now here what you can see, this is a positive number. So for positive number, whether it is binary or it is sign magnitude representation or it is ones complement or it is twos complement, for positive number all are equal. Binary is equals to sign magnitude representation is equals to ones complement representation is equals to twos complement representation for positive numbers. So what is this number? What is a? A is 10. I can see 1 2 4 8. So a is 10. So your a is plus 10. And b is given in signed number system. B is given in signed number system. B is given is 1 1 0 1 0. So this is given in sign magnitude representation. So what is b? This sign is minus 1 2 4 8 16. 1 2 4 8 16. 26. So b is 26. B is minus 26 and a is plus 10. So what you need to do? X is equals to a plus b you need to do. That is plus 10 minus 26. That is equals to minus 16. So you need to represent minus 16 in sign magnitude representation first. What is the answer we are requiring? What would be x in 2's complement form? So first you represent in sign magnitude form. So first bit will be of sign. And how will I represent 16? So this is how I will represent 16. 1 2 4 8 1 2 4 8 and 16. 1 2 4 8 and 16. This is how I will represent in sign magnitude form. So now I need to take 2's complement. So how will I take 2's complement? This will be the 2's complement only, because I will start from here 0 0 0 0 and 1 I am getting. So this is the 2's complement form only. So answer is 1. Very simple question. Like usually people are not that much comfortable with number system. So I have spent a lot of time, like I guess we have spent around 7 to 8 hours in understanding only the number system only. Usually people spend only 2 to 3 hours on number system, but we have spent a lot of time because this is one of the topic which is confusing to a lot of students. So you can go and check out on YouTube only, we have uploaded it. Okay. Yeah. So this is a good question. Here, which of the following options are correct? R's complement. Let's take an example. Forget about all these options. Let's take an example. Let's take an example of base 10. Which example we are taking? We are taking an example of base 10. Base 10. That means R value is 10. Now I am taking an example of n equals to, let's just say 123. Now if I need to calculate 9's complement, what I am going to do? 9's complement. How do I calculate 9's complement? So for calculating 9's complement, I do 999 minus 123. This is what we do, right? There are 3 digits. So 999 I will write down 3 times minus 123. So that will be my answer. Whatever we get here, that is 876, right? So my answer is 876. This is my 9's complement. And if I need to calculate 10's complement, what do I do? For 10's complement, what do I do is that whatever the 9's complement I am getting plus 1, right? So 876 plus 1, or what I can say is that this can be written as 999 minus 123. This is your 9's complement plus 1. This will be the answer, whatever the answer you get. Or can you write it down in this manner? 1000 minus 123. So this will be your 10's complement. So from here what you are getting to know is that your 10's complement is r to the power n minus the integer. R to the power n minus the integer. What is my r? 10. 10 to the power 3. What is n here? N is the number of digits. N is the number of integer digit. So here number of integer digit is 3. So r to the power n minus n. What is my n? That is 123. So is this your 10's complement? Yes. This is my 10's complement. And what is my 9's complement here? So my 9's complement is r to the power n minus 1. Because this is getting subtracted from 999. So this is my 9's complement. Are you getting this point? Or instead of 10's complement, here I should write r's complement. Because 10 is equals to r. So this is your r's complement. And this is your r minus 1's complement. So your r's complement is equals to r to the power n minus n. R's complement is equals to, r's complement is equals to r to the power n minus n. This is correct. And r minus 1's complement is equals to r to the power n minus 1. So these two options are correct. What about the third one? Here they are saying that n digits and m digits in integer and fraction respectively. That means here fraction is also there. What do I mean by fraction? what I mean to say is that now for the C option, your example should be something like this: 123.456. This is my example. Now if I need to calculate 9's complement, how do I do that? 9's complement. How do I do that? 999.999 123. Basically you write down the number and above that you write down 99999, whatever the 9 you get, minus, what do you see, 3 4 5.678. what they are talking about, they are talking about r minus 1's complement only. So how do I calculate r minus 1's complement? So what they are saying is that it is equals to r to the power n minus r to the power n minus r to the power minus m minus n. This is what it is equals to. So here, what is the value of n here? N is 3. Now let's make this example better. So now I am gonna do this thing. What I have done is that I have made the value of m equals to 2. What is m? M is the number of digits in fraction. N having n digits and m digits in integer and fraction respectively. That means n is the number of digits in integer, that is 3. N is the number of digits in integer and m is the number of digits in fraction, that is 2. So if I do this calculation, what is my r? R is 10 to the power 3 because n value is 3, minus, what is my r? R value is 10 to the power minus 2 because m is minus 2, minus n, that is 123.45. Will I get r minus 1's complement? That means will I get 9's complement here? Let's check that out. 10 to the power 3 minus what is this? This is your 10 to the power minus 2 is 0.01, right? 10 to the power minus 2, that is 1 by 100, that is equals to 0.01. So what you are getting? You are getting this equals to, here you can put 2 0, so 10 minus 1 9 9 9 9 9. So 999.99. So this is equals to, this is becoming equals to 999.99 minus 123.45. Yes, this is my r minus 1's complement. So yes, this is my r minus 1 complement. So this is how you calculate r minus 1's complement as well. Is that clear to you? So this is the option C that is correct. Option C that is correct. So actually, like directly these formulas are taught that this is how you can calculate r minus 1's complement. But we already know the process, and if we don't remember the formula, we can build up the formula in the examination, right? We already know the process. When we know the process, then we can build up the formula. When we know the formula, then we can build up the process as well. So usually we remember the process. I don't think you remember this formula. You remember that 9's complement, okay, 999 I will write. 10's complement, then I will first calculate 9's complement and then I will add up 1. So this is how we remember it actually. So this is how we remember it, then we can develop the formula as well, right? So these two formula we can develop, and if there is fraction, then this is how we can solve it, and this is how we can develop the formula. Fine. Okay. Yeah, so you need to implement the given Boolean expression using minimum number of 2 input NAND gate. So what we will do first, I will simplify it. So how I can simplify it? A bar B, can I take A bar B common anywhere? No. So let's keep A bar B D as it is. Can I take A bar C as common? Yes. A bar C if I take common, then D plus D bar, that would be 1 only. Plus, can I take A B D as common? Yes. So C bar plus C. So we are simplifying it. You can simplify it using the K-map as well, but here I am doing using this analysis. This is what I am left with. Now I can take BD as common, right? If I take BD as common, then A bar plus A would be there, plus A bar C, right? So what I am getting? A bar C plus BD. So AC plus BD, how much this will require? This will require 3. This we have already seen in the last test series as well. I have already proved it. AC, BD, and then the addition. So if I need to make it NAND, then another or NOT gate I will use here. If I need to make it NAND, then another NOT gate I will use here. So 1, 2, and 3. So these 3 will be required. So for AC plus BD, 3 will be required, but for this one, 1 will be required. If you need to make A bar, then 1 NAND gate will be used. And if you need to make AC plus BD, then 3 NAND gate will be used. So 1 plus 3, total 4 NAND gate. Okay, so that is the answer. Very easy question. Fine. Yeah, so in this one, they are asking the number of NOR gates. So again, what I'm going to do is that I'm going to make the K-maps. I'm gonna make K map. So for NOR gate, usually what do we do? Usually we implement zeros. For NOR gate, we usually solve with respect to POS. So let's solve with respect to POS. So this is 0, 1, 2 and 3. 8, 9, 10, 11. Rest all zeros will come here. Rest all zeros will come here. So this is W, X, Y, Z. Sorry, W plus X, W plus X and here Y plus Z would come. Rest all will be 1. These all will be 0. So what will come here? W plus X. Here W plus X bar. Here W bar plus X bar. W bar plus X bar. And here W bar plus X. 0, 0, 0, 1. Same goes here. 0, 0, 0, 1, 1, 1, 1, 0. So what do you see? This is the group we are getting. So in this group, what is my expression f? My expression f is only x bar is constant. So what we are getting? X bar. So for x bar, how many gates you will require? One NOR gate you will require. This is your x, one NOR gate you will require. Basically, you need a NOT gate. So how many NOR gate are required to make NOT gate? Only one. So 1. Answer is 1. Like in a hurry, people will write down the answer to be 0. Why is that so? They will say that, okay, group of 8 is becoming. So they will not even check what is the expression you are getting. Just by the group of 8, you cannot say that 0 gates will be required. If your expression f was x, then you would say that 0 NOR gates are required. Because I am already having x. So no NOR gate I require to get x. Because I already have it. So that then answer would be 0. But here you need x bar. So for that you would require 1. So that is an error which students might be doing. So if my g was x, then I would require NOR gate to be 0. Okay. Yeah. So let's see this question. Minimum number of NAND gate they are asking. So first let's try to simplify this one. So what I can see, I can take C as common. So A bar plus B bar, C as common I can take, and here I can take DF as common. So D bar plus E bar. So always you need to simplify the expression. Always look for simplifying the expression. If you have simplified it, then it would be very easy for you. Can I make it AB bar into C? Can I make it DE bar into F? If I call this as X, XC plus YF, I am calling X as AB bar and Y as DE bar. So these two combined will require me 2 NAND gate, right? This will take one NAND gate and this will take another NAND gate. So this is taking one NAND gate and this is also taking one NAND gate. So these two combined is taking me 2 NAND gate and this will take me 3 NAND gate. So 3 plus 2, total 5 NAND gate you require. There you go. Okay. So always any expression is given and you want to implement it is using minimum number of 2 input NAND gate. Here 2 inputs should be written. Minimum number of 2 input NAND gate. Then always you need to look for simplifying the expression. So I have simplified it in this manner. So answer would be 5 NAND gate. Okay. Yeah. Let's see this one. So what should be the value of D0, D1, D2 till D7 such that F follows the sum of input ABC. Okay, so ABC are applied to multiplexers, right? ABC are applied to multiplexer. So if ABC all 3 are 0, 0, 0. If all 3 are 0, then what will happen? From here 0 would come, from here also 0 would come, and from here also 0 would come. That means D0 will be the output. Are you getting this point? If ABC all are 0, 0, then your F will be equals to D0. And what is your D0? D0 is the sum of input ABC. That means D0 is your 0 plus 0 plus 0. That would be 0 only. That means D0 is equals to 0. Are you getting this point? Now let's just say my ABC is 0, 0, 1. ABC is 0, 0, 1. But here, yeah, ABC is 0, 0, 1. Then if C is 1, then D1 will go out. If B is 0, then this D1 will travel here and F will be equals to D1. Do you agree to this point? If C is 1, then F will be equals to D1. If this is the condition that A is 0, B is 1 and C is 0, then what will be the output? If A is 0, that means this guy will go out. If B is 1 means this guy will go out. And if C is 0, C is 0 means this guy will go out. C is 0, B is 1 and A is 0. That means D2 will go out. Are you getting this point? In that manner, if I ask you that if this is the condition, if this is the condition, then what will be the F output? A is 1, that means this will go out. B is 0, B is 0, that means this will go out. And C is 1, C is 1, that means this will go out. That means output will be D5. So basically decimal equivalent we are getting out. If our input was 0, 1, 1, if our input was 0, 1, 1, then output would have been D3. If our input was 1, 0, 0, then output would have been D4. In that manner we will get our output. Now what they are asking, the F should be the sum of input ABC. That means D1 has to be 1 only. Why is that so? Because 0 plus 0 plus 0. What is 0 plus 0 plus, 0 plus 0 plus 1? That is equivalent to 1. What about this one? What should be D3? What do you think what should be your D3? D3 should be equals to 0 plus 1 plus 1. What is the sum of this? 0 plus 1 plus 1. What is the sum of this? 2. Or you can write down 1, 0. Where 1 is the carry and the summation is 0 only. So what is the sum? If I perform this operation, what I will get? Sum equals to 0 and carry equals to 1. Say yes or no. That means D3 has to be 0. So here you can check. D0 is 0. D1 is 1. What will be your D2? D2 will also be 1. D3 has to be 0. In that manner you can check. What will be D4? D4 will be 1. What will be D5? D5 will be 0. What will be D6? D6 will be 0. And what will be D7? What is D7? 1, 1, 1. That means it should be 1 plus 1 plus 1. That means it is sum is 1 and carry is also 1. So sum is 1, carry is also 1. So this is the answer. So option A is correct. Very easy, very straightforward. Let's see this question. This is a priority encoder. So this is a 8:3 priority encoder and they are asking you the output expression. Now it is easy to find the output of a 4:2 priority encoder. I have told you, you should always use K-map, right? You should not be telling the output blindly. You should always use K-map for priority encoder. But if I use 8:3, for 8:3 if I use K-map, then it will be very, very large, right? There will be a lot of input. So I cannot use K-map. So I have to go by the options. Now do I know the meaning of priority encoder? What is the meaning of priority encoder? And what is my lowest priority? My lowest priority is D0. And what is my highest priority? My highest priority is D7. That means if I click on 1, if I click on D7, then no matter whatever I have clicked here, the output should be given with respect to D7. That means output should be given as 1, 1, 1. Basically, I have clicked on button 7. So output should be given with respect to 7 only. That is 1, 1, 1. And what is my highest priority? My highest priority is 7. Now let's just say if I click on D5, and I click on D7 as well. What I have done, I have clicked on D5 as well and I have clicked on D7 as well. I have clicked together. So now what will be the output? Output will be with respect to 5 or with respect to 7? Output will be with respect to 7. Why is that so? Because 7 is my higher priority. So this is the meaning of priority encoder, right? So now if I'm clicking on D5, then I need to make sure that my D6 and D7 are 0. Now I don't care whether I click on D0, D1, D2, D3 or D4. I don't care about that. If I am clicking on D5, then my output should be with respect to D5 only. Are you getting this point? If I have clicked on D5, then output will be with respect to D5, considering that I did not click D6 or D7. That means if I click D5 and D3 together, then output will be given with respect to D5. So this is the meaning of priority encoder. So the scene is like what you need to do is that if my D5 is 1, then my Q1 should be 0. If my D5 is 1, then what should be my output? What should be my output? My output should be 1, 0, 1. That means my Q1 should be 0. But if I put D5 equals to 1 here, what I am getting? My Q1 is equals to 1. That means this is wrong. This is how I need to eradicate the options. Are you getting this point? Let's take another example. If I click on D3, if my D3 is 1, then what should be my output? My output Q2, Q1, Q0. That should be 0, 1, 1. So if I click on D3, if my D3 is 1, here D3 is not even mentioned. So this is wrong. Here if you check this one, if my D3 is 1, so D2 plus D3, that would be 1 only. So what we are getting? d5 dash d4 dash plus d6 plus d7. So if your d3 is 1, then your output is 0 1 1. That means certainly your d4, d5, d6 and d7 would have been 0 only. Are you getting this point? Because if you want your output to be 0 1 1, that means you need to click on d3 button. But those buttons which are in higher priority, which buttons are in higher priority? 4 5 6 7, those should not be clicked. That means 4 5 6 7, I will not click on that. So I'm not clicking on 4 5 6 7. That means my d4 is 0, d5 is 0, d6 is 0 and d7 is 0. So from here directly I can check that if I put 0 here, this will be 0, this will be 0. But if I put 0 0 here, this will be 1. So here what I'm getting, q1 is equals to 1. So based on that you can check other options as well, and this will be the answer. So I'm not gonna make k-map here. I'm gonna check by the options, because that is a easier method for me. If you make the k-map, it will take a lot of time, and your answer would be like you will not be able to make the k-map. It would be very large. So certainly you would not be able to make the k-map, because here there will be 8 variables. So 8 variable k-map you cannot make, right? Only till 4 variable and or till 5 variable we make the k-map. So 8 variable k-map will be very difficult. So we will ignore making k-map here. Are you getting this point? So this will be the answer, that is option 2. It was an easy question only, but you need to check by the options. That was a good thing. Yeah, so in which of the condition overflow will occur? So in the last test series only we have seen this kind of question, right? So in which of the following option overflow will occur? So what we need to do? We need to add up these numbers. So 1 1 0 1 1 0 1 1 0, and then here you are getting 1. So what is your C in here? 1. What is your C out here? 0. 1 XOR 0 is 1. Yes, overflow is there. This is the option A. What about option B? 0 1 1 0 0 0 1 1 1 0 0 and 1. So carry in is 1, carry out is 0. Yes, overflow occurs here. What about option C? 1 0 0 0 1 0 1 1. So what you are getting? 1 1 0, here 0 and 1. So here what is your carry out? 1. And what is your carry in? 0. Yes, overflow occurs. What about option D? 1 1 1 1 1 1 1 0 1 0 1. Here also 1 is coming. So here also 1 will come. Here also 1 will come. So what is carry in XOR carry out? 1 XOR 1, that is 0. So no overflow. So where overflow is occurring? In 1 2 and 3. What they are asking, detect the overflow condition. So in 1 2 3 overflow is occurring. So this is how we can check it. Or you can see 0 0 is giving you 1, overflow is there. 0 0 is giving you 1, overflow is there. 1 1 is giving you 0, overflow is there. 1 1 is giving you 1, no overflow. Okay, fine. Yeah, so this is a factual based question only. What they are saying, 3-bit comparator is there. 3-bit comparator is there. That means 2 3-bits number are being compared. What do I mean by this statement is that there are 2 numbers which are being compared. But in these numbers, this number is of 3 bits only. Here are 3 bits, 1 2 3, and here also there are 3 bits, 1 2 and 3. So 2 3-bits number are being compared. That means there are total 6 input bits. Input bits are 6, and what will be the output? Greater than B, equals to B, and less than B. These 3 kind of output could be there. Are you getting this point? So what about total outputs? What will be the total output? Total output. So how many combinations are there? 6. 6 bits are there. So total output could be 2 to the power 6. Are you getting this point? If there are 2 bits, then how many combinations you can make? 2 to the power 2. If there are 3 bits, then how many combinations you can make? 8. 2 to the power 3. Here 2 to the power 2. So here there are 6 combinations, no? There are 6 bits of input. So how many combinations you can make? 2 to the power 6. So total output is 2 to the power 6. Out of these, 2 to the power 6 is the total output. Out of these, 2 to the power 3 will be A equals to B. What is this? This is your A equals to B. This is the condition for A equals to B. Because when you will get equal, 0 0 0 is equals to 0 0 0, 1 1 1 is equals to 1 1 1. That means this bit is equals to this bit is equals to this bit. Sorry, what I'm saying is that this bit should be equals to this bit should be equals to this bit, and this bit should be equals to this bit. So these kind of condition will be there 2 to the power 3. Right? 0 0 0 0 0 0 is equals to 0 0 0, 0 0 1 is equals to 0 0 1, 0 1 0 is equals to 0 1 0. 2 to the power 3 condition will be there. So these are the condition for equal. Now half of condition will be there for greater than and lesser than. That means this much conditions are left. Out of these, half will be for greater condition and half will be for lesser condition. This is how we need to remember it. I have told you, right? So better than mugging up some formula, we should always go with the concept. This will be the condition for a greater than b and this will be the condition for a less than b. And I guess this is what they are asking, right? Usually people remember this formula 2 to the power 2n minus 2 to the power n divided by 2. But how long can you remember this formula? In the examination with so much of pressure, with pressure of 65 questions, will you be able to remember this? No. So always have the concept with you, right? So 64 minus 8 divided by 2, 28. So answer is 28. Okay. Very simple. Just if you mug up the formula, then it will be difficult. Otherwise, it will be easy only. So what is this? You are designing a block which will detect a 13579 in a 4-bit 5211 code. 5211 code. What you need to detect? 13579. So at what time your output will be 1? That only I am writing. Because what I am gonna do, I am gonna make the logic. I need to make the logic y. So I will solve it using K-map. And in K-map, I will use the min terms. So what I need to write, I need to write down only those conditions where my y is 1. That's it. This is my target, right? So let's write down. So y will be 1 when your decimal equivalent is 1. So when you can get decimal equivalent equals to 1, 0, 0, 0, 1 or 0, 0, 1, 0. In this condition, you can get your decimal equivalent 1 because this is 5211 code. When your decimal equivalent can be 3, 0, 1, 1, 0 or 0, 1, 0, 1. Your output y will be 1 in these conditions, right? I am writing down only those conditions when my output y will be 1. So 1, 3. How I can get 5? So 5 I can get in this manner only. Is there any other chance of getting 5? No. 1, 0, 0, 0, it will give me 5. Is there any doubt about that? No. What about 7? How I can get 7? So 7 I can get in this manner, 5 plus 2. Or I can get 7 in this manner as well, 5 plus 2. How I can get 9? So all should be 1. All should be 1. So this is how I can get 9. So these are the conditions for y equals to 1. Is there any other condition left? Let's check again. So 1. Okay. Then 3. 3. Okay. 5. Okay. 7. 1, 1, 0, 0, 1, 0, 1, 1 and 9. Fine. Do I have a page? No, I need to add a page. So I will make the K-map now and I will solve it. Zero 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 1 1 1 1 0 0 0 0 1 1 1 1 0 A B C D, right? These are my inputs A B C D. A is MSB. Okay. So 0 0 0 1. That means here the decimal equivalent is 1. Here the decimal equivalent. Look, K-map you always make with respect to the binary numbers, right? That means 0 0 0 1. At this point you will get output 1. Here you will not say that, sir, here the decimal equivalent is 1 only. Decimal equivalent is 1 with respect to 5211 code. But when we make the K-map, we make the K-map for what? We make the K-map for binary equivalent, no? Are you getting this point? Here, this block will be 1, this block will be, this block will be 0, this block will be 1, this block will be 2. Why is that so? Because 0, 0, 1, 0. This has the decimal equivalent of 2. But with respect to 5211 code, it will be 1. Are you getting this point or not? K-map is made with respect to the binary equivalent, right? So this will be 3 here. But till what points? 0, 0, 1, 0. When input is 0, 0, 1, 0, then it will be lit. Output. When input is 0, 1, 1, 0. When input is 0, 1, 1, 0. 0, 1, 1, 0. Then it will be lit. When input is 0, 1, 0, 1. When input is 0, 1, 0, 1, this will be lit. When input is 1, 0, 0, 0. When input is 1, 0, 0, 0, this will be lit. When input is 1, 1, 0, 0. When input is 1, 1, 0, 0, this will be lit. When input is 1, 0, 1, 1. 1, 0, 1, 1. And when the input is 1 1 1 1 1 1 1 1. So these are the outputs we are getting. So directly I can see that this is a K map, this is a K map, this is a K map, sorry, this is the club, this is a club, this is a club. So these clubs we are getting. What is the output Y we are getting? So A bar C bar D plus A bar C D bar plus A C bar D bar plus A C D. So what you can see here is that A bar C XOR D plus A C XNOR D, right? So here I can see that it is A bar C XOR D plus A C XOR D bar. So what you can see here, X bar Y plus X Y bar. That means this is equals to A bar XOR, sorry, A XOR C XOR D. So this is the answer. Or it can be equivalent to A XNOR C XNOR D. So the answer is these two, right? Well and good. Let's see the next one. Yeah, so you need to make 3-bit comparator using 1-bit magnitude comparator. You are having AND gate as well and you are having OR gate as well. So what we need to make 3-bit magnitude comparator? What we have? 1-bit magnitude comparator. That means we actually need to make this 3-bit magnitude comparator. 3-bit magnitude comparator means it will have 6 input bits, right? It will have 6 input bits and basically each of them these are the two numbers, you can say, or you can call it bit string. These are the bit string we can call it. Like there will be number of A2, A1, A0 and there will be a number of B2, B1, B0. Basically this A number is string of 3 bits and B number is a string of 3 bits. So what will be the outputs? Output could be greater, A greater than B, A equals to B or A less than B. Output could be A greater than B, A equals to B and A less than B. These 3 kind of output could be there. Okay. So in 1-bit magnitude comparator as well, there is this condition that 3 kind of outputs are there. In 1-bit magnitude comparator, what I'm going to do is that it will compare only 1 bits. So I will give the input as A2 B2, A1 B1 and A0 B0. Now you should have some concepts clear here now. Then only you will be able to understand the next step. What is the concept? That if A2 is greater than B2, here I am writing this as G2. Okay. It could be G2, it could be equal as well. That I am writing E2. Basically G means G2 means, what is the meaning of G2? That A2 is equals to, sorry, A2 is greater than B2. And what is the meaning of G1? The meaning of, sorry, what is the meaning of E2? Meaning of E2 is A2 is equals to B2. And what is the meaning of L2? Meaning of L2 is A2 is less than B2. Right? Same goes for E1, L1 as well. So this will have 3 outputs. This will also have 3 outputs. And this will also have 3 outputs. Right? Now what we need to do? We need to generate this G, E and L. So what will be the equation of G? Can you write down the equation of G? If your A2 is greater than B2, that means certainly A will be greater than B. What I mean to say is that 1 0 0 will be greater than 0 1 1. Say yes or no. If first bit is greater, that means 1 is greater than 0. If first bit is greater, then the complete number will be greater. You can take any example. So if G2 is there, that means you don't need to worry about anything else. Or what could be the condition? Or the condition is if first bits are equal, that means this bit is also 1, this bit is also 1. But second bit is greater, that means this is 1 and this is 0. Rest could be anything. What I mean to say is that first bit is equal, that means first bit is equal, but the second bit is greater, then also this guy will be greater than this guy. Say yes or no. Here first bit are equal. If first bit are equal, then where I will go? I will go to the second bit. So if second bit is larger, then the number will be larger. Or what could be the condition? Or the condition could be that if first bit is equal, this second bit is also equal, but the third bit is greater. What I mean to say is that first bit is equal, first bit is equal, second bit is equal, second bit is equal, but this bit is greater. This bit is greater. 1 is greater than 0, then certainly this number will also be greater. So this is the condition for G. Are you getting this point? This is the condition for G, right? What about the condition for E? Condition for E has to be that E3, E2, E1 and E0. That means A2 should be equal to B2. When two numbers will be equal, when two binary number will be equal, 1 1 1 is equal to 1 1 1 is equal to 1 1 1. That means this guy is equal to this guy. Here let's take 0. This guy equals to this guy is equal to this guy, and this guy is equal to this guy. That means E2 should be there, E1 should be there, and E0 should be there. So this is the condition for equal. And what about the condition for lesser? The condition for lesser is if you get L2, then also it is fine. That means first bit is lower only. But if first bit is equal, then second bit is lower. If second and these two bits are equal, then last bit should be lower. Last bit should be lower. So this is the condition, right? So this is how you can make the gates. Now here 3 1-bit magnitude comparators are required, and how many AND gates are required? You let me know. How many AND gates are required? 1 AND gate, 2 input AND gate are there. Okay, 2 input AND gate are there. 1, 2, 3, 4, 5, 6. 6 AND gate are required. How many AND gates are required? 6. Why 6? Because wait a second. Look, wait. E2 into G1, E2 into L1. This is a different gate. 1, 2. Now E2 into E1. If I have made this one AND gate, E2 into E1, the same AND gate is used here as well, no? So look, this is one AND gate. This is another AND gate. This is third AND gate. This third AND gate is used here as well. Now this is different. This into L0, fourth AND gate. This into G0, fifth AND gate. And here, this is already made. This has been already made here, E2 into E1. Now another AND gate you require, that is 6. So 6 AND gate I require. Although answer was 6 only, but my calculation was wrong. 1 here, 2 here, 3 here, right? This has been already made. This will be 4th. This will be 5th. This has been already made. This will be 6th. So 6 AND gates are required. What about OR gate? 1 OR gate. Here this is 1 OR gate and this is another OR gate. So 2 OR gate, right? Here there is no OR gate requirement. Here also there are 2 OR gate. So total 4 OR gates are required. 4 OR gates are required. So this is the answer we are getting, and 3 1-bit magnitude are required. 1-bit magnitude comparator are 3. So what they are asking now? So 3. What is the cost of 1-bit magnitude comparator? So 3 into 10, 30. And 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 OR gate each are of 5 rupees. So total 10 into 5. Each are of 5 rupees. AND gate are 6. AND gate are 6 and OR gate are 4. And OR gate are 4. OR gate are 4. All are of 5 rupees only. 30 plus 30 plus 20. Total 80 rupees. So this is the answer. Okay, a very good question. So these kind of topics are usually ignored. I don't know why. You will not find these kind of circuitry in a lot of notes. But the thing is, from any combination circuit, you can make another combination circuit. You just need to have a good amount of patience and good amount of concepts as well. So this is how you can make a 3-bit magnitude comparator from 1-bit magnitude comparator. Although this has been already covered in our notes, right? Okay, let's see the next. Yeah, so you need to make this following function using 4:1 cross, 4:1 mux. So here, what is the value of how many bits are there? This function is of 4 variables, and how many select lines you are having? 2. So if n is greater than k, that means you need to make the excitation table, right? So now I need to make the excitation table. So what are my select lines? My select lines are A and C, considering A as S1 and this is your S naught. Select lines are AC, A as S1. Okay, so A is my MSB, C is my LSB. And then these are the input line which I need to find. I naught, I1, these are not I1, I naught. This is the I naught, I1, I2 and I3. And my function f is 1, 3, 4, 5, 6, 8, 12. That I will see. So how do we solve these kind of problems? So first I will vary the value of AC. 0, 0, 0, 1, 1, 0, 1, 1. With respect to 0, 0, what I will get? I naught. With respect to 0, 1, what I will get? I1. If AC is 0, 0, then I will get I naught. If AC is 0, 1, then I will get I1. Here I will get I2. Here I will get I3. Now what all things are left? BC is left. So now I will vary the value of BC. So BC could be 0, 0, 0, 1, 1, 0, 1, 1. So now this and this combined, basically what number should come here? If A is 0, B is 0, C is 0 and not BC, it is BD, sorry, BD. So if A is 0, if A is 0, B is 0, C is 0, D is 0, so here 0 would come. Now let's check this one. If A is 0, B is 0, C is 1 and D is 0. So this would be 2. So this is 0, 2. Let's check this one now. Let's check this one. A is 1, rest all are 0. So this is 8. Let's check this one. A is 1, 0, 1, 0. This is 10. 0, 2, 8, 10. What about this one? A is 0. B is 0. This is BD now. C is also 0 and D is 1. So this is 1. 0, 1. What about this one? If A is 0, B is 0, C is 1 and D is 1. So this is 3. So the condition is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is how it should be coming. Look, if you just write down 2, 3 numbers, you will get an idea that how the numbers would be coming. Let's check for this one. Did we write 12 correctly? So let's check. Here, what is the value of A? 1. What is the value of, here the value of A is 1. What is the value of B? 1. What is the value of C? 0. What is the value of D? 0. So 1, 1, 0, 0. What is this? 12 only. Yeah, we have write down 12 correctly. That means all these are correct only. So what all things we need to mark up? 1, 3, 4, 5, 5. Where is 5? 5, 1, 3, 4, 5, 6, 8 and 12. So what I am getting here with respect to these BD value. If BD both are 0, 0, that means it is B plus D. What about this one? This is B bar D plus B D bar. That means this is your XOR gate. So this is B XOR D. B XOR D. What about this one? This is 0. This is 0. And what about this guy? This guy is B bar D bar plus B D bar. This is your B bar D bar plus B D bar. So what you are getting? D bar. So this guy is D bar. So here you can see B plus D, B XOR D, D bar and 0. So this is a concept which we already studied in our notes and everyone teaches it. Like if you have studied digital electronics, then you would be knowing this concept. This is known as excitation table. So this is a very, very important kind of question. Okay, this is not a very good question, but this is an important question. Are you getting this point? There is a difference between both of the things. Very good question and important question. So this is a very important question because these kind of questions are asked very frequently in GATE examination. But this is very simple. If you know it, then you will be able to solve. If you don't know it, then you will not be able to solve it, right? Let's move to the. Now this is an excellent question. Okay, very good question. Try thinking about it. You have the answer, then it will be easy. Otherwise, when I saw this question for the first time, this is a question that is not framed by me. I got it from somewhere else. Okay, like I gave this work to some guy and he framed this question. I don't know from where he got it, but this is the question that is not framed by me and it is a very good question. Okay, so when I saw it for the first time, I said that answer should be 0. But then I thought about it and I got the correct answer. That should be -7. Why is that so? Because what they are saying, this is a 4-bit ripple carry adder. Right? What do you mean by ripple carry adder? ripple carry adder, that means it is 4-bit binary parallel adder. And you need the maximum delay. So if you have studied this from our YouTube playlist, so there we have solved 4 kind of problems on delay. There are 4 kind of pattern, if you remember it. In binary parallel adder, we solved 4 kind of pattern. And there I told you one thing, that if your inputs are 1 1, then what does full adder will do? The full adder will not wait for the previous carry. It will generate the carry to be 1 immediately. Why is that so? Because in 1 1, even if the carry is 0, even if your CI is 0, or even if your CI is 1, always the CI plus 1 will be 1 only. Because 1 plus 1 plus 0, what will be the carry? 1. 1 plus 1 plus 1, what will be the carry? 1. So if your input is 1 1, let's just say on this block my input is 1 1, then this block will not wait for this carry. This block will not wait for this carry, because this carry will be getting from here and then they will perform the operation. But if the input is 1 1, then it doesn't wait for the previous carry. So when does it wait for the carry? It waits for the carry when the input is, when input is 1 0 or 0 1. Are you getting this point or not? When the input is either 1 0 or 0 1, then it has to wait for the carry. Because let's just say input is 1 0. Then if the previous carry is 0, then what will be CI plus 1? That will be 0 only. But if the previous carry is 1, then what will be CI plus 1? That would be 1. So your next carry is depending on these carries. So these are known as propagating terms. And this is known as generating term. This is known as generating term and this is known as propagating term. What is the reason behind that? You already know, right? That's why we show it using AB and we show it using A XOR B. And then we write down our CI equation. So all these intuition I have already given, that how this equation came like this, right? So let's not talk about all these things. But for solving this question, you just need to know one thing, that if my inputs are 1 1, then it will not wait for the previous carry. If my inputs are 1 0, that means it will wait for my previous carry. So what do you want? You want your inputs to be, and what about 0 0? What about 0 0? In 0 0, even if the previous carry is 0 or even if the previous carry is 1, in both of the cases, it will generate the CI plus 1 to be 0 only. Because in this case, 0, in this case as well, CI plus 1 will be 0. In this case, CI plus 1 will be 0. In this case as well, CI plus 1 will also be equals to 0. Right? So in like whenever your input bits are 0 0, at that time also it will not wait for the previous carry, it will immediately generate the output to be 0 only. CI plus 1 will be 0 only. If A and B both are 0, then CI plus 1 will be 0 only, no matter here either you get 1 or you get 0. You either get 0 or you get 1, always CI plus 1 will be 0 only. Are you getting this point? Right? So that means what do you want? You want maximum latency. What is written? The number are represented in this form leads to the longest latency. You want the longest latency. That means you want longest delay. And if you want more delay, that means you want these bits to depend on the previous bits. Say yes or no? If you want longest delay, then what do you want? You want these bits to depend on the previous bits. Say yes or no? Right? So this is what I want. Right? Okay. So let me erase all this and then we will again see this question. Okay, we will again reframe this question. I will erase all this and then we will solve it again. Yeah. So now let's read our question again. So what they are saying, 4-bit triple carry adder is there computing sum of two different number x, y. These numbers are represented in 2's complement form. One of the decimal value is 7. One of the decimal value is 7. So one of the number is plus 7 it is. So plus 7, what is that 2's complement form of plus 7? That is 0, 1, 1, 1 only, because this is a positive number. So 0, 1, 1 and 1. So this is a 2's complement form of plus 7. Now you need longest latency. So you are performing the operation in this full adder. So what will be the carry in here? This will be 0 only, right? This is a very important point. This is 0. Now what you will think that, sir, I need propagating term. That means, sir, I want this block to wait for the previous carry. So this should be 0. I want this block to wait for the previous carry as well. That means this should be 0. Now sir, let's just say I put this as 0 as well. But now sir, what do I need? I need the minimum possible value. What they are asking? The number are represented in 2's complement form. If the decimal value of x is plus 7, then minimum possible value of y. Minimum possible value you need. That means you can take negative number, no? Are you getting this point? What I would require if I need minimum possible value. So where I will go? In negative number. That means here what I will put? 1. For negative number, if you need to represent a negative number in 2's complement form, that means first bit has to be 1. So here I will put 1. So what is the number I am getting? 1, 0, 0. So you will say that, sir, my answer should be minus 2 to the power 3. This is that 2's complement form of which number? 1, 0, 0 is 2's complement form of which number? Minus 2 to the power n. I hope you remember it. So sorry, my answer should be minus 8. But why you have written minus 7 here? Are you understanding what we are doing? Till this point, in first 5 minutes, what did I explain you? That these should be 1, 0, so that it waits for the previous carry. Right? Now here, this was fixed. This was given in the question. This 0 was given, this 1 was given, this 1 was given, and this 1 was given. If I had made this as 1 or this as 1, then there would be an issue. What would be the issue? The issue would be that these guys will not be waiting for the previous carry. These guys will not be waiting for the previous carry. But I want them to wait for the previous carry. That means this should be 0, this should be 0. And now let's talk about this one. We will talk about this one. So as of now, we are keeping this as 0 and then this as 1 because I need to go towards the negative values. So this is 1. So what we are getting, our number is 1, 0, 0, 0. So the number is 1, 0, 0, 0. And this is the 2's complement form of what? This is a 2's complement form of minus 8. Number of zeros are 3. So minus 2 to the power 3 minus 8. But this answer is wrong. Why is that so? Because when I put 0 here, what happened? Previously, what was the carry? Like in the steady state, like when these inputs are not applied, like all these added are blank, completely blank. At that time, what was the carry? 0, 0 only, no? Like there was nothing. Everything was 0, 0 only. When the inputs were not applied, everything was 0, 0. Right? Now what did I do? This one is fixed. This is given in the question. Now I applied this as 0. And my previous carry is also 0. Now 1 plus 0 plus 0. Here I will get summation equals to 1. But my carry is 0 only here. Are you getting this point or not? 1, 1, 1, 1. These were fixed. Now I applied this guy to be 0 only. And previous carry is also 0. So 1 plus 0 plus 0. How much carry we are getting? 0. So this guy is not even changing. That means this guy would have already started working at t equals to 0 only. At t equals to 0, these input got changed. 1, 0 it was. At t equals to 0, this carry was 0. Are you getting this point? At t equals to 0, this carry was 0. We thought that after some time it should change. We thought that this block should start working perfectly after some delay. But it is not working after some delay. It is started working at t equals to 0 only. Why is that so? Why it has started working at t equals to 0 only? Because this carry never changed. If this carry got changed, let's just say if this carry was going from 0 to 1, at some 5 nanosecond. So now at 5 nanosecond, the condition would be different. Are you getting this point? At 5 nanosecond, it will generate carry to be 1. After 5 nanosecond plus delay of this one, that means at 10 nanosecond, it will generate the carry to be 1. But here, what is the scene? Here the scene is, if this guy was 0, then what is the carry it is generating? Again, it is generating 0 carry only. That means this guy was also working at same time. So again, it will generate 0 carry only. So this carry is never getting changed. And here also the carry will never change. This guy is never changing. Only what is changing, sum is changing. So there is no delay in the circuit. If you take this guy to be 0, but if I take this guy to be 1, then what will happen? 1 plus 1 plus 0, the carry will change from 0 to 1. And if this guy is changing from 0 to 1, then 1, 0, 1, this guy will also change from 0 to 1. And if this guy is changing 1, 0, 1, this guy will also change from 0 to 1. So this will change from 0 to 1 after some delay of this block, That means this guy has to be 1. So your first bit for negative number is 1. Your second bit and third bit 0 0, and this bit has to be 1. So this should be my input. This should be my input. This is the input. Now this is the input. This is the input in 2's complement form. This is the input in 2's complement form. So again 2's complement I will take. So if I take again 2's complement, then what I am getting? 1 1 1 1. So this is your sign magnitude representation, and this is sign magnitude representation of -7. So that's why the answer is -7. Are you able to understand this question? A very good question. Excellent problem. Right? I hope you would have understood that, you would have understand the complete concept behind it, that why this was not 0, because this would be the task. Like first thing, if anyone is thinking that all should be 0, then that is wrong, because you are not going towards negative number, and if this is also 0, then what is the meaning of that? If this is 0, then there is no use of it, because if this is 0, then it is not being propagated. The carry is not even changing, but you want carry to change. From 0 to, you want it to change to some other value, and if you want it to change to some other value, that means you need to put it equals to 1 only, because 1 plus 1 plus 0 will give carry to 1. So this has to be 1 only. If in the question it was mentioned that initial carry you need to take as 1, if it is not mentioned, that means initial carry has to be 0 only. But if it is mentioned that initial carry you can take 1, then you could have taken this to be 0, because if my initial carry is 1, then carry will be changing here. But if my initial carry is 0, then you need to take this as 1. Are you getting this point or not? So two different answers are possible, -8 and -7. -8 is possible only when this guy is 1. So if this guy is 1, then answer would be -8. Otherwise the answer would be -7. Did you understand this question or not? Amazing question it is. So star mark it, and certainly it will help you a lot if these kind of questions are asked in your final examination. Okay, let's see the next. Yeah, let's see this one. Number of half adders required. What you need to tell? Number of half adders required. So what is D here? Let's simplify it. So D is C into A XOR B. E is already given as A XOR B. Why I am making it in this manner, in XOR or multiplication? Because I know that my sum bit of half adder is A XOR B, and my carry bit is AB. So from half adder I can get the AND operation, and I can get the XOR operation. Two operation I can get AND and XOR. So that's why I am making in this manner, that here XOR operation is there, AND operation is there. And what about F? So here I can see is that A bar C, let's take as it is, plus if I take A bar C plus B bar C plus A B C bar, right? So if I take C as common, so what I am getting? AB bar plus AB into C bar. So what I can see? AB XOR C. Yes or no? Right? So now I can implement it using half adders. So first I am giving my input to be A XOR B. Sorry, A and B. So A XOR B I will get as the output, and the next input would be C. So here output would be A XOR B XOR C. This is A, B. This is the sum bit, which is A XOR B. This is C bit. This will be the sum bit, A XOR B XOR C. So what I am getting? This was my E. This was my E. Right? So E I have got. What else I need? A XOR B dot C. So from here only I will get A XOR B dot C. This was my D. What is my D? This is my carry. So A XOR B dot C, because what is the carry term? Multiplication of both of the input. A XOR B dot C. Multiplication of both of the inputs. Because in half adder, if my input are AB, then from here what I will receive? Here I will receive multiplication of both of the inputs, that is AB. Now next what I need to do? AB XOR C. Next I need to do AB XOR C. AB XOR C. That means AB XOR C. So again another half adder I need to use. What will be the sum output of this one? So whatever the inputs are applied, XOR operation of these two input. What will be the carry output? The carry output will be AB into C. Multiplication of both of them. But this is what you don't need. You need E, D and F. This also you will get, but this is something that you don't need. So total half adder required are 3. So how many half adders are required? 3. Okay. So answer is 3. Yeah, so let's solve this question. A very easy question. If you know the concept, then it is easy. If you don't know, then it would be tough. So this is a multiplexer is given. From output, you are getting a feedback and it is fed to this multiplexer. Then output of this multiplexer is fed back as a select line, and then output of this multiplexer is fed back as a select line, and then the output again a select line. This is what it is going, right? So let's just say this output is some V naught. So if this is V naught, then this would be V naught. Then what would be the output here? Look, if V naught is not there, then 0 would come. If V naught is there, then 1 would come. So what is this? This is a buffer, right? This is nothing but a buffer. So if this is V naught, then this will also be V naught. What about this one? What this will be? Let's check here. If V naught is there, if V naught is not there, then 1 would come. If V naught is there, then 0 would come. So what is the output here? V naught dash. Or you can say V naught bar. Right? Now let's check for this condition here. What is the select line? V naught bar. So if V naught bar is not there, then 0 would come. And if V naught bar is there, then 1 would come. So this is 0. So here what is the answer you are getting? V naught bar. Then what will happen? V naught bar will be fed. Then this will be V naught bar, this will be V naught bar, this will be V naught. Then output will be V naught. So from V naught to V naught bar, then V naught bar to V naught, then V naught bar in that manner. The conclusion is, in a 2:1 mux, at I naught there is 0, at I1 there is 1. That means it is a buffer. Now at I naught there is 1 and at I1 there is 0. That means this is your inverter, or you can say NOT gate. What about this one? This is also buffer. So basically there is a loop. In this loop, what is the condition? In this loop, the condition is there is a buffer, there is an inverter, then again there is a buffer, and then there is a feedback. This is the condition. And all are having a delay of 3 nanosecond each. 3 nanosecond, 3 nanosecond, and 3 nanosecond. And this is your V naught. How many inverters are there? 3 inverters are there. And if there are, sorry, 1 inverter is there. 2 buffer is there, 1 inverter is there. That means odd number of inverters are there. If odd number of inverters are there, that means it is yeah. So odd number of inverter means it is a astable multivibrator, right? Astable multivibrator. And if it is a astable multivibrator, then what will be the frequency of oscillation? That would be 1 by 2 into total delay. What is the total delay? That is 9. So 1 by 9 nanosecond, that would be 55.55 megahertz. Okay, this would be the answer. Very easy. Just you need to know this is your buffer, this is your inverter, and this is your buffer. This we have already seen in our class notes as well, right? Let's move to the next. Yeah, so let's see this one. What you need to implement? You need to implement 136:1 multiplexer from 4:1, right? So how do we do this kind of question? Like there are 136 input line. Total 136 input line should be there, but you have 4:1 mux only. That means your one multiplexer can take only 4 lines. One multiplexer can take only 4 lines. So how many multiplexer you will require at the first stage? So you will require 4 3s are 12 and 34. So you will require, from here you will require 34 mux. Now you are having 34 outputs. Basically here you have put 34 mux, right? Here you have put 34 mux. Now you will have 34 outputs. Now these 34 outputs will be input of other mux. Now one mux can take 4 select line. One mux can take 4 select line. Sorry, not select line, really sorry. One mux can take 4 input. There are 2 select line. Forget about the select line. One 4:1 mux can take 4 inputs. It can take 4 inputs, right? So how many inputs are it needs to take? 34. It needs to take 34 inputs. So how many mux will be required? 9. Like 8 4:1 mux. 8 4:1 mux. How many inputs they can take? 32 input they can take. Because one 4:1 mux takes 4 input. So 8 can take 32. But you require 34. That means 2 more you require. 2 more. So either you can use the 2:1 mux, but you don't have 2:1 mux. You have 4:1 mux only. So here you will require another 4:1 mux, right? So from here what you will get? You will get 9. So basically now in the second stage we have connected 9 mux, right? So if there are 9 mux, that means there will be 9 outputs. How many outputs will be there? 9 outputs will be there. 9 outputs will be there. Now to take these 9 outputs, how many 4:1 mux will be required? So 9 by 4 if I do, so 3 4:1 mux will be required. Why is that so? because two 4:1 mux can take 8 input. So one input will be taken by another 4:1 mux. So now here you will connect 3 4:1 mux. Now from these 3 4:1 mux, 3 output lines will be there. So these 3 output lines can be taken by 1 4:1 mux only, right? So this can be taken by 1 4:1 mux only. So basically 3/4. So this will be. Or the simple thing is, always you need to take least integer function. Just take the least integer function of these calculation. Just start from here 34, then 34/4. What do you get? 8 point something. That means you need to take 9. Then 9 goes here, 9/4. What do you get? 2 point something. That means you need to take 3. Then 3 goes here, 3/4. What do you get? 1. At 1 you need to stop. So if I add them up, what do we get? 10, 13, 47. So what is the answer? 47. Okay. So this is the way. This is a good question, you can say. Now this is an excellent question, and those who have studied this topic on a surface level, they would have certainly matched it up. The answer is 1, 4. You would have clicked on 2, 3. Now what is the mistake that you are doing? You are solving it without making K-maps. This is the mistake that you are doing. If you solve it without making K-maps, then you are mistaken, right? So let's solve it. Now what is the scene? Priority encoder is there. Pre-priority I have written. Priority encoder it is. Has these inputs D3, D2, D1 and D0 in the ascending order of priority. So here also there is an error. This should be D0. So I will modify this one, and this spelling also I will modify. So now what they are saying is that D0 is prioritized over D1, D2, D3. That means your maximum priority is D0. Your priority is D0 this time. That means if I click on the D0 button, that means no matter if I have clicked on D1, D2 or D3, the output will be given with respect to D0. And how the output will be given? With respect to the D3 output will be 1, 1. With respect to D2 output will be 1, 0. D1 output will be 0, 1. And with respect to D0 output will be 0, 0. Are you getting this point? Now can you make the truth table? Yes. Now let's see the truth table now. And what is the expression of the reduced expression of output AB is, where here AB, what is MSB, what is LSB, that is not given. So I will name this one as well. This is MSB, this is LSB. So this modification I will do in the question itself. So when you see the question in the test series, you will see these modification already, right? So okay, let's start. So who is my priority? My priority is D0, D1, D2, D3. So my priority is D0 this time. Usually when we study this priority encoder, we take D3 as the priority, right? And these will be our output. So if I have clicked on D3, that means D2 should not be clicked, D1 should not be clicked, and D0 should not be clicked. So if this is the scene that you are only clicking on D3, then this will be the output you will be getting. If you have clicked on D2, then even if you have clicked on D3, that doesn't matter, because D2 is our priority. So this will be the output you will get. With respect to 2, you will get 2 is 1, 0. If you have clicked on D1, then D1 is our priority, no matter whether you click on D2 or D3, or you don't click on D2, D3. If you have clicked on D1, then D1 will be our priority. 1 will be our priority. And if you have clicked on D0, then 0 will be our priority. And if you don't click anywhere, if you don't click on any button, then output will be don't care. So these 5 output you should be habitual of writing. Are you getting this point or not? Usually people forget this one. This is very important. Usually people forget this one, that what will happen if I don't click on any button. If you don't click on any button, then output will be don't care. It could be 0 as well, it could be 1 as well. So you don't care about that. So let's make the table for A now. Now what people would have done, what a student usually think is that, so when A is becoming 1, so A is becoming 1 at these 2 points. So A is becoming 1 when D0 is not there, D1 is not there, D2 is not there, and D3 is there, plus when D0 is not there, D1 is not there, and D2 is there. So this is what student does, and then they take D0, D1 common, and then they say D2 plus D2 bar D3. So our answer is D0, D1 bar, D2 plus D3. Absolutely wrong. Why it is wrong? Because you would have clicked on which answer? D0, D1 bar, D0, D1 bar, D2 plus D3. Yeah, you would have clicked on option B. So that is also absolutely wrong, because you did not even use the K-map. You did not even use this condition. So let's make the K-map, and you will see we will get another reduced expression, a better expression we are going to get. Okay. So when I was teaching this topic, this has been taught in YouTube itself. So there also I told this concept, that you always solve the problem of priority encoder using K-map. Luckily till this time all the questions that has been asked in the GATE examination, those could be solved without using K-map. So people think that it should be solved without using K-map. No. You are not even taking this condition into action. No. Let's check that out. What I mean to say is that. So here, this is D0, D1, D2, D3. 0, 0, 0, 1, 1, 1, 1, 0. So if 0, 0, 0, 0, 0, 1 is there, that means 1. If 0, 0, 0, 0, 1, 1 is there, or 0, 0, 1, 0 is there, then also it will be 1. Are you getting this point? 0, 0, 1, 0, 0, 1. Then my D3 is don't care. D3 is don't care. Even if it is 1 or it is 0, it will be 1 only. I am not writing all 16 inputs here. Nah, all 16 input I am not writing. Okay. And now what about the don't care? This is the don't care condition. 0, 0, 0 is the don't care condition. Now what do you see here? What do you see here? What do I see here is that this is something that I am getting. So what is my output? My output A is simply this line, that is D0 bar D1 bar. So answer is D0 bar D1 bar. There you go. So this is the correct answer. A very good question. Okay, I would say a very good question. Now what about B? So if you solve blindly, then this option you will be getting. But if you solve by K-map, then this option you will get. Let's check for B. Okay, so always solve with respect to K-map. Don't solve blindly. So last year as well, as far as I remember, there was a question on priority encoder. Luckily, I thought that when I saw this question, I thought that okay, my question has come in GATE examination. But again, luckily, that question could have also been solved without using K-map, and you are getting the same answer only. But ideally, you should always solve with respect to K-map. Okay. But in the future, what I feel is that they will frame these kind of questions where using K-map and without using K-map, different answer are given. So in the future, I can expect these kind of questions to be coming. And I'm not sure last year this question was asked and why people were calling that MTA. I'm not sure. Okay, a lot of people were calling that MTA. That would be MTA. Why is that so? Still, it is unknown to me. Because that was very straightforward. That was a standard question. Like those questions you can find in textbook as well. Yeah, so let's start now. So let's see the truth table here. What is the scene? When it is 1, 0, 0, 0, 1. 0, 0, 0, 1, it is 1. 0, 0, 0, 1, it is 1. And what else? 0, 1 and then don't care. 0, 1 and then don't care about D2, D3. Then it is 1. And then for 0, 0, 0, 0, it is don't care. So this is the condition, right? So where I can see now, this is a group of 4 and this is also a group of 4, right? So what will be the expression of B here? The expression of B I can check here is that this is D0 bar D1 plus, and in this group what is constant? D0 bar is constant and D2 bar is constant. So D0 bar and D2 bar. So here you can see extra term D3 is there, that will not come. When that D3 will come into action, if you don't take this don't care into action, if you don't take this don't care into action, then this will be the this will be the loop we will be getting. So then that answer would be there. Okay, so always solve with respect to K-map only. So this is the B answer. So 1 and 4 are correct. Okay, so let me modify this question. Here a lot of error are there. A should be MSB, B should be LSB. So I will modify it. Okay, fine. Yeah, so let's see this one. This is a good question. Borrow out you need to write down for a full subtractor. So what is the borrow out if you remember? That is written as AB plus BC plus CA. But there would be bar would be there at the first term. What is the first term? B. So bar would be there on B. So AB plus BC plus CA. What is the other way of writing it? The other way of writing it, AB plus CA XOR B. But bar will be there on B. What is the other way of writing it? AC plus BA XOR C. But bar will be there. And BC plus A B XOR C. But certainly bar will be there on B. So these are the way of writing it. This is same as carry out of a full adder. Carry out of full adder will be written in the same manner, just B bar would not be there. Here there will be B bar. So this is the way of writing it. Now we can verify. AB bar plus B bar C plus CA. First option is no doubt correct. Second option is wrong because here there is a bar on C and whatever it is. Now this one, AB bar plus C into A XOR B bar. That means what I can do is that This is your AB bar plus C. A XOR B bar. This can be written as A XOR B, right? So option B. What about the third one? AC plus B bar A XOR C. So 1, 3 and 4. A very good question. Just you need to write down the B out. Okay. Yeah, so this is 32-bit binary parallel adder. How many half adders and OR gate will be required? So don't remember any formula, don't mug up any formula. Simply what you are making 32-bit binary parallel adder. That means you will require 31 full adder plus 1 half adder, right? 31 full adder, 1 half adder would be there because C will be 0, right? Now 31 full adder. 1 full adder is made of 2 half adder plus 1 OR gate. Right? So 31 into 2 is 62. So 62 plus 1 is 63 half adder plus 31 OR gate. So 63 half adder plus 31 OR gate. 63 half adder plus 31 OR gate. So that's the answer. Well and good. Yeah, so 5-bit look ahead carry generator. Look ahead carry generator. I'm not talking about look ahead carry adder. In look ahead carry generator, that particular circuitry, here there will be half adder, here there will be some circuitry in between, and then there will be XOR gate. So this is the circuitry of look ahead carry adder. This is complete look ahead carry adder. But I am talking about only look ahead carry generator. I am talking about only look ahead carry generator. So what they are saying, in look ahead carry generator, the value of alpha is number of AND gate. So how many number of AND gates are required? That is n into n plus 1 by 2. Right? And how many OR gates are required? That is n only. If you remember the circuitry, and what gate was there, and then there was a big OR gate. Then and gate was there, then there was a big OR gate. Right? So what is the value of n? That is 5. So 5 into 6 by 2, 15, and this will be 5 only. So alpha plus beta is 15 plus 5, 20. So usually these kind of questions are only asked from look ahead carry adder, but still if they ask some more, then you can think about delay problems as well. So delay problems also we have seen in look ahead carry adder, but if you need to revise it, you can revise it. Otherwise, usually only this kind of question has been asked from this particular topic. Okay, so this is the answer. Yeah, so let's see the solution of this question. So here what they are saying, gate 1 has a delay of 4 nanosecond and gate 2 has a delay of 2 nanosecond. AB initially were at 0, 0. So if they were initially at 0, 0, then what does that mean? That output P and Q would have been at 1, 1, right? It was 0, 0, 1, 1. If this is 0, then any of the input of NAND gate is 0, then output will be 1 only. Now output PQ at the steady state, what that would be if it is changed to 1. Now if it is changed to 1, so at steady state they are asking the output, right? So this has lower delay, that means this is faster. This guy is faster, right? Now this one would have reached here and this one would have reached here. But who is faster? This guy is faster, right? This 2 nanosecond guy is faster. So 1 NAND with 1, what will be the output? 0. So Q will go to 0 because this is faster. So this will go to 0 first. This guy will go to 0 first. Now this 0 will come here. Now what is 1 NAND with 0? 1 NAND with 0 will be 1 only. This is not the output at some 2 nanosecond or 3 nanosecond or 4 nanosecond. This is the output at steady state. Now what may happen is that some guy will start analyzing, that they will say they can start analyzing at 1 nanosecond, 2 nanosecond, 3 nanosecond. I am talking about steady state. How do you analyze at steady state? At steady state, the way of analysis is that you take both of the outputs here. One goes here, one goes here. Now which one is faster? This guy is faster. If this guy is faster, that means this will reach to 0 first and then this 0 will go here and then 1 NAND with 0 will give me 1. Are you getting this point? So P will be at steady state, P will be at 1 and Q will be at 0. So 1, 0, this is the answer. If they had asked at some particular time, then the answer would be different. What I mean to say is that, look, this was 0, 0, then output was 1, 1. This is the condition at t equals to 0 nanosecond. This is the condition at 0 nanosecond. This is the condition at 0 nanosecond. Now at 0 nanosecond, these two guys became 1. Now this one is going here. This one is going here at 0 nanosecond only. And this one is also going here at 0 nanosecond only. Now 1 NAND with 1. So this will be 0 but after 2 nanosecond. Are you getting this point? Now this one has gone here, 1 NAND with 1. So in between, this guy will become 0. But after how many time? 4 nanosecond. So at 4 nanosecond, this guy will be 0. Now what will happen is that this 0 will come here. So you can keep on analyzing. In that manner, you keep on analyzing. This 1 will go to 0 at 4 nanosecond. So you again analyze that at 4 nanosecond what is happening. This is 0, this is 1. So 1 and with 0, what it will become? It will become 1 again. At how much time? 4 plus 2, 6 nanosecond. Then this guy will go there. In that manner, you can keep on analyzing. But if you need to analyze at steady state, so what is the way of analyzing at steady state? The way of analyzing at steady state is, initially both were at 0, 0. That means output were at 1, 1. Now this one will travel here, this one will reach here, this one will travel here, this one will reach here. But which one will give the output first? This one will give the output first, because this is faster. If this is faster, that means 1 NAND with 0. What it will give me? This one has reached here. So 1 NAND with 0. It will give me 1 only. Wait a second, what is the scene? 0, 0. This one has reached here. This one has reached here. Okay, yeah. Now the input has changed to 1. Now the input has changed to 1. Both of the inputs have changed to 1 now. So 1 NAND with 1. What it will give me? 0. Since this is faster, then this 0 will reach here at steady state. Now 1 NAND with 0. What it will give me? It will give me 1. Because this is late. So this is the output at steady state. This is the analysis at steady state. So this is a very confusing point sometimes for the student, that sir, how you are analyzing this, that this is faster, this is giving me output early. Because this is the analysis at steady state. At steady state, you can say that this will be giving eventually the faster output. That means this 0 will go here and this will be 1 only. 1 NAND with 0, that would be 1. So this is the answer at steady state, not at some particular time. So you can analyze in between at some particular time, but at steady state 1, 0 will be there. You can analyze it using different example. You can analyze it at steady state. You will get 1, 0 only. Okay. So this is a good point which is usually missed by a lot of aspirants. Yeah. So this is a good question on FSM. Usually we don't study making the FSM. So if you want to study it, then on YouTube only I have uploaded a playlist regarding FSM. So you can go, not playlist, sorry, there are some videos regarding FSM. So you can go and check out. So here I am not going to give the complete concept. Here I am just going to tell how to solve the method, how to solve this particular question. Okay. So what we are doing? We are making a FSM for detecting 0, 0, 1, 1. So this is what we are doing. And S1 is the initial state. What they are finding, what they are asking, what will be the next state from S3 if the input is 0. So basically what is the scene? From S1 we are going, if applied input is 0, then we are going to the next stage. If applied input is again 0, then we are going to the next state. If applied input is again 1, then we are going to S4. And then if applied input is again 1, then we have detected the sequence and we are going to state S1. This is what we are doing. So if I am at state 1, that means I have detected 0. If I am at state 3, that means I have detected 0, 0. And if I am at state 4, that means I have detected 0, 0, 1. Okay. Now what they are saying, what will be the next state if input is from S3, if the input is 0. That means if you are here 0, 0, and now again 0 is applied. So what you will do, you will look for the best case. What is the best case? 0, 0. Can you see 0, 0 anywhere? Yes. So I will come back to S3 only. What I am doing here, I am not going to tell the complete concept. The concept is you are at S3. Now what is the next number? The next input applied is 0. So now you cannot go to the next state, because what I am detecting 0, 0, 1, 1. So now the next number is 0. That means now the sequence is 0, 0. So you cannot go to the next state. So you need to go to some previous state. Either you can go to S3 or S2 or S1. So what do? You start from the backward. You take the maximum number. 0, 0 you can take. You cannot take 0, 0 because 0, 0 is not detected anywhere. You start from here. You see the 0, 0. So can you see 0, 0 here? I can see a single 0 here, but I can see 0, 0 here. So I will go to S3. So if applied input is 0, then I will go back to S3 only. The next question is of same kind only. The next question is ditto the same kind. So we will solve that next question here only. What they are saying, what will be the next state from S4 if the applied input is 0? So from S4 if applied input is 0, that means if you are at S4, that means you have already reached 0, 0, 1. Now the applied input is 0. So again you will look for the best case. So for best case is 0, 1, 0. Can you see 0, 1, 0 anywhere? No. I cannot see 0, 1, 0 anywhere. Then I will look for the second best case, that is 1, 0. 1, 0. Can I see 1, 0 anywhere? This is 0, this is 0, 0. No, I cannot see. Now I will look for the next best case, that is single 0. So yes, I can see single 0 anywhere. What is that? That is your S2. So this 0 I can see here. So best case is S2. So if the applied input was 0 here, then I would go to S3 only. If the applied input is 0 here, then I will go to S2. Now I can complete it. How I will complete it? So in S2, if my applied input was 1, in S2 if my applied input was 1, that means if I am at S2, that means I have directed 0. If I am at S3, that means I have directed 00, and if I am at S4, that means I have directed 001. Now at S2, if my applied input was 1, then I will look for the best case, that is 1 only. So can I get 1 anywhere? No. That means I will go back to S1. Are you getting this point? So I will go back to S1. So what is that? If my next number was 1, then giving the output to 0, I will go back to S1 only. And what about S1? If the applied input was 1, then again you will start from here only. If applied input was 1, giving the output 0, I will start from S1 only. So this is the complete diagram. So like when I was teaching this concept, then people were thinking that how the questions can be framed in MCQs from this concept. That you are making these diagrams, this can be asked in interviews, this can be asked in like anywhere in interviews, but how you can frame MCQ? This is how I can frame MCQ from here. Although this question is taken from NPTEL, so if these kind of questions are there in NPTEL, then certainly it can be asked in your examination as well. So this is taken from NPTEL although, but still this is how the questions can be framed. That what will be the next state, they will make the half diagram and then they will ask what will be the next state. So here for the next question answer would be S2. Okay, they could have asked the same question for S2 as well, that if the applied input is 1, then what will be the next state? The answer would be S1. And they could have asked the same question for S1 as well, if the applied input is 1, then what will be the next state? That would be S1 itself. So this is how you need to study it. Like a lot of students I know, like this is there in no notes, in nowhere in any notes this concept is not there. So that's why I have uploaded it directly on YouTube itself. You can go and check out the content there. There we have made the FSM for 3 different sequence. Like even if you are detecting 3 sequence in one FSM only, you can make it. So how many states will be required, how to make the diagram, that is a very good concept. And if they want to frame a good question from FSM, then they will frame these kind of problems. So you can go and check out. Okay, let's move to the next. Yeah, so this is a shift register we are having, which is having an initial content of 40. Now what they are asking, now how many clock pulses are required to get the content of register to be 0001? This is what they are asking. So initially 00, this is the 00, right? This is 00. This 00 is fed here. This is 0 and this 0 is fed here. This 00 is fed here. Then what will come out? From here 1 will come out. So this has happened at t equals to 0 before the clock. Before the clock only this has happened. What I mean to say is that this 0 would have already come. This 0 would have already come, and 00 it would have given I naught as the output. What is I naught? That is 1. So this has happened at t equals to 0. Now first clock trigger will come. Now the first clock trigger will come. Now if the clock trigger has come, then what it will do? It will push this one inside. This one has been pushed inside and the final 0 will be gone. So 1 0 has been inside, and this final 0 would have been collected here. That I don't care, right? Now what will happen? Now these 2 zeros will go here. Now these 2 zeros will go here. What it will give? Again it will give 1. So what will happen? Again it is giving me 1. So another clock pulse will come. Just as the clock pulse is coming, this 0 will be again, this 1 will be again pushed inside. So this 1 is pushed inside. Now this 1 was already there, then 00. Now what will happen? Again 00 will go. Again 1 is there. Again clock will come. Again 1 will be pushed inside. So 1, 1, 1, 0. This 0 is gone, right? Now what is the scene? Now here, now the content of register is 1, 1, 1, 0. So now 1, 0 will be fed here. What I mean to say is that now the content is 1, 0. So now this guy is 1 and this guy is 0. So which is MSB? Certainly S2 has to be MSB. S2 has to be MSB because S2 is the larger number. So 0, 1 is applied actually. So what do you mean by 0, 1? That means I1 will go out. So here 0 will go out now. Are you getting this point? What I am saying? Here S1, S2 is 1, 0 now. But S2 has to be MSB, no? S2, S1. Although it is not written in the question, I will write it down. But S2 has to be MSB because S2 is the larger number. So now what Mux will say? Mux will say that I will take out I1. How I1 will be taken out? As 0. So I1 will be taken out as 0. So just as the clock cycle comes, what will happen? This 0 will be pushed inside and this will be 1, 1, 1. Right? Now what will happen? Now content of these two guys is 1, 1. So here what will happen? Here 1, 1 will come now. Here 1, 1 will come. So since 1 1 has come, that means from here I3 will come out, that is 0 only, and just as the clock cycle comes, this 0 will be pushed inside, right? 0 is pushed inside. Then another clock cycle will come because of 1 1, because of 1 1, what will happen? Again 0 will be pushed inside, again 0 is pushed inside. So what is the register of the content now? 0001. So how many clock cycles you require? 1 2 3 4 5 6. So answer is 6. A very good question, but these kind of questions should be solved by you. Just here the confusion is, then when the 0 or 1 will be pushed inside, it will be pushed inside just as the clock cycle comes, because from here to here there is no delay. Basically this 0 will come here, this 0 will come here, and whatever the I0, I1, I2, I3 you get here, it will have no delay. Basically these bits will come and it will give some output, and then clock cycle will come and it will be pushed inside. So just as the clock cycle comes, everything will be running, right? So at 6th clock cycle you are getting 0001. Yeah, fine. Now this is also a good question. There is very high chance that you may mess it up. How you will mess it up? Because the thing is, like, initial condition A B C D E F is, this is the initial condition. Although I should have framed this question as NET, then there would be higher chance of messing it up. And since this is a MCQ, then I guess there would be some guys who would have got it correct. Now what is this? This is a ring counter. So in ring counter what happens? This one will go here and then it will be pushed in the other direction. Basically this one will go here, then this will be 0 0 0 0. Now what will happen to this 0? This is a toggle state, right? You can see here, this is a toggle state. So in toggle state what happens? Output toggles, but negative edge triggered. You can see here, neg is triggered. This is negative edge triggered toggle state, right? So when your E goes from 1 to 0, at that time it will toggle. When your E goes from 1 to 0, it will toggle. Say yes or no? So it has toggled. What about the ring counter? Ring counter will keep on performing its operation. Ring counter will keep on performing its operation. Its operation is to push this one to the right side. So this is pushing this one to the right side. Then again it will do the same thing. So you are thinking that here, this is the mode of your counter. So you are thinking that 1, 2, 3, 4, 5, 6. Answer should be 6, option 1. That is wrong. Why is that so? Because when this E bit was going from 1 to 0, this has toggled. Now your E bit is going from 0 to 0. Will it toggle? No. 0 to 0, will it toggle? No. 0 to 0, will it toggle? No. 0 to 1, will it toggle? No. This is negative edge trigger, no. So this will be at 1 only. So are these two guys same? Absolutely not. So no, this is not the mode of counter. This is not the mode, right? Now what will happen? Again ring counter will keep on working. Again ring counter will work. How it will work? This one will be coming here. Then zeros will be pushed towards the right. Now again this E has gone from 1 to 0. If the again E has gone from 1 to 0, that means counter will again toggle now. This counter, sorry, not counter, this flip-flop will again toggle now. So 1 to 0 it will go. Toggle means just a complement of the previous state. If it was 0, then it is 1. If it was 1, then it will be 0. So again it has toggled. So 1 0 0 0, this is what you are getting. So again this is not the mode of counter because this is not similar to any other state. But let's check out what else happen. So what will happen now? Now this one will be keep on shifting. Since you are going from 0 to 0, so this state will not change. This one will keep on shifting 0 to 0. This state will not change. Since now still the state is not changing. Now this state I have got. So this state is similar to this one. So yeah, these are the states we will get. Now what will be the next state? In the next state what will happen? Counter will work as it is. Sorry, ring counter will work as it is. This one is going here, it will work as it is. Since it is going from 1 to 0, that means again it will toggle. So this will become 1. So now the states are being repeated. Now the states are being repeated. So what is the mode? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the mode is 10. Some guys will understand here and then they will do the double. 6 into 2, 12. Some guys will say answer would be 11, but the answer is 10. 6 plus 4, 10. And this is how you need to analyze it. So I always say in the questions of counter, never ever go by any method. Like people remember that frequency of output will be f to the power f divided by 2 to the power n, and these kind of formula people remember. So I never ever recommend remembering this formula. in our test series only, you will frame we will see a lot of questions where all these methods will fail. So that's why I always say, whenever you get a question from digital electronics, rather than your memory, believe in yourself, believe in your concepts. In digital electronics, concepts are much greater than your memory. Okay, so just see the circuit and solve it. Same goes for network analysis, same goes for analog electronics, same goes for control system, and same goes for signal system. In EMFT, I always say that remember the formula, but remember with the assumption. In EMFT, assumption is also important. Remember the formula, but remember with the assumption. In communication system, remember the formula, but remember with the derivation. Because there, if you know the concept, how the formula is derived, then that is very helpful for you. And in EDC, I usually say that you remember the formula, because most of the questions are framed based on formula only. So this is how, in some subjects, formula are important, and in some subjects, formula are not important at all. So digital electronics is one of the subjects where you should not apply any single formula. You should go with the concept. Okay, so let's see the next one now. Yeah, so in this one, you need to do Moore to Mealy conversion. So this is something that I did not include in my notes. When I was teaching you FSM, I did not teach you how to convert from Moore to Mealy or Mealy to Moore. But I guess since we have spent like 6 to 7 hours on FSM, so I guess you will be able to do it correctly. How will you do it? In what we need to do, this is a Moore machine, we need to go to Mealy. So what we are going to do is that in Q naught, if input A is applied, then you will come back to Q naught only, giving the output to be 0. If input A is applied, you will come back to Q naught only, giving the output to 0, right? In Q1, if input B is applied, you will come back to Q1 only, giving the output to 1. Now in Q naught, if input B is applied, you will go to Q1. Now the doubt will be whether the output will be 0 or it will be 1. The output will be 1. That means the output of next state you need to write. And from Q1, if I am going to Q naught, from Q1, I will go to Q naught if the input is A. But what will be the output? Output of the next state where I am going. So that will be 0. Okay, so answer A is correct. So this is how we convert. Now from here to here, this conversion also you can do, right? This conversion also you can do, and this conversion also you can do. This is just a small topic which I think I should have taught already in the notes only, but in the notes I forgot it. So in test series you are going to revise it now. Well and good. Okay, let's go to the next. Yeah, so let's see this question. This is also a decent enough question. So what they are saying, a 4-bit register converts a binary number stored in its register to 2's complement form. When input is 1, when x is equals to 1, it will convert it, and when x equals to 0, it will keep it as it is. The flip-flops used are T flip-flop, determine the inputs of T flip-flop. That means you need to determine TA, TB, TC and TD. Assume TA to be MSB and ABCD. Here in the options, ABCD are referring to QA, QB, QC and QD. So did you understand what they are saying? Now you are not going to design complete sequential circuit. What they are saying is that you have designed a sequential circuit in a manner that, let's just say in your sequential circuit you have stored any value. That means this will be your T flip-flop, no? These will be your T flip-flop. So these T flip-flop will have certain output. Now these outputs are, let's just say, kept in a box. What is the use of a flip-flop? Flip-flop is used to store 1 bit of data. Flip-flops are used to store 1 bit of data, right? And those stored bit of data is known as register. So whenever you see this word register, what does that mean? That means data has been stored in flip-flops. That's it. So whatever the output that you have got, let's just say this output was 1011. Now in this register, if you apply the input to be x equals to 1, if you apply input x equals to 1, then what it will do? It will calculate its 2's complement. So what will be the 2's complement? 1 will be as it is, this will be 0, this will be 1, this will be 0. Now don't say that, sir, this 1 will remain there as it is because this is a sign bit. No, this is not a sign bit. If they are saying you are calculating 2's complement, that means they have ignored the sign bit. This is the magnitude bit. This is not the sign bit. So 1 will be as it is, 1 will be complement to 0, 0 will be complement to 1, 1 will be complement to 0. So if applied input is x equals to 1, then this will be the output you will be getting. That means if this is your QA, QB, QC, QD, then your QA plus will be this guy, QB plus will be this guy, QC plus will be this guy. and your QD plus will be this guy. Are you getting this point? This will be your QD only. Basically, if your QA, QB, QC, QD was 1 0 1 1, then your and applied input is x equals to 1, then your QA plus should be 0, QB plus should be 1, QC plus should be 0, and Q0 plus should be 1. This is what they are saying. That means what should be your TA? What is your T? T is equals to Q XOR with Q plus. What is Q plus? Q plus is next state. Basically, Q plus is your Qn plus 1. And what is your Q? Q is Qn. This is just my notation. This is how I represent. Okay, in the textbook as well, you can see these kind of notation. In the examination as well, these kind of notation can come. And in a lot of NPTEL lectures as well, you will see these kind of notation. This is very rarely used. Okay. Yeah. So what I was saying. So what will be your TA? 1 XOR with 0, 1. What will be your TB? 0 XOR with 1, 1. What will be your TC? 1 XOR with 0, 1. And what will be your TD? That should be 0. So this would be your TA, TB, TC, TD. Considering your X is 1. Considering your X is 1 and QA, QB, QC, QD are this guy. Basically, you are not going to design the complete sequential circuit. You will match by the option. What you will match is that in which of the options I am getting this condition. That if I put my QA equals to, if I put my QA equals to 1, which is shown by A only. So if I put my A equals to 1, B equals to 0, C equals to 1, and D equals to 1, and X equals to 1, then my TA should be equals to 1, TB should be equals to 1, TC should be equals to 1, and TD should be equals to 0. In which of the option this is being satisfied? Okay. So last option is gone because that is completely 0, 0, 0, 0. Let's see the first one. This is also gone because this is 0, but TA is becoming 1. Let's see the third one. So in third one, this is 1. First bit is 1. So we need to hold here. Now D into X. What is D into X? 1 only. So TB is also 1. What is this? C plus D into X. C plus D into X. So this is also 1. And what is TD? That is also 0. So we need to hold here. What about this one? 0 plus 1 into 1. 1 only. C plus D 1 plus 1 into 1. This is also 1. D plus X. This is also 1. And 0 is also 0. So we need to hold here as well. So two options are still matching. Now we need to take another example. So in the same manner, you take another example. Or what you can do is that you can put X equals to 0 here. If I put X equals to 0 here. If I put X equals to 0. So at X equals to 0, it doesn't do anything. What do I mean to say is that QA, QB, QC, QD. These are my values, right? QA, QB, QC, QD. So let's just say these were the values 1, 0, 1, 1. Now if I take X equals to 0, so what will be the next state? QA plus, QB plus, QC plus, QD plus. Why I am writing it B again and again? QD plus. So if X is equals to 0, that means they will not do anything with that. That means 1 will be equals to 1 only, 0 will be equals to 0 only, 1 will be equals to 1 only, and this will be equals to 1 only. Are you getting this point? If your X is 0, that means this state will not change. Right? So what should be your TA? TA, TB, TC, TD. So what I need to do? What is my T? T is Q XOR with Q plus. 1 XOR with 1, 0. 0 XOR with 0, 0, 0, 0. So basically if X was 0 here, then all should be 0. All should be 0. All these guys should be 0. So if you put X equals to 0, then all these guys should be 0. But here what I see is that they have fixed this 1, which is wrong. If I put X equals to 0 here, if I put X equals to 0 here, this is 0. If I put X equals to 0 here, this is 0. If I put X equals to 0 here, this is 0. 0 is already 0. So what is the correct answer? Option 3. So that's why I say again and again, in digital electronics, focus more on your understanding. Just see the question, try to understand what they are saying, and try to build the logic. This is an aptitude problem which a 8th or 9th standard guy also can solve. But just you need to understand it, what they are saying. You know what is the meaning of 2's complement. You know what is the characteristic equation of T flip-flop. You know every single thing about it. Just you need to see it and try solving it. That's it. So if you build good practice, that's why I am making these kind of questions in the test series. So if you build good practice, then you will be able to solve it very quickly in the examination. Let's move on to the next one. Yeah, so let's see this question. This is a good question, but I know like you might have got this answer to be correct. In your test series, you might have got this answer to be correct, but you are still watching the solution because you need to understand the concept, right? Because if you play with these values, right, n into 1 by 2.25 mega is equals to 0.48 milli, then you will get the answer. But how this expression came, let's understand. Like, let's understand the meaning of this question. What they are saying, that we are designing a delay circuit. For designing the delay circuit, what you are using? You are using a set of register. That means you are using some flip-flops. So how many flips are required in serial register? Both input and output are in serial. That means you are making a serial in and serial out shift register you are making. So how many flip-flops will be required to produce a delay of 0.48 millisecond? So forget about this question. Let me tell you what they are saying. So you are having a register. Okay. You are having a register where, let's just say, there are 4 flip-flops. Here there are 4 flip-flops. Right? Now what do is that you take an output bit from here. Basically you are standing here. Whatever the output you get at this flip-flop, that will be your final output. And now you are applying an input here. This is how you are applying the input, and whatever the bit you are getting here, that is your final output. Okay. Now what do is that you kept all these in a box. Now this has been kept in a box. So what user can see? User can see only the input and the output. Right? So what user did? User gave input 1 here. Initially the condition was 0 0 0 0. User gave the input 1 here. Now user will say that after how much time I will get my output to be 1. So what will happen? Initial content is 0 0 0 0. Then what will happen? 1 clock cycle will come. This 1 will be shifted inside 0 0 0. Still the output is 0 only. Another clock cycle will come. Then let's just say next bits are 0 0 0. Don't care. I don't care what are the next bit. It could be some alpha, beta, gamma, sigma. Any bits are there. So what will happen now? Now this alpha will be getting in 1 0 0 0. Now another clock cycle will come. Now this beta will be getting in alpha 1 0 0 0. Right? And then what will happen? Another clock cycle will come. Another clock cycle will come. Now what will happen is that this gamma will be here, beta will be here, alpha will be here, and this one will be here. So now this one you have got. So after 4 clock cycle, you have got this input. Are you getting this point? So the same thing we are doing now. What we are doing, we are having a shift register. Now in this shift register, I am not sure how many flops are there. I am not sure how many flip-flops are there. I don't know about that. I don't know about that how many flip-flops are there. The same thing I am doing. Sorry. Same thing I am doing. I am giving one input and I am collecting my output here. Here I am collecting my output. And I have kept all these in a box. All these I have kept in a box. Now here, let's just say initially content is all 0 0 0 0. Now I have applied an input 1 here. So after how many clock cycles? N into T clock. Let's just say these are N flip-flops. These are N flop. These are N flip-flops. So after N into T clock, you will get the output to be 1. That means it feels like that you have applied 1 here, but after some delay you get the output to be 1. This was a box, he applied 1 here, but after how much delay you will get the output to be 1? After this much delay you will get the output to be 1. Here after how much delay you get the output to be 1? So delay of this block will be 4t clock. Can you say it? That sir, if you apply 1 here, then after 4t clock time you will get the output to be 1. So delay of this block is 4t clock. Delay of this block is 4t clock. Say yes or no? Right? So what is the delay of this block? The delay of this block is nt clock. And what is that equals to? That should be equals to 0.48 nanosecond. Sorry, 0.48 millisecond. Are you getting this point? Right? So what is your t clock here? T clock is 1 by 2.25 mega. 2.25 mega, that is 10 to the power 6. That is equals to 0.48 into 10 to the power minus 3. So n value is coming out to be 1080. So again, you know everything about this question, but still it feels like an amazing. Now you know everything about this question, but still it feels like an amazing question, because like this is something that will test your aptitude only. It is completely based on aptitude. So answer is 1080. I hope you enjoyed it. Let's see the next one. Yeah, so let's see this question. How many flip-flops will be complemented in a 10-bit ripple up counter to reach the next count after the count? This one. So this is a 10-bit triple up counter. So here the mode value will be 2 to the power 10. That we don't need to care about. What we need to tell is that what is this? This is a up counter, right? This is a up counter. Since it is a up counter, what is the current condition? The current condition is this one: 1 0 0 1 1 0 0 1 1. This is the current condition, right? What will be the next count? So what guys can do is that they will convert it into decimal. If you have converted it into decimal, then what you can do, you can add 1 from there. Let's just say if I convert it into decimal, I am getting some x value, some x decimal value. Then I will get next count will be x plus 1. Then I can convert it to binary. This is what I can do. But just hear me out. Just let me know one thing. If this is my current state, then what will be the next state? 8, right? This is 7, next state will be 8. If this is my current state, then what will be the next state? 8 only. Now if this is my current state, then what will be the next state? If this is my current state, what is this? 1 2 4 8 16 32. So what is this? What this is becoming? 6 7. So this is 7. So basically this is 7 39. Next count will be 40. So how I can get 40? 40 will be 32 plus 8. So 1 0 1 0 0 0. Say yes or no? So basically if all these three are 1, then the next state will be 1 0 0. Don't care about all these guys. So same thing will happen here only, no? That if these three are 1, then the next state will be, this guy will be 1 and rest all will be 0. And don't care about these guys will be same as it is. Now when all these guys become 1, let's just say after some clock cycles, all these guys are becoming 1. All these guys are becoming 1. Now if I ask you what will be the next state? So in the next state what will happen? All these guys will be 0 and this guy will be 1. Say yes or no? But they are asking the next state from this one. So this will be the next state, right? So better than converting it to decimal than finding out the binary, just to think that here all three are 1. The next state would be, this guy will be 1 and all three will be 0. So what they are saying, will be complemented in 10. How many flip-flops will be complemented? That means they are asking how many output of the flip-flops will be complemented. Flip-flops complemented means output of flip-flops complemented. So this is complemented. 1, 2, 3 and 4. Rest all are as it is. This is a buffer. This is also a buffer. Rest all are as it is. These 4 are complemented. So these 4 are complemented. So answer is 4. Right? Answer is 4. This answer is option 3. That means 4. Okay, not 3 are complemented. So 4 are complemented. So that is the answer. Let's see the next. Yeah, so let's see the solution of this question. So here what they are saying, gate 1 has a delay of 4 nanosecond and gate 2 has a delay of 2 nanosecond. AB initially were at 0 0. So if they were initially at 0 0, then what does that mean? That output P and Q would have been at 1 1, right? Because 0 0 1 1. If this is 0, then any of the input of NAND gate is 0, then output will be 1 only. Now output PQ at the steady state, what that would be if it is changed to 1. Now if it is changed to 1, so at steady state they are asking the output, right? So this has lower delay, that means this is faster. This guy is faster, right? Now this one would have reached here and this one would have reached here. But who is faster? This guy is faster, right? This 2 nanosecond guy is faster. So 1 NAND with 1, what will be the output? 0. So Q will go to 0 because this is faster. So this will go to 0 first. This guy will go to 0 first. Now this 0 will come here. Now what is 1 NAND with 0? 1 NAND with 0 will be 1 only. This is not the output at some 2 nanosecond or 3 nanosecond or 4 nanosecond. This is the output at steady state. Now what may happen is that some guy will start analyzing, that they will say they can start analyzing at 1 nanosecond, 2 nanosecond, 3 nanosecond. I am talking about steady state. How do you analyze at steady state? At steady state, the way of analysis is that you take both of the outputs here. One goes here, one goes here. Now which one is faster? This guy is faster. If this guy is faster, that means this will reach to 0 first and then this 0 will go here and then 1 NAND with 0 will give me 1. Are you getting this point? So P will be at steady state, P will be at 1 and Q will be at 0. So 1 0, this is the answer. If they had asked at some particular time, then the answer would be different. What I mean to say is that, look, this was 0 0, then output was 1 1. This is the condition at t equals to 0 nanosecond. This is the condition at 0 nanosecond. This is the condition at 0 nanosecond. Now at 0 nanosecond, these two guys became 1. Now this one is going here. This one is going here at 0 nanosecond only. And this one is also going here at 0 nanosecond only. Now 1 NAND with 1. So this will be 0, but after 2 nanosecond. Are you getting this point? Now this one has gone here, 1 NAND with 1. So in between, this guy will become 0. But after how many time? 4 nanosecond. So at 4 nanosecond, this guy will be 0. Now what will happen is that this 0 will come here. So you can keep on analyzing. In that manner, you keep on analyzing. This one will go to 0 at 4 nanosecond. So you again analyze that at 4 nanosecond, what is happening? This is 0, this is 1. So 1 NAND with 0, what it will become? It will become 1 again. At how much time? 4 plus 2, 6 nanosecond. Then this guy will go there. In that manner, you can keep on analyzing. But if you need to analyze at steady state, so what is the way of analyzing at steady state? The way of analyzing at steady state is, initially both were at 0, 0. That means output were at 1, 1. Now this one will travel here, this one will reach here. This one will travel here, this one will reach here. But which one will give the output first? This one will give the output first, because this is faster. If this is faster, that means 1 NAND with 0. What it will give me? This one has reached here. So 1 NAND with 0. It will give me 1 only. Wait a second. What is the scene? 0, 0. This one has reached here. This one has reached here. Okay, yeah. Now the input has changed to 1. Now the input has changed to 1. Both of the inputs have changed to 1 now. So 1 NAND with 1. What it will give me? 0. Since this is faster, then this 0 will reach here at steady state. Now 1 NAND with 0. What it will give me? It will give me 1. Because this is late. So this is the output at steady state. This is the analysis at steady state. So this is a very confusing point sometimes for the student, that sir, how you are analyzing this, that this is faster, this is giving me output early. Because this is the analysis at steady state. At steady state, you can say that this will be giving eventually the faster output. That means this 0 will go here and this will be 1 only. 1 NAND with 0, that would be 1. So this is the answer at steady state, not at some particular time. So you can analyze in between at some particular time, but at steady state, 1 0 will be there. You can analyze it using different example. You can analyze it at steady state. You will get 1 0 only. Okay. So this is a good point which is usually missed by a lot of aspirants. Yeah. So this is a good question on FSM. Usually we don't study making the FSM. So if you want to study it, then on YouTube only I have uploaded a playlist regarding FSM. So you can go, not playlist, sorry. There are some videos regarding FSM. So you can go and check out. So here I am not going to give the complete concept. Here I am just going to tell how to solve the method, how to solve this particular question. Okay. So what we are doing? We are making a FSM for detecting 0, 0, 1, 1. So this is what we are doing. And S1 is the initial state. What they are finding, what they are asking, what will be the next state from S3 if the input is 0. So basically what is the scene? From S1 we are going, if applied input is 0, then we are going to the next stage. If applied input is again 0, then we are going to the next state. If applied input is again 1, then we are going to S4. And then if applied input is again 1, then we have detected the sequence and we are going to state S1. This is what we are doing. So if I am at state 1, that means I have detected 0. If I am at state 3, that means I have detected 0, 0. And if I am at state 4, that means I have detected 0, 0, 1. Okay. Now what they are saying, what will be the next state if input is from S3, if the input is 0. That means if you are here 0, 0, and now again 0 is applied. So what you will do, you will look for the best case. What is the best case? 0, 0. Can you see 0, 0 anywhere? Yes. So I will come back to S3 only. What I am doing here, I am not going to tell the complete concept. The concept is you are at S3. Now what is the next number? The next input applied is 0. So now you cannot go to the next state, because what I am detecting 0, 0, 1, 1. So now the next number is 0. That means now the sequence is 0, 0. So you cannot go to the next state. So you need to go to some previous state. Either you can go to S3 or S2 or S1. So what do? You start from the backward. You take the maximum number. 0, 0 you can take. You cannot take 0, 0, because 0, 0 is not detected anywhere. You start from here. You see the 0, 0. So can you see 0, 0 here? I can see a single 0 here, but I can see 0, 0 here. So I will go to S3. So if applied input is 0, then I will go back to S3 only. The next question is of same kind only. The next question is ditto the same kind. So we will solve that next question here only. What they are saying, what will be the next state from S4 if the applied input is 0. So from S4 if applied input is 0, that means if you are at S4, that means you have already reached 0, 0, 1. Now the applied input is 0. So again you will look for the best case. So for best case is 0 1 0. Can you see 0 1 0 anywhere? No, I cannot see 0 1 0 anywhere. Then I will look for the second best case, that is 1 0 1 0. Can I see 1 0 anywhere? This is 0, this is double 0. No, I cannot see. Now I will look for the next best case, that is single 0. So yes, I can see single 0 anywhere. What is that? That is your S2. So this 0 I can see here. So best case is S2. So if the applied input was 0 here, then I would go to S3 only. If the applied input is 0 here, then I will go to S2. Now I can complete it. How I will complete it? So in S2, if my applied input was 1, that means if I am at S2, that means I have directed 0. If I am at S3, that means I have directed 00. And if I am at S4, that means I have directed 001. Now at S2, if my applied input was 1, then I will look for the best case, that is 1 only. So can I get 1 anywhere? No. That means I will go back to S1. Are you getting this point? So I will go back to S1. So what is that? If my next number was 1, then giving the output to 0, I will go back to S1 only. And what about S1? If the applied input was 1, then again you will start from here only. If applied input was 1, giving the output 0, I will start from S1 only. So this is the complete diagram. So like when I was teaching this concept, then people were thinking that how the questions can be framed in MCQs from this concept. That you are making these diagrams, this can be asked in interviews, this can be asked in like anywhere in interviews, but how you can frame MCQ? This is how I can frame MCQ from here. Although this question is taken from NPTEL, so if these kind of questions are there in NPTEL, then certainly it can be asked in your examination as well. So this is taken from NPTEL although, but still this is how the questions can be framed. That what will be the next state? They will make the half diagram and then they will ask what will be the next state. So here for the next question, answer would be S2. Okay. They could have asked the same question for S2 as well, that if the applied input is 1, then what will be the next state? The answer would be S1. And they could have asked the same question for S1 as well. If the applied input is 1, then what will be the next state? That would be S1 itself. So this is how you need to study it. Like a lot of students, I know, like this is there in no notes. In nowhere in any notes, this concept is not there. So that's why I have uploaded it directly on YouTube itself. You can go and check out the content there. There we have made the FSM for 3 different sequence. Like even if you are detecting 3 sequence in one FSM only, you can make it. So how many states will be required, how to make the diagram, that is a very good concept. And if they want to frame a good question from FSM, then they will frame these kind of problems. So you can go and check out. Okay, let's move to the next. Yeah, so this is a shift register we are having, which is having an initial content of a 40. Now what they are asking, now how many clock pulses are required to get the content of register to be 0001? This is what they are asking. So initially 00, this is the 00, right? This is 00. This 00 is fed here. This is 0 and this 0 is fed here. This 00 is fed here. Then what will come out? From here 1 will come out. So this has happened at t equals to 0 before the clock. Before the clock only this has happened. What I mean to say is that this 0 would have already come. This 0 would have already come, and 00 it would have given I naught as the output. What is I naught? That is 1. So this has happened at t equals to 0. Now first clock trigger will come. Now the first clock trigger will come. Now if the clock trigger has come, then what it will do? It will push this one inside. This one has been pushed inside and the final 0 will be gone. So 1 0 has been inside, and this final 0 would have been collected here. That I don't care, right? Now what will happen? Now these 2 zeros will go here. Now these 2 zeros will go here. What it will give? Again it will give 1. So what will happen? Again it is giving me 1. So another clock pulse will come. Just as the clock pulse is coming, this 0 will be again, this 1 will be again pushed inside. So this 1 is pushed inside. Now this 1 was already there, then 00. Now what will happen? Again 00 will go. Again 1 is there. Again clock will come. Again 1 will be pushed inside. So 1, 1, 1, 0. This 0 is gone. Right? Now what is the scene? Now here, now the content of register is 1, 1, 1, 0. So now 1, 0 will be fed here. What I mean to say is that now the content is 1, 0. So now this guy is 1 and this guy is 0. So which is MSB? Certainly S2 has to be MSB. S2 has to be MSB because S2 is the larger number. So 0, 1 is applied actually. So what do you mean by 0, 1? That means I1 will go out. So here 0 will go out now. Are you getting this point? What I am saying? Here S1, S2 is 1, 0 now. But S2 has to be MSB, no? S2, S1. Although it is not written in the question, I will write it down. But S2 has to be MSB because S2 is the larger number. So now what Mux will say? Mux will say that I will take out I1. How I1 will be taken out? As 0. So I1 will be taken out as 0. So just as the clock cycle comes, what will happen? This 0 will be pushed inside and this will be 1 1 1. Right? Now what will happen? Now content of these two guys is 1 1. So here what will happen? Here 1 1 will come now. Here 1 1 will come. So since 1 1 has come, that means from here I3 will come out, that is 0 only. And just as the clock cycle comes, this 0 will be pushed inside. Right? 0 is pushed inside. Then another clock cycle will come. Because of 1 1, what will happen? Again 0 will be pushed inside. Again 0 is pushed inside. So what is the register of the content now? 0001. So how many clock cycles you require? 1, 2, 3, 4, 5, 6. So answer is 6. A very good question. But these kind of questions should be solved by you. Just here the confusion is then when the 0 or 1 will be pushed inside. It will be pushed inside just as the clock cycle comes. Because from here to here there is no delay. Basically this 0 will come here, this 0 will come here, and whatever the I0, I1, I2, I3 you get here, it will have no delay. Basically these bits will come and it will give some output, and then clock cycle will come and it will be pushed inside. So just as the clock cycle comes, everything will be running. Right? So at 6th clock cycle you are getting 0001. Yeah, fine. Now this is also a good question. There is very high chance that you may mess it up. How you will mess it up? Because the thing is, like, initial condition A, B, C, D, E, F is, this is the initial condition. Although I should have framed this question as NET, then there would be higher chance of messing it up. And since this is a MCQ, then I guess there would be some guys who would have got it correct. Now what is this? This is a ring counter. So in ring counter what happens? This one will go here and then it will be pushed in the other direction. Basically this one will go here, then this will be 0 0 0 0. Now what will happen to this 0? This is a toggle state, right? You can see here, this is a toggle state. So in toggle state what happens? Output toggles, but negative edge triggered. You can see here, neg is triggered. This is negative edge triggered toggle state, right? So when your E goes from 1 to 0, at that time it will toggle. When your E goes from 1 to 0, it will toggle. Say yes or no? So it has toggled. What about the ring counter? Ring counter will keep on performing its operation. Ring counter will keep on performing its operation. Its operation is to push this one to the right side. So this is pushing this one to the right side. Then again it will do the same thing. So you are thinking that here, this is the mode of your counter. So you are thinking that 1, 2, 3, 4, 5, 6. Answer should be 6. Option 1. That is wrong. Why is that so? Because when this E bit was going from 1 to 0, this has toggled. Now your E bit is going from 0 to 0. Will it toggle? No. 0 to 0, will it toggle? No. 0 to 0, will it toggle? No. 0 to 1, will it toggle? No. This is negative edge trigger, no. So this will be at 1 only. So are these two guys same? Absolutely not. So no, this is not the mode of counter. This is not the mode, right? Now what will happen? Again ring counter will keep on working. Again ring counter will work. How it will work? This one will be coming here. Then zeros will be pushed towards the right. Now again this E has gone from 1 to 0. If the again E has gone from 1 to 0, that means counter will again toggle now. This counter, sorry, not counter, this flip-flop will again toggle now. So 1 to 0 it will go. Toggle means just a complement of the previous state. If it was 0, then it is 1. If it was 1, then it will be 0. So again it has toggled. So 1 0 0 0, this is what you are getting. So again this is not the mode of counter because this is not similar to any other state. But let's check out what else happen. So what will happen now? Now this one will be keep on shifting. Since you are going from 0 to 0, so this state will not change. This one will keep on shifting 0 to 0. This state will not change. Since now still the state is not changing. Now this state I have got. So this state is similar to this one. So yeah, these are the states we will get. Now what will be the next state? In the next state what will happen? Counter will work as it is. Sorry, ring counter will work as it is. This one is going here, it will work as it is. Since it is going from 1 to 0, that means again it will toggle. So this will become 1. So now the states are being repeated. So what is the mode? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the mode is 10. Some guys will understand here and then they will do the double. 6 into 2, 12. Some guys will say answer would be 11, but the answer is 10. 6 plus 4, 10. And this is how you need to analyze it. So I always say in the questions of counter, never ever go by any method. Like people remember that frequency of output will be f to the power f divided by 2 to the power n, and these kind of formula people remember. So I never ever recommend remembering this formula. In our test series only, you will frame we will see a lot of questions where all these methods will fail. All these methods will fail. So that's why I always say, whenever you get a question from digital electronics, rather than your memory, believe in yourself, believe in your concepts. In digital electronics, concepts are much greater than your memory. Okay, so just see the circuit and solve it. Same goes for network analysis, same goes for analog electronics, same goes for control system, and same goes for signal system. In EMFT, I always say that remember the formula, but remember with the assumption. In EMFT, assumption is also important. Remember the formula, but remember with the assumption. In communication system, remember the formula, but remember with the derivation. Because there, if you know the concept, how the formula is derived, then that is very helpful for you. And in EDC, I usually say that you remember the formula because most of the questions are framed based on formula only. So this is how in some subjects formula are important and in some subjects formula are not important at all. So digital electronics is one of the subjects where you should not apply any single formula. You should go with the concept. Okay, so let's see the next one now. Yeah, so in this one you need to do Moore to Mealy conversion. So this is something that I did not include in my notes. When I was teaching you FSM, I did not teach you how to convert from Moore to Mealy or Mealy to Moore. But I guess since we have spent like 6 to 7 hours on FSM, so I guess you will be able to do it correctly. How will you do it? In what we need to do, this is a Moore machine, we need to go to Mealy. So what we are going to do is that in Q0, if input A is applied, then you will come back to Q0 only, giving the output to be 0. If input A is applied, you will come back to Q0 only, giving the output to 0, right? In Q1, if input B is applied, you will come back to Q1 only, giving the output to 1. Now in Q0, if input B is applied, you will go to Q1. Now the doubt will be whether the output will be 0 or it will be 1. The output will be 1. That means the output of next state you need to write. And from Q1, if I am going to Q0, from Q1, I will go to Q0 if the input is A. But what will be the output? Output of the next state where I am going. So that will be 0. Okay, so answer A is correct. So this is how we convert. Now from here to here, this conversion also you can do, right? This conversion also you can do, and this conversion also you can do. This is just a small topic which I think I should have taught already in the notes only, but in the notes I forgot it. So in test series you are going to revise it now. Well and good. Okay, let's go to the next. Yeah, so let's see this question. This is also a decent enough question. So what they are saying, a 4-bit register converts a binary number stored in its register to 2's complement form. When input is 1, when x is equals to 1, it will convert it, and when x equals to 0, it will keep it as it is. The flip-flops used are T flip-flop. Determine the inputs of T flip-flop. That means you need to determine TA, TB, TC and TD. Assume TA to be MSB and ABCD. Here in the options, ABCD are referring to QA, QB, QC and QD. So did you understand what they are saying? Now you are not going to design complete sequential circuit. What they are saying is that you have designed a sequential circuit in a manner that, let's just say in your sequential circuit you have stored any value. That means this will be your T flip-flop, no? These will be your T flip-flop. So these T flip-flop will have certain output. Now these outputs are, let's just say, kept in a box. What is the use of a flip-flop? Flip-flop is used to store 1 bit of data. Flip-flops are used to store 1 bit of data, right? And those stored bit of data is known as register. So whenever you see this word register, what does that mean? That means data has been stored in flip-flops. That's it. So whatever the output that you have got, let's just say this output was 1011. Now in this register, if you apply the input to be x equals to 1, if you apply input x equals to 1, then what it will do? It will calculate its 2's complement. So what will be the 2's complement? 1 will be as it is. This will be 0, this will be 1, this will be 0. Now don't say that, sir, this will be this one will remain there as it is because this is a sign bit. No, this is not a sign bit. If they are saying you are calculating 2's complement, that means they have ignored the sign bit. This is the magnitude bit. This is not the sign bit. So 1 will be as it is, 1 will be complement to 0, 0 will be complement to 1, 1 will be complement to 0. So if applied input is x equals to 1, then this will be the output you will be getting. That means if this is your QA, QB, QC, QD, then your QA plus will be this guy, QB plus will be this guy, QC plus will be this guy, and your QD plus will be this guy. Are you getting this point? This will be your QD only. Basically, if your QA, QB, QC, QD was 1, 0, 1, 1, then your and applied input is x equals to 1, then your QA plus should be 0, QB plus should be 1, QC plus should be 0, and Q0 plus should be 1. This is what they are saying. That means, what should be your TA? What is your T? T is equals to Q XOR with Q plus. What is Q plus? Q plus is next state. Basically, Q plus is your Qn plus 1. And what is your Q? Q is Qn. This is just my notation. This is how I represent. Okay, in the textbook as well, you can see these kind of notation. In the examination as well, these kind of notation can come. And in a lot of NPTEL lectures as well, you will see these kind of notation. This is very rarely used. Okay. Yeah. So what I was saying. So what will be your TA? 1 XOR with 0, 1. What will be your TB? 0 XOR with 1, 1. What will be your TC? 1 XOR with 0, 1. And what will be your TD? That should be 0. So this would be your TA, TB, TC, TD. Considering your x is 1. Considering your x is 1 and QA, QB, QC, QD are this guy. Basically, you are not going to design the complete sequential circuit. You will match by the option. What you will match is that in which of the options I am getting this condition. That if I put my QA equals to, QA equals to 1, which is shown by A only. So if I put my A equals to 1, B equals to 0, C equals to 1, and D equals to 1, and X equals to 1, then my TA should be equals to 1, TB should be equals to 1, TC should be equals to 1, and TD should be equals to 0. In which of the option this is being satisfied? Okay. So last option is gone because that is completely 0, 0, 0, 0. Let's see the first one. This is also gone because this is 0, but TA is becoming 1. Let's see the third one. So in third one, this is 1, first bit is 1, so we need to hold here. Now D into X, what is D into X? 1 only, so TB is also 1. What is this? C plus D into X, C plus D into X, so this is also 1. And what is TD? That is also 0, so we need to hold here. What about this one? 0 plus 1 into 1, 1 only. C plus D, 1 plus 1 into 1, this is also 1. D plus X, this is also 1. And 0 is also 0. So we need to hold here as well. So two options are still matching. Now we need to take another example. So in the same manner, you take another example. Or what you can do is that you can put x equals to 0 here. If I put x equals to 0 here. If I put x equals to 0. So at x equals to 0, it doesn't do anything. What do I mean to say is that QA, QB, QC, QD. These are my values, right? QA, QB, QC, QD. So let's just say these were the values 1, 0, 1, 1. Now if I take x equals to 0, so what will be the next state? QA plus, QB plus, QC plus, QD plus. Why I am writing it B again and again? QD plus. So if x is equals to 0, that means they will not do anything with that. That means 1 will be equals to 1 only, 0 will be equals to 0 only, 1 will be equals to 1 only, and this will be equals to 1 only. Are you getting this point? If your x is 0, that means this state will not change. Right? So what should be your TA? TA, TB, TC, TD. So what I need to do? What is my T? T is Q XOR with Q plus. 1 XOR with 1, 0. 0 XOR with 0, 0. 0, 0. So basically if x was 0 here, then all should be 0. All should be 0. All these guys should be 0. So if you put x equals to 0, then all these guys should be 0. But here what I see is that they have fixed this 1, which is wrong. If I put x equals to 0 here, if I put x equals to 0 here, this is 0. If I put x equals to 0 here, this is 0. If I put x equals to 0 here, this is 0. 0 is already 0. So what is the correct answer? Option 3. So that's why I say again and again, in digital electronics, focus more on your understanding. Just see the question, try to understand what they are saying and try to build the logic. This is an aptitude problem which a 8th or 9th standard guy also can solve. But just you need to understand it, what they are saying. You know what is the meaning of 2's complement. You know what is the characteristic equation of T flip-flop. You know every single thing about it. Just you need to see it and try solving it. That's it. So if you build good practice, that's why I am making these kind of questions in the test series. So if you build good practice, then you will be able to solve it very quickly in the examination. Let's move on to the next one. Yeah, so let's see this question. This is a good question, but I know like you might have got this answer to be correct. In your test series, you might have got this answer to be correct, but you are still watching the solution because you need to understand the concept, right? Because if you play with these values, right, n into 1 by 2.25 mega is equals to 0.48 milli, then you will get the answer. But how this expression came, let's understand. Like, let's understand the meaning of this question. What they are saying, that we are designing a delay circuit. For designing the delay circuit, what you are using? You are using a set of register. That means you are using some flip-flops. So how many flips are required in serial register? Both input and output are in serial. That means you are making a serial in and serial out shift register you are making. So how many flip-flops will be required to produce a delay of 0.48 millisecond? So forget about this question. Let me tell you what they are saying. So you are having a register. Okay. You are having a register where, let's just say, there are 4 flip-flops. Here there are 4 flip-flops. Right. Now what do is that you take a output bit from here. Basically you are standing here. Whatever the output you get at this flip-flop, that will be your final output. And now you are applying an input here. This is how you are applying the input, and whatever the bit you are getting here, that is your final output. Okay. Now what do is that you kept all these in a box. Now this has been kept in a box. So what user can see? User can see only the input and the output. Right. So what user did? User gave input 1 here. Initially the condition was 0 0 0 0. User gave the input 1 here. Now user will say that after how much time I will get my output to be 1. So what will happen? Initial content is 0 0 0 0. Then what will happen? 1 clock cycle will come. This 1 will be shifted inside 0 0 0. Still the output is 0 only. Another clock cycle will come. Then let's just say next bits are 0 0 0. Don't care. I don't care what are the next bit. It could be some alpha, beta, gamma, sigma. Any bits are there. So what will happen now? Now this alpha will be getting in 1 0 0 0. Now another clock cycle will come. Now this beta will be getting in alpha 1 0 0 0. Right? And then what will happen? Another clock cycle will come. Another clock cycle will come. Now what will happen is that this gamma will be here, beta will be here, alpha will be here, and this one will be here. So now this one you have got. So after 4 clock cycle, you have got this input. Are you getting this point? So the same thing we are doing now. What we are doing, we are having a shift register. Now in this shift register, I am not sure how many flops are there. I am not sure how many flip-flops are there. I don't know about that. I don't know about that how many flip-flops are there. The same thing I am doing. Sorry. Same thing I am doing. I am giving one input and I am collecting my output here. Here I am collecting my output. And I have kept all these in a box. All these I have kept in a box. Now here, let's just say initially content is all 0 0 0 0. Now I have applied an input 1 here. So after how many clock cycles? N into T clock. Let's just say these are N flip-flops. These are N flop. These are N flip-flops. So after N into T clock, you will get the output to be 1. That means it feels like that you have applied 1 here, but after some delay you get the output to be 1. This was a box, he applied 1 here, but after how much delay you will get the output to be 1? After this much delay you will get the output to be 1. Here after how much delay you get the output to be 1? So delay of this block will be 40 clock. Can you say it? That sir, if you apply 1 here, then after 40 clock time you will get the output to be 1. So delay of this block is 40 clock. Delay of this block is 40 clock. Say yes or no? Right? So what is the delay of this block? The delay of this block is N-T clock. And what is that equals to? That should be equals to 0.48 nanosecond. Sorry, 0.48 millisecond. Are you getting this point? Right? So what is your T clock here? T clock is 1 by 2.25 mega. 2.25 mega, that is 10 to the power 6. That is equals to 0.48 into 10 to the power minus 3. So n value is coming out to be 1080. So again, you know everything about this question, but still it feels like an amazing. Now you know everything about this question, but still it feels like an amazing question, because like this is something that will test your aptitude only. It is completely based on aptitude. So answer is 1080. I hope you enjoyed it. Let's see the next one. Yeah, so let's see this question. How many flip-flops will be complemented in a 10-bit ripple up counter to reach the next count after the count? This one. So this is a 10-bit ripple up counter. So here the mode value will be 2 to the power 10. That we don't need to care about. What we need to tell is that what is this? This is a up counter, right? This is a up counter. Since it is a up counter, what is the current condition? The current condition is this one: 100 11 00 111. This is the current condition, right? What will be the next count? So what guys can do is that they will convert it into decimal. If you have converted it into decimal, then what you can do, you can add 1 from there. Let's just say if I convert into decimal, I am getting some x value, some x decimal value. Then I will get next count will be x plus 1. Then I can convert it to binary. This is what I can do. But just hear me out. Just let me know one thing. If this is my current state, then what will be the next state? 8, right? This is 7, next state will be 8. If this is my current state, if this is my current state, then what will be the next state? 8 only. Now if this is my current state, then what will be the next state? If this is my current state, what is this? 1 2 4 1 2 4 8 16 32. So what is this? What this is becoming? 6 7. So this is 7. So basically this is 7 39. Next count will be 40. So how I can get 40? 40 will be 32 plus 8. So 1 0 1 0 0 0. Say yes or no? So basically if all these three are 1, then the next state will be 1 0 0. Don't care about all these guys. So same thing will happen here only, no? That if these three are 1, then the next state will be, this guy will be 1 and rest all will be 0. And don't care about these guys will be same as it is. Now when all these guys become 1, let's just say after some clock cycles, all these guys are becoming 1. All these guys are becoming 1. Now if I ask you what will be the next state? So in the next state what will happen? All these guys will be 0 and this guy will be 1. Say yes or no? But they are asking the next state from this one. So this will be the next state, right? So better than converting it to decimal than finding out the binary, just to think that here all three are 1. The next state would be, this guy will be 1 and all three will be 0. So what they are saying, will be complemented in 10. How many flip-flops will be complemented? That means they are asking how many output of the flip-flops will be complemented. Flip-flops complemented means output of flip-flops complemented. So this is complemented. 1, 2, 3 and 4. Rest all are as it is. This is a buffer. This is also a buffer. Rest all are as it is. These 4 are complemented. So these 4 are complemented. So answer is 4. Right? Answer is 4. This answer is option 3. That means 4. Okay, not 3 are complemented. So 4 are complemented. So that is the answer. Let's see the next. Yeah, so let's see the solution of this question. So these kind of circuits you have already seen. So what would be your confusion? Your confusion would be that, sir, wherever we see these kind of circuits, we have calculated our output here. But now we are calculating our output here. So will there be any changes? Like will it make any effect in the circuit? So answer is no. If it is a A-stable multivibrator, then no matter wherever you calculate the output, the frequency of oscillations will be same. If it is a A-stable multivibrator. So let's check. First thing is that you need to check if it is a A-stable multivibrator or not. So what you will do, this I have already told you, that you need to look into the loop. In the loop, how many inverters are there? 1, 2, 3, 4, 5. 5 inverters, that is equivalent to 1 inverter. That means certainly it is a A-stable multivibrator. Yes. So one thing is sure, it is A-stable multivibrator. Now the thing is, usually we have seen that we calculate our output here. But if I am calculating my output here, will that make any changes? So let's check that out. So how will I check it? So let's just say initially I applied my input to be 0. Here I have applied my input to be 0. Then this would be 1. This would be 1 only. This would be 0. This would be 0 only. Okay, let's write down here. Because this is a buffer. This is not an inverter. This is a buffer. So this is 0. This will also be 0. This will be 1. This will be 0. This will become 1. This 0 will go here. this will become 1 here, this will become 0 here. Now initially it was 1 only, now from 1 to 0 it has become, now from 0 to 1 it will become, from 0 to 1 only it will become 1 to 0, 0 to 1, 1 to 0, now from 0 to 1, now again 0 to 1, 0 to 1, this will become 1 to 0, 1 to 0. So here you can see that output is changing from 0, 1, 0, 1, 0, 1. In that manner it is changing. But now let's start. This was there at 3 nanosecond, right? 3 nanosecond. This will be changing at first 0 you are getting. From 0 to 1 you are getting. Now this one you are getting at 5 nanosecond. Now this 0 you are getting at 8 nanosecond. This 0 you are getting at 12 nanosecond, right? 8 plus 12 nanosecond. Now 12 plus 3 plus 2, 5, 17, 17, 18, 18 plus 3, 21, 21. Here you are getting 21, 21 plus 3, 24, 24 plus 4, 28. So after 28 nanosecond, this is becoming 1. After 28 nanosecond. Right? Now let's move in the cycle. So this is the scene at 28 nanosecond. So 28 plus 2, 28 plus 3. 28 plus 3 is 31. 31 plus 2, 33. 33 plus 1, 34. 34 plus 3, 37. 37 plus 3, 40. 40 plus 4, 44. So this is the scene at 44 nanosecond. So now what you can see, 12 nanosecond, after 16 nanosecond, output are changing. After again 16 nanosecond, output is again changing. Are you getting this point? 12 nanosecond, then output is changing at 28 nanosecond, then again output is changing at 44 nanosecond. So what was the gap here? 16 nanosecond. What is the gap here? 16 nanosecond. So after every 16 nanosecond, output is changing. 1 to 0, 0 to 1, 1 to 0 in that manner. So it is a astable multivibrator and output is changing after every 16 nanosecond. So you don't need to do all these analysis. This is just to make sure that whenever you calculate the output, even if you are calculating the output here, still the answer would be same. The output will change after 16 nanosecond only. Even if you calculate the output here, output will change after 16 nanosecond only. Even if you calculate the output here as well, the output will change after 16 nanosecond only. So first thing I will verify that it is a astable multivibrator. Now in the loop or apart from the loop, like here in the loop or after the loop, I can calculate the output anywhere. It will change after the certain amount, and that amount you can calculate just by calculating the delay of the loop. What is the complete delay of the loop? That is delay of the loop, delay in loop. So this analysis you don't need to do in the examination. In the examination, first thing you need to verify whether it is a astable multivibrator. Yes. Now I can calculate the output anywhere. So what will be the frequency of oscillation? First I need to calculate the delay in the loop. 3 plus 4, 7. Basically 3 plus 4 plus 3 plus 2 plus 1 plus 3. 10, 16 nanosecond. Right? This is the complete delay. So after every 16 nanosecond, output is changing. Basically 0 to 1, then 1 to 0. This will be there. This one will be there for 16 nanosecond, and this 0 will be there for 16 nanosecond. Then in that manner it will go. So this is the, now if you are asking the frequency of oscillation, frequency of oscillations. So this is the time period. The time period is 32. Time period is 32. So answer would be 1 by 32. So what we are getting, I guess no option would be matching here. 1000 by, where is the calculator? 1000 by 32. Okay, yeah, 31.25. Answer would be 31.25 megahertz. So this I need to verify. Sorry, this I need to modify here. Here option would be 4. None of the above. Instead of that, I could have put 31.25 megahertz. So okay, this is the answer. Well and good. Let's move to the next one. Yeah, so let's see the solution of this one. This is also a very good question. So you need to make the function f using NAND gate, right? The minimum number of NAND gate required to implement the Boolean function f is alpha, and you need to implement the function g using NOR gate. So whenever we see NAND gate, our target would be to make SOP form. This we have already seen our concept, right? We will try to make the form to be AB plus CD. And whenever we see NOR gate, we will try to make it look like this, A plus B into C plus D. So NAND gate means SOP, NOR gate means POS. This we have already seen. These two examples also we have seen already in our class notes, but let's see it again. I told you these are very, very important. One of the example has been already asked in the gate examination, this one. Now this is probable, like next time if they frame the question from this topic, I really think that this example will be asked. Okay, so let's see this one, what they are saying for function f. X bar plus y bar, x bar plus y bar. Can I write it down in this manner, x y bar into w plus z, right? Can I call this as a? If I call this as a, what I am getting? AW plus AZ. And how many gates will be required for this one? AW plus AZ. How many NAND gates are required for AB plus CD? 3, right? This we already know, AB plus CD. A into B, C into D, and then NOR gate. Now what we need to do, we need to make NAND gate. So one inverter I will add here, so another inverter I will have to add here. One inverter I will add here, so another inverter I will have to add here. So this is NAND gate, this is also NAND gate, and this is also NAND gate. So 3 NAND gates are required to implement AB plus CD. So similarly here as well, you are requiring 3 NAND gates only, but 3 NAND gate for this one and 1 NAND gate for this one as well, XY bar, 1 NAND gate for this one as well. So how many total are required? 4 NAND gate. Okay, so value of alpha is 4. What about beta? So if we see the B function, so X, what is B? Oh, sorry, not B, sorry, G. G is X bar Y bar plus WZ. So can I write it down in this manner? X bar Y bar, right? So X plus Y whole bar, X plus Y whole bar plus WZ. Is there any error? No. Can I call this one as A? I am calling this one as, not A, I am calling this one as B. So B plus WZ. Can I write it down in this manner? B plus W into B plus Z. Say yes or no. What did I do? This, I thought that I can write it down in one term only. What I need here, what did I do? I needed it in one term only. Here there was two terms, X bar plus Y bar. I needed it in one term. So I made it one term, XY bar. Now I could see that it is AW plus AZ, and that I know I can implement in 3 NAND gate. Here my target is to make A plus B into A plus C, or A plus B into C plus D, A plus B into C plus D. How many NOR gates are required for this one? 3 NOR gate. I have made this expression. How many NOR gates are required for this one? 3 NOR gate, and 1 NOR gate for this guy as well. So total 4 NOR. How many nodes are required? 3 NOR are required. I hope you know it. How do you do it? B plus W, OR gate, B plus Z, OR gate, and then multiplication. Now I need to make it NOR. So another one inverter here, so another inverter here, one inverter here, so another inverter here. This is 1 NOR, 2 NOR, 3 NOR. So total 3 NOR are required. But here what is our B? Our B is already coming from a NOR gate, right? B is already coming from a NOR gate. So 1 NOR here, 3 NOR here. So total 4 NOR. So this is the value of beta. So alpha is 4, beta is 4. A very good question, and hopefully these kind of questions could be coming in our examination in future. But if you see, like from last 5 to 6 years, they are not framing these kind of questions in the examination. I don't know why, but certainly they are not framing in from last 4 to 5 years. Then it is probable in the upcoming examination. Okay. Yeah, let's see the question solution of this question. This is also a very good question. So these 4 gates are given. Which of them will work as a universal gate? This is what we are asking, and we are saying that we have separately available 0 and 1 as well. We have bits 0 and 1 separately available, and which of them will work as a universal gate? That means using which of the gate you can implement all possible Boolean expression. So what do I mean by that? That it should work as a universal gate only. So like if you haven't studied digital from PrepFusion, if you have studied from somewhere else, then I guess you might not be comfortable with this concept. So the concept is like what you have already studied. You would have already studied that if you are having NOT gate plus AND gate plus OR gate, if you are having these 3, then you can implement any possible Boolean expression. These 3 gates are known as basic gates. So if you are having basic gates with you, NOT gate, AND gate, and OR gate, if you are having these 3 gates, then you can implement any Boolean expression. This is correct. But there is one more condition. This is the one condition that this will help you implement any Boolean expression. There is no doubt about that. But if I am having a NOT gate plus I am having one of the gate of AND gate or OR gate, only one of the gate I am requiring. I am not saying I need both of the gates. Here you are saying that you need NOT gate as well, you need AND gate as well, and you need OR gate as well. But here I am saying that you are having NOT gate, you can either have AND gate or you can have OR gate. One of the gate you require, plus you are having 1 and 0. So these three are also enough to implement any Boolean expression. Are you getting this point? These three guys are also enough to implement any Boolean expression. Let's check that out. Here what is the output? The output is A bar plus B. So here I am having the property of OR gate as well, plus I am having the property of NOT gate as well. So can I implement all possible Boolean expression? So do you agree with me on this point that if I am having NOT gate, if I am having AND gate, and if I am having OR gate, all three together, if I am having all three together, then I can implement anything. Do you agree to this point? You might not be agreeing to this point, but you are agreeing to this point, right? Now let's check that out. Can I implement any Boolean expression using these? So what will be my target? My target would be to get the OR gate from here, to get the NOT gate from here, and to get the AND gate from here. From this particular expression, if I am able to get these three gates, then you will be agreeing that using these three gates you can implement any Boolean expression. Look, I am proving this point. What I am doing? I am proving this point. How I am proving this point? I am proving this point by these concepts that this is the expression I am having, A bar plus B. So if I am having A bar plus B, from A bar plus B, if I am able to make OR gate, NOT gate and AND gate, then you are agreeing to this point that using these three I can implement anything. So this is my target. My target is to get OR gate, NOT gate and AND gate from this expression A bar plus B. Can I get it? Yes. What I need to make? First I need to make NOT gate. So for making NOT gate, what I am gonna do? Put B equals to 0. If I put B equals to 0, what I am getting? A bar. What I need to make? Next I need to make is OR gate. What I need to make? OR gate. So how I can make OR gate from here? What I can do is that from this gate only I can make an inverter. From this gate only I can make an inverter because I can see here I am having the property of NOT gate. So what I am gonna do is that I am gonna make B as B bar, or let's not make B as B bar. What I can do is that, yeah, here this is my A bar, no? Here what I am getting? A bar. So what I am gonna do is that I am gonna make this A bar as A. What I mean to say, this is the gate I am having. Here I will put A and here I will put 0. So what I am getting? A bar, right? A bar plus 0 will be A bar only. So here I am getting A bar. Now what I am gonna do is that this is what I am gonna do. Now here I will put B. So what is A plus B? What I am getting? Y is equals to A plus B I am getting. So OR gate also I have implemented, right? OR gate is also done. Now what is the next target? I need to make a AND gate. So for AND gate, what I need to do? So for AND gate, what I will do is that first I will make B bar. Yeah. So in AND gate, what I will do? This is my B. Here I am putting 0. So what I am getting? B bar I am getting here, right? B bar I am getting here. Now this is what I am gonna do. Here I am gonna put A. So this is your A bar plus B bar. Here what you are getting? A bar plus B bar. And what is A bar plus B bar? A bar plus B bar is AB bar. This is your A. After that there is a bubble. So A bar plus B bar is AB bar. Now what I need to do? I need to remove this bar. So how will I remove this bar? This is how I will remove this bar. Here I will put 0. So AB bar and then bar. So AB plus 0. Here you are getting AB only. So what you are getting? AND gate. So using this gate only, what I have made? I have made AND gate, I have made OR gate, and I have made NOT gate. So these three gates I have already made. And now you are agreeing to this point. Which point you are agreeing? That if you have made AND gate, OR gate, and NOT gate, then certainly you can implement any Boolean expression. So you are agreeing to this point now. So from this concept only, we have made a conclusion that if you are having NAND gate or one of the gate of AND gate or OR gate, and you are having 1 0, because here we are using 0, here we are using 0, here we are using 0, somewhere we need to use 1 as well. So if you are having NOT gate, if you are having one of the gate of AND or, and if you are having 1 and 0, then certainly you can implement anything. So D1 is correct. Let's check that out. Let's check this one out. So what you are having here, A bar plus B bar, what that would be? AB bar. So here you can see the property of here you can see the property of NOT gate plus AND gate. So if you are having NOT plus AND and 1 0, then also this can also be helpful for you. What about this one? What is this? This is A bar plus B bar and then whole bar. So what that would be? AB bar bar. What that would be? AB. So here you can get the property of only AND gate. There is no NOT gate. Can you make NOT gate from this gate? Try doing it. You can never make it. What I am asking you is that if I give input A to this gate, I need the output to be A bar. Can you make NAND gate from this gate? No, you cannot make. And in the final expression as well, we can see that here I can see the property of only AND gate. So this is not correct. From using this gate, you cannot make all the universal gates. Are you getting this point? And what about this one? This is your A bar plus B bar. This is AB bar. So AB bar, this is already a NAND gate, and using NAND gate you can make all the gates. Or you can see from here as well that you are getting the property of AND plus NOT. You are getting the property of AND gate as well and NOT gate as well. So from this one as well you can make all the possible Boolean expression. So D1, D2 and D4. These are the answer. And this was the concept. I hope you enjoyed this concept. This is something that is not usually discussed, but here we have discussed it. Okay. Yeah, let's see the solution of this question. So which of the following identity is true? This is what you need to tell. So A plus BC, A plus B into A plus C, this is true. There is no identity like this. If you feel like that, A plus B, this is not like a multiplication, nothing like that. So there is no identity like this, right? And what about this one? AB plus BC plus C A bar. So what we used to do, this is we call as census law. So what do we see? A and A bar is there. So multiplication of B and C is available. Yes, it is available. So yeah. So this is redundant. So AB plus AC bar. How do we check it? The way is, what you need to see, A and A bar is there. So apart from A bar, what do you see? B and C. So multiplication of B and C is available. Yes, it is available. That means this term is redundant. So AB plus A bar C. So yeah, this is correct. What about the next one? The next one. Again, you need to check the same thing. A and A bar is there. That means multiplication of BC is available. Yes, it is available. Apart from this, there could be anything. Again, this complete term will be redundant only. Now, you might not be agreeing to me. So what we will do, we will prove it. How we will prove it? AB plus A bar C plus BCPF. So what we can do? We can multiply A plus A bar, because what is A plus A bar? A plus A bar is 1 only. So can we multiply it? Yes. So what we are getting? AB plus A bar C plus, can I get A BCPF plus, can I get A bar BCPF? Yes. So what you can see here, AB can come common from these two terms. AB can come common. So 1 plus CPF, and what you can see here, from here A bar C can come common. So plus A bar C can come common. 1 plus BPF. So what is 1 plus BPF? That is 1. 1 plus CPF, that is 1 only. So AB plus A bar C. So what is the answer? Fourth option, right? So this is the proof as well. So usually when we study census law, we only study about this, but this is also true. What you need to see, A and A bar. So multiplication of BC is available. Yes. Now in the multiplication, anything else can also be available. There is no doubt about that. This will be completely redundant. So AB plus A bar C. Okay. So option 1, 3, 4 are correct. Very simple. Yeah, so let's see this one. So with 4 variables, the number of different Boolean functions possible are alpha, self-dual function are beta, and maximum possible prime implicants are gamma. So value of alpha plus beta plus gamma you need to find. Here this should be gamma or gamma. Okay, so alpha plus beta plus gamma you need to find. So for n variable, what will be the value of alpha? Maximum possible Boolean expression. So even if you forget the formula, what is the way to remember it? Just take the example of one variable. If you are having one variable, then how many Boolean expression you can make? A bar, 0 and 1. 4 you can make. So the formula is 2 to the power n. Because if you put n equals to 1, then 2 to the power 2 answer is 4. So this is how I remember it. Even if I forget this formula, then I can take the example of one variable and then I will be able to solve it. So with one variable 4, so formula is 2 to the power n. What about beta? Number of self dual. So out of these, which are self dual? In self dual, this will become 1, this will become 0. Self dual of a bar is a bar only, self dual of a is a only. When we take the dual, what we do? Plus 2 dot dot to plus 1 to 0, 0 to 1. And there is a special note that never complement the variables. So a is not being complemented, a bar is also not being complemented, right? So these are not being complemented. So what do you see? This is same, this is same. So self dual are these two. Whenever you take the dual, you never complement, right? So these are self dual, these are not self dual. So how many of them are self dual? 2 are self dual. So what is the formula? 2 to the power n minus 1. This is the formula, because for one variable you are getting 2. So one might be thinking that sir, formula could be 2 to the power n as well. But if you have studied, at least if you have studied, then you would know that formula is not 2 to the power n. Like in your mind there would be this doubt that sir, formula is 2 to the power n minus 1, or it is 2 to the power 2n minus 1. What is the, like, at least you should have studied it. How do we prove it? We prove it using the example of 2. But if you take the example of 2 variable, then it would take a lot of time. So I am just telling a way to remember the formula. I am not telling this is how the formula is derived. No, I am telling a way to remember the formula, not the derivation of the formula. Are you getting this point? So this would be 2 to the power n minus 1. Usually we find the formula from here only, that total possible Boolean expression are 2 to the power n minus 1. Out of these, 2 to the power n minus 1 are self dual, and rest all are not self dual. So this is how we remove, this is how we derive it, or you can say this is how we write it down, right? And what about the maximum possible prime implicant? So maximum possible prime implicants are 2 to the power n only. So this you can remember by the example of this K map, that maximum possible prime implicants. So 1 0 1 0 1 0 1 0. So maximum possible prime implicants are 1 2 3 4. So 2 to the power n minus 1 it is. With 3 variables you can make 4 prime implicants with maximum possible prime implicants. Prime implicants or essential prime implicants? Here it should be essential prime implicants, sorry, right? Because maximum possible prime implicants could be anything. This should be essential prime implicants. Maximum possible essential prime implicants. Here it should be essential prime implicants. So I will modify this one as well. Maximum possible essential prime implicants would be 2 to the power n minus 1. Okay. So now this question will be solved. So what you are getting here, you can put the values, this value 2 to the power 3, and this value will be 2 to the power 3 as well, right? 8, 2 to the power 8, and 2 to the power 16. You can add them up and you will get this answer only. Okay, so just you need to add it up. Fine. Yeah, so let's solve this one. You need to find number of prime implicants and essential prime implicants. So for finding prime implicants, what is the method? The method is first find the biggest group. So what are the biggest group here? So this group I can see, that is of 4, right? This group of 4 I can see. Can I see any other group of 4? Yes. 1, 2, 3, and 4. Another group of 4 I can see. Now can I see another group of 4? No. Now I will make the groups of 2. Just I will make sure that when I am making a group of 2, there should be no smaller group inside the bigger group, right? Like if this is the bigger group, so inside the bigger group there could not be any smaller group. What I mean to say is that inside the group of 4 I cannot frame the group of 2, but one of the element I can take, like this element I can take, this group I can frame, but this group I cannot frame, this and this group I cannot frame, because that is, this group is completely inside the bigger group. So complete group cannot be there inside the bigger group. So this is the way of making it. So 2 prime implicants we have already seen. This is the third one, fourth one, fifth one. One of the element I can always take, but I cannot take 2 elements. So 1 2 3 4 5 6 and 7. I cannot make this group. Why I cannot make this group? Because this is already a part of a bigger group. So these are the 7 prime implicants. Which all are the essential ones? So for essential one, what I need to do? I will go to all the prime implicants. I will go to all the prime implicants. So first I will go to this guy. I am going to this guy. Now I will ask each element that if you are having any other group with you or not. So I will go to this guy. I will ask this one, are you having any other group? So this guy will say that no, I'm not having any other group. This guy is only there in this group only. So this is a prime implicant. This complete group is essential prime implicant. Now you need to go to this group and ask every single one that if you are associated with some other group or not. So I went to this one and I asked him whether you are associated with some other group. So no, this is only there in one group only. So this is the essential prime implicant. Now in the other group, I went to this one and I asked you, are you associated with some other group? It will say yes, I am associated with this group, I am associated with this group as well. I will go and ask this one. It will say that I am associated with this group and I am associated with this group. So this is also associated with two guys. This guy is also associated with two guys, this group and this group. But this guy is alone. This guy is associated with only one group. So this is also a essential prime implicant. Now I will go and ask this one. So this one is associated with this guy and this one is associated with this guy as well. So this is not essential prime implicant. What about this group now? Now I will go to this guy. This is also associated with two guys. This is also associated with two guys. This is also associated with two guys. This guy is also associated with two guys. And this guy is also associated with two groups. So all these are associated with two groups. So only two essential prime implicants are there. So 7 prime implicants. Out of these 7 prime implicants, only 2 essential prime implicants are there. So 7 and 2. So this is the way of analyzing. Or you can go and you check on YouTube. We have our marathon. So there I have explained this point in a much deeper manner and a lot of examples I have taken there as well. Okay. Yeah, so in a particular number system, one of the roots is given for a quadratic system. Only one root is given. Usually 2 roots are given, but only one root is given this time. You need to find the base of the number system. So what is given? Alpha plus beta, that is minus b by a, that is given as 11, but in some another number system. And alpha into beta, that is c by a, that is given as 22. Okay. Yeah. So one root is given, that is 3. So 3 in some other number system, but 3 it could be in any number system. It would be 3 only, no? If I write 3, 5 and I need to convert it into decimal, the base is 5. Now I need to convert it into decimal. So what will be the value? It would be 3 only, no? Because here I will write 3 into 5 to the power 0 and here I will write 3 into 10 to the power 0. It would also be 3. This would also be 3. So here I can only write 3 as well, or I can write 3 to the base r as well. Plus beta is equals to 11r, right? And here 3 to the base r into beta is equals to 22r. So let's solve first this one. So this would be 3 only plus beta. This would be 1 plus r. Say yes or no. So what is beta? Beta is coming out to be r minus 2. Beta is coming out to be r minus 2. So here what I can see, now use this equation. This I have used this equation. Now I will use this equation. So what I can see here is that 3 into beta is equals to 2 plus 2r. Do you agree to this point? 3 beta is equals to 2 into r to the power 0, that would be 2, plus 2 into r to the power 1, that is 2r. So 3 into r minus 2 is equals to 2 plus 2r. So 3r minus 6 is equals to 2r plus 2. So from here we are getting r is equals to 8. So that's it. Very easy question. So using only one root as well, these kind of questions can be solved. So this was my point of framing this particular question. That usually 2 roots are given. So there, even if you use one equation only, even if you use this equation only, still you would be able to solve. But even if only one root is given, then also you can solve it. So answer is 8. Fine. Yeah, so let's solve this question. You need to perform the following operation using 2's complement representation, and then you need to tell me where will the overflow occur. So this concept I have already told, but a lot of guys might not be comfortable with that. So let's start it again. So 2 minus 3. First I need to perform 2 minus 3. So how will I represent plus 2 in 2's complement form? Plus 2 in 2's complement form. So that would be written as 0, 1, 0, right? And how will I represent minus 3 in 2's complement form? So first I will represent in sign magnitude representation. So this is the sign magnitude representation of minus 3. This is the sign bit and this is your 3. Okay. And now if I need to represent in 2's complement representation, so what I will do is that 1 as it is 1 and 0. So this is how I will represent 1, 0, 1. So this is something that you should be comfortable with. Otherwise you will not be able to solve these kind of problems. Like I am not going to tell how to represent 2's complement form. So that you should be comfortable. Then only you will be able to understand this particular problem. So this is 1, this is 1, and this is 1. So now here you can see that there is no overflow. How will I see that? What was the carry in here? 0 only. And what was the carry out here? That is also 0. So 0 XOR 0 is 0 only. Right? Another thing I can see is that here there is 0, 1 and 1. So that is also a desirable condition. That means there is no overflow. Or you can say is that, like if it was the condition that 1, 1 was giving you 0 or 0, 0 was giving you 1, then there would be overflow. This is the condition of overflow. If a 1, 0 is giving you 0 or 1, 0 is giving you 1 or 0, 1 is giving you 0 or 0, 1 is giving you 1. So this is not the condition of overflow. The condition is C in XOR C out should give you 1. It is giving you 0, so not overflow, and 0, 1 is giving you 1, so another there is no overflow. So in the first example, there is no overflow. So this is the way, this is the first way, but every time you cannot check in this manner. Every time you cannot write down the 2's complement of 2, then you write down the 2's complement of -3, and then you see the final answer, then you write down the 2's complement again. Like what is the final answer? The final answer is 1, 1, 1, 1. So this is given in 2's complement representation. Right? If I need to take the sign magnitude representation, so what I need to do? Again, I need to take 2's complement representation. So if I take again 2's complement, then sign bit will be as it is, this one will be as it is, and this will be 0. So this is the sign magnitude representation of this. 1 is minus, 0, 1 is 1. So answer what you are getting? -1. 2 minus 3 is -1. Correct answer. There is no overflow. So answer is correct. But this is the method of solving it. But there is one conclusion that we got from here. What was the conclusion? The conclusion was, what is the minimum number of bits to represent 2 in 2's complement form? What I am saying, what is the minimum number of bits required to represent 2 in 2's complement form? 3, right? 3 bits are required to represent 2 in 2's complement form. 3 bits are required. Now, what is the minimum number of bits required to represent -3 in 2's complement form? 3 bits. Minimum number of bits I am asking. Now, what is the answer of 2 minus 3? That is -1. So, can I represent -1 in 3 bits? Can I represent -1 in 3 bits in 2's complement form? Yes, I can represent. That means there will be no overflow. Let's check another example. 4 plus 6. 4 plus 6. 4 plus 6. What is the answer? 10. What is the minimum number of bits required to represent 4 in 2's complement form? 4 bits are required, right? One bit will be of sign. And how will I represent 4? This is how I will represent 4. And what is the minimum number of bits required to represent 6? 4 bits are required. One will be of sign. And then 6. Right? And if I perform the operation 10, what is the minimum number of bits required to represent 10 in 2's complement form? What is the minimum number of bits required? So to represent 10 will be, how many bits will be required? So to represent 10, number of bits required is 5. Right? This is requiring 4 bits. This is also requiring 4 bits. But you cannot represent 10 in 4 bits. You need 5 bits. So certainly there will be overflow. Yes, this is the condition of overflow. Now you can check it as well. If you perform this operation, what you are getting? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0. What is the carry? 1. And what you are getting here? What is the carry out? 0. So C in, sorry, this is your C in. C in XOR C out. 1 XOR 0. What you are getting? 1. Yeah, this is the condition of overflow. And here what you see? 0, 0 is giving you 1. So this is also a condition of overflow. So certainly there is overflow is occurring. So this is one of the method you can check. Or you can think that 4 will require 4 bits. 6 will require 4 bits. So how much bits 10 will require? So 10 will require 5 bits. So certainly overflow will occur. What about 8 minus 11? 8 minus 11. So let's check for 8 minus 11. 8 minus 11. So how many bits 8 will require? 8 minus 11 is -3. So 8 will require 8. 1 0 0 0. 5 bits it will require, right? 5. How many bits -11 will require? -11 will also require 5 bits only, right? Yeah, -11 will also require 5 bits only. So can you represent -3 in 5 bits? Certainly I can represent. -3 I can represent in 3 bits only. -3 I can represent in 3 bits only, right? So there is no overflow. No overflow. So this is how we need to check. Otherwise, I can represent the numbers and then I can check it. But if there is big numbers are given, like -19 plus 26. So this was the option C. If I talk about option D, -19 plus 26. So here if I go on representing the numbers, then it would take a lot of time. So what I can think is that minus 19 plus 26 is 7. So I can directly see here, whatever the bits this will require, whatever the bits this will require lesser bits only. If this requires, let's just say 5 bits, I am not sure if it is require 5 bits or 6 bits, I am not sure about that. But you can see that 19 and 26, this will certainly require lesser bits only, no? Are you getting this point? 7 will certainly require lesser bits than 19 and 26. So certainly there will be no overflow. So rather than solving, rather than converting into 2's complement form, directly you can see here that this will require less than the bits that these guys will require. That's it. Here there could be some doubt that how many bits 1 will require. Here also there would be no doubt that 2 minus 3, whatever the bits 2 and 3 require, certainly 1 will require lesser bits only. So no worry about that. Now 4 plus 6, how many bits 4 will require? 4. How many bits 6 will require? 4 only. So this 10 is requiring more bits. So if you are getting more answer than that, then you need to check. Otherwise, if you are getting the lesser answer, 8 minus 11, 3 you are getting. Minus 20 plus 26, 7 you are getting. So they will require lesser bits only, no? So there will be no overflow. Only the condition is you need to check here. Right? Now don't make a conclusion out of it that, sir, if we are getting the larger answer, let's just say, if I do the calculation, 2 plus 1 is equals to 3. So sir, there will be overflow. No, there is no overflow in this case. 2 plus 1 is here. What conclusion people will make that, sir, 4 plus 6. So the final answer you are getting 10. So 10 is larger than 4, 10 is larger than 6. So certainly there will be overflow. Wrong conclusion. 2 plus 1 is equals to 3. Is there any overflow? No. Why there is no overflow? You can check. How will you represent 2? 2 will be represented in this manner. How will you represent 1? 1 will be represented in this manner. If you do the calculation, what you are getting? 3. Very easily you are getting. There is no overflow. Because this is represented in 3 bits. This is also represented in 3 bits. Although you can represent 1 in 2 bits only. But you need to check this 3 is represented in 3 bits. And this can be 1 can be represented in 2 bits as well. Like some guy will say that, sir, I will represent 1 like this. Okay, you can represent it. But to perform this operation, 2 plus 1, how many bits you require? 3 bits you require, no? Are you getting this point? If I ask you, I need to add 19 plus 2. I am asking you mathematics. So can you say that, sir, 19 plus 2 I will add in this manner. 19 plus 2. This is how I will add. So 9 plus 3. This is how you don't add, right? What you do is that you add another 0 here. Similarly, if I need to add 2 plus 1, then for 2 I require 3 bits. So for 1 as well, I will need 3 bits only, no? Although I can represent 1 in 2 bits only. But if I need to perform the operation, if I need to add it up, then I would require 3 bits. So 3 bits here, 3 bits here. So can I represent 3 in 3 bits? Yes, I can represent. So there is no overflow. So don't make any conclusion that if larger number we are getting, then there will be overflow. Otherwise, there will not be any overflow. So always check that how many bits this guy is requiring, how many bits this guy is requiring, and how many bits the final answer is requiring. So once you check it up, then you can tell the final answer. Are you getting this point? Okay. So a very good question and a very good concept as well. The same kind of question will be introduced again in the next test series only. You will see the same kind of question will be there. But there we will solve it using this concept, which is easier. This is a bit more intuitive. But if you solve it using this concept, then directly you can see C in XOR C out. Right? So that we will see in the next test series. Yeah, let's check this question. This question is based on hazards. So what you need to do, you need to tell static 1 hazard is there or static 0 hazard is there. So one thing we already know that for POS form, there will be hazard 0. And for SOP form, there could be hazard 1. So this second option, this first option is gone. This is wrong. That this is your POS form. So in POS form, hazard 1 can never occur. Hazard 0 can occur. So this can have hazard 0 and this can have hazard 1. But there would be condition that there would be no hazard as well. So how to check if there is an hazard or not? So how to check that? So the way to check that is that you need to make the k-maps. What I need to do? I need to make the k-maps. So x bar x, y bar z bar, y bar z, y z and y z bar. Although hazard is not, I guess in 90s there has been one question from hazards. So usually it is not asked in the examination, but this is something that is related to our basics only. So certainly it can be introduced in your examination. Yeah. So first let's see this x plus z. So this I will make for POS form. This I am making from for SOP, this I am making from POS. This would be y plus z, y plus z bar, y bar plus z bar, and y bar plus z. Okay, so let's check this one, x plus z. So x plus z, x plus z. Okay, need to denote by 0, and then y plus z bar, y plus z bar. So which all grouping they are making? They are making this group, and another group they are making is this one. Now you need to see if there is another group possible, right? There is another group possible. So this is the group possible. So that will result into hazard. Yes, that will result into hazard. So certainly there is static 0 hazard is there, right? Static 0 hazard is there. Static 0 is present. And now if they ask you what is the way of removing this hazard, so what you will say that sir, your function was, your g function was, not g, your f function was, f only, the f function was x plus z into y plus z bar. So this you have already taken. If you take this guy as well, if you take this group as well, then there will be no hazard. So in this group, what is constant? X is constant and y is constant. So if you implement this particular Boolean expression, then this will be hazard free. This is hazard free. So two kind of questions can be framed from hazards. First one is to whether to determine if there is hazard. The other one could be that how to remove this hazard. So this concept we have already studied, just it is a revision now. Okay. Now what about this one? Yz plus xz bar. Yz plus xz bar. Xz bar. Xz bar. Xz bar. So here also I can see that they have made these groups. They have made this group as well, and they have made this group as well. But here I can see that I can make another group, which is this one, right? So certainly there is a hazard. Now if they ask you how to make it hazard free, then what you will say? That sir, your g was yz plus xz square, xz bar. But if you add this group as well, what is this group? This is xy. So if you add xy group as well, then this will be hazard free. So this will be hazard free. So two kind of questions can be framed from hazards. So this is the only one question which you will see in the complete test series from the hazards. Only one question, and in one question the complete hazard has been revised, right? So answer would be this one. So this is how you need to solve it. Okay. Yeah, so let's see this question. In this question, what they are saying, you need to identify how the circuit is working. Okay, so in the options you can say they are talking about positive edge and negative edge. So that means you need to verify whether it is positively edge triggered or negatively edge triggered. So what do you mean by positively edge triggered? What do you mean by positive edge? Positive edge means you are going from 0 to 1, right? This is the meaning of positive edge, right? As positive edge, you are going from 0 to 1. So initially if I say my y was 0, if my y was 0, that means this would have been 1. If y was 0, that means from here x would have got out. If y was 0, then x would have got out. Then x would have been here. Now, here y is 1. Here y is 1. So at 1 what you are having? At 1 you are having q. Right? At 1 you are having q only, no? This q is being fed back. So at 1 you are having q. So what is your output? What is your q plus? When your y was 0, your q plus is becoming q only. Let me analyze it again. When y was 0, from here what would have got out? X would have got out. So x is here. This is your x. X is here. But this guy became 1. This guy became 1. If this guy became 1, that means this guy will get out. Now what is this guy? This guy is q only, no? Because feedback is there. So this guy is q only. So q plus is q. Next state is equals to q only if y is 0. Now if y is going from 0 to 1, that means now the y has become 1. Now the condition is y has become 1. Now if the y has become 1, then what will happen? Y has become 1. So what this will be? This will be 0. If y has become 1, that means what it will take now? It will take this guy. And now what is this guy? When initially y was 0, what I am talking about? I am talking about positive feedback. I am talking about, sorry, not positive feedback. I am talking about positively edge triggered. So when initially y was 0, this guy was x. Now you have changed y to 1. Now y has become 1. So what you will get here? This x would come back here, no? Are you getting this point? From 0 to 1 you are going. That means previous condition was that this point was x. Now this x is in feedback. So this x will be fed back to 1. this x will be fed back to I1. So now I1 should get out. What is I1? I1 is x only. So here I1 will come. And what is y here? Here this input is 0. So that means this x will get out now. So q will be equals to x. Q plus will be equals to x. Like, do you understand the meaning of previous state and next state? Here x is working as a previous state. In this example, x is working as a previous state because that is coming from the previous stage. This is coming from y equals to 0. When y was 0, at that time this point became x, and then this x is fed back. Now when I make y equals to 1, so at that time I will get x here. Now let's just say if I started all this circuit, assuming that I started all this circuit from 1 to 0. If I had started this circuit from 1 to 0, that means initially my y was 1. This is how I am starting it now. Initially my y is 1. So now you cannot predict that what will be the input here, because at that time you are not having x. But when I started my circuit from y equals to 0, so when I applied y equals to 0, then what happened is that x became here. Now that x is fed back. Now what did I do is that I changed my input y equals to 1. And when I changed my input y equals to 1, at that time what I could see is that when previously it was 0, then x was already here. Now when I changed my input y equals to 1, at that time I could see that at I1 I am having x. So this x will be again going here. And since this is 1, this is 0, so x will be fed out. So q plus will be x only. Next state will be x. And when y was 0, when initially y was 0, at that time this point was 1. At that time this point was 1. So what was this point? This point was x only. Sorry, this point was q only. When here the select line was 1. So this point was q. Right? Because of the feedback, because this is always at q. Let's just say this bit was 1. When this circuit started, this bit was 1. So this 1 would be coming here, no? And when you go to know that here, that this applied input is 1. So what will happen? This 1 would have already traveled here. Now this 1 will be going towards the output. So q plus will be 1, which is equals to q only. So this is the concept of previous state. Are you able to understand the concept of previous state here? Right? So that's the answer. This is a positively edge triggered flip-flop. That means it is, what do you see here? When your applied input, when your clock is 0, that means it is in hold state. And when positive edge is coming, when you are going from 0 to 1, that means it is giving the input to the output. That means q plus is equals to d. This is a property of flip-flop. So this is a property of a d flip-flop. So it is a positively edged d flip-flop, where x is working as an input, because here q plus is equals to x. So x is working as an input and y is the clock and q is the output. Okay, so it is a positively edged triggered flip-flop. A very good question where output is fed back towards the input. Now someone will ask me, sir, how to analyze from 1 to 0? That means if my initial y was 1 here, so initial y was 1, so this y was 1, then this y would have been 0. I should not say y, this input would have been 0. If I am going from 1 to 0, if here y was 1, then what you would look for? You would look for this guy. You would look for this guy. That means you need to know that when circuit started, what was the bit here? When circuit started, what was the bit available here? That you don't know. Are you understanding my point? If I apply y equals to 1 initially, that means I need to pick this I1. Now this I1 is coming from here. So when the circuit started, at that time, what was the bit available here? That you need to know. If I say the bit was 0, that means bit 0 will be transmitted. And from here, this 0 bit will get out. Basically, this 0 bit will be transmitted here. Now what this 0 will say? This 0 will say that I will pick this 0. So this 0 will be transmitted. So if you are analyzing from 1 to 0, that means you need to know what was the bit available here. Since you don't know that, that means you cannot analyze the circuit. From 1 to 0, we are not able to analyze that what is happening. Certainly, it is not working as a D flip-flop. This is not working as a negatively edged D flip-flop, because what is the property of negative edge? If it was a negative edged D flip-flop, then when you are going from 1 to 0, that means at 0 what it would have done? It would have taken the previous state. That means q plus would have been equals to q. But it is not equals to q. Q plus is equals to this bit. Here q plus is equals to question mark. Q plus is not equals to q here. Q plus is equals to question mark, and that question mark is what is the bit available here. Right? Are you understanding the depth of this question now? Okay, let's move on to the next one. let's see this one. Consider the following table. Which of the following options are correct? Here I forgot to write which of the following options are correct. Okay, so the state table corresponds to Millie machine. Yeah, surely it is corresponding to Millie machine. Why is that so? Because with respect to different inputs, you are having different outputs. Like here, your output is depending on the input as well. In case of a Moore machine, output doesn't depend on input. In case of Moore machine, you already write down the output, right? That if applied input is x equals to 0, then output will be 0 only. Are you getting this point? And you will be coming to this state. And when x equals to 1, then you will go to some different state. What will be the output? So basically here output doesn't depend on the applied input, right? But here you can see that if x was 0, then output is 0. If x is 1, then output is 1. So with respect to the x value as well, your output is depending. That's why it is a Millie machine. So no doubt about that. No doubt about that. Now how the states can be reduced? So I told you the states which are similar, those states can be reduced. So now I will look here that from A you are going to AB, from B you are going to CD. That means if from A, if applied input is 0, then you will come back to here. I should not write x equals to. If applied input is 0, then you will come back to A, and if applied input is 1, then you will go to B. What is the output? When applied input is 0, then output is 0. When applied input is 1, output is 1. So this is one of the state diagram. This is not the complete state diagram. This is one of the portion of state diagram I have made. So from B to you will go to C when applied input is 0. And when applied input is 1, you will go to D. When applied input is 1, you will go to D. In that manner, you can make the state diagram, right? So which of the states are similar? Let's check that out. So always look here: AB, CD, AD, EF, AF, GF, AF, AF, AF. Look, AF, AF. So basically the scene is, if you are at E and AF, AF, along with that you need to see these outputs as well. 1, 0, 1, 0. So the point is, if you are at state E and applied input is 0, then you will go to state A giving the output 1. And if you are at state E and applied input is 1, then you will go to state F giving the output 0. Right? Let's talk about G. So G is having the same condition. Applied input is 0, you will go here giving the output 1. Applied input is 0, you will go to F. Sorry, applied input is 1, you will go to F giving the output 0. So E and G are doing the similar operation. That means they are one of them can be reduced. Basically, what I can say is that I can replace G with E. So basically, I can replace this G with E. So what I will do is that, small cut. Now in the complete diagram, I can replace G with E. So here also I am having G, no? So this G can be replaced with E. Now what you can see is that EF, EF. So these two guys are similar, EG are similar, and DF is also similar. Why is that so? Because here also EF, here also EF. Here 1, 0, here also 1, 0. But can you say all four are similar? No, all four are not similar. Are you able to understand this point? I cannot say that E, G, F, D are equivalent. No. The state D and F are equivalent and state E and G are equivalent. This is what I will say. Here D is going in EF, F is going in EF, E is going in AF. If E was going in EF, let's just say if E was going in EF only, then I would have said that E, D, F, E, G all are similar. Are you understanding this point? Here there is a difference between D and E, no? You cannot say D and E are equivalent. So this statement is wrong. D and E are not equivalent to each other. D is going in EF, E is going in AF. So they are different state. But D and F are same because this is going in EF, and since G is equals to E, so this is also going in EF only. And what about E? What about E and G? So E is going in AF and G is also going in AF, giving the same outputs. So if someone looks from here only, then he would think that all four states are same. But no, you need to look at the both of the things. That the state that you are going in, along with that the output that you are giving, both has to be same. Then only you can say that states are same. So here EG are similar and DF are similar. So you can cut this one as well and you can replace F with D. So wherever you get F, you can replace that with D. D, D. All these can be replaced with D. Let's check if there are other redundant states as well, because I'm not sure. AD, AD. Yeah. Look. Now someone will think that, sir, C is going to AD and E is also going to AD. What someone will say that, sir, C is going to AD and E is also going to AD. But this guy is giving 0, 1 output and this guy is giving 1, 0 output. So that's why they are not similar. Although the transition is same, C will go to A but giving the output 0. E will go to A but the giving output 1. So that's why they are different. So both of the columns should be similar. So first what I usually do is that I look here, then I match here. So this is a good example. This is a very good example. I guess other similarities also we can find. CD, no. AB, no. So this similarity also we could have find that C and E are equivalent, but C and E are not equivalent to each other because the outputs are different. Okay, so what will be the number of states now? That this is different, 3, 4, 5. These two are same to previous one. So 5 states are there. So number of reduced states are 5. Basically D and F you can take both similar. So D is equivalent to F and E is equivalent to G. So instead of using F I will use D only. Instead of using G I will use E only. Well and good. So 5 states are reduced and D and F are equivalent. So this is the answer 1, 2, 4. Let's move on to the next one. Now that's a very good question. So and I want you to solve this question on your own. I know you would have tried it and you were not able to solve, I guess, but still I will give you an intuition or I will tell you one very good thing which will help you in any competitive examination you write. So you read this question, you have to read that Moore machine is there, 4 flip-flops is there, 2 input, 6 output, maximum number of transition arrow that are leaving and coming. So you know everything about it, right? You know everything about the question, but still you are not able to solve it. So if these kind of condition arrive, and here what do you see? Inputs are given 4, 2 and 6. So if any day if these kind of condition are arriving in front of you in the examination, then always take the smaller example. This is what I tell every time when I teach PNC. People get afraid of PNC question. What I always say that if you are not able to get the logic, always take the smaller example. Whenever you learn programming, whenever you learn DSA, whenever you learn simple coding language as well, I always say if you are not able to understand a problem statement, always take a smaller example. So here I will take a smaller example. What I will do is that a Moore machine with 2 flip-flop, 1 input and 1 output. Moore machine with 2 flip-flop, 1 input and 1 output. Determine the maximum number of transition. So if 2 flip-flops are there, then how many states I will be having? 4. 0, 0, 0, 1, 1, 0, 1, 1. 1 input is there. What they are saying? Determine the maximum number of transition arrow leaving. Transition arrow leaving. That means if you are at state 0, 0, I am calling this state as S0. So if you are at state S0, then applied input is X. Then you can leave from here. Applied input is X, that is 1 only. So if applied input is 0, 1 input means either it could be 0 or it could be 1. So if applied input is 0, then you can leave it. If applied input is 1, then also you can leave it. Now some people will say that, sir, I can come back as well. No. That if applied input is 1, then I can come back to S0 only. Yes, you can do that. But certainly that is leaving as well. No. That you are leaving this state. If applied input is 0, then you are leaving this state. Now let's just say I am at 1, 1. So if applied input is 0, then I can leave the state. If applied input is 1, then I can leave the state. So that means there are only 2 chances of leaving the state. But if the inputs were 2, I am saying if my inputs were 2. So with respect to 2 input, how many combination I can have? 0, 0, 0, 1, 1, 1, 1, 0. So if my applied input was 0, 0, then I can leave the state. 1, 0, then I can leave the state. 1, 1, then I can leave the state. And 0, 1, then I can leave the state. Basically, 4 kind of inputs can be there. If 2 input are there, then total 4 kind of combination can be applied to the state. If I am standing at state S0, then I can receive 0, 0 from the input side. I can receive 1, 0 from the input side. I can receive 0, 1 from the input side. And I can receive 1, 1 from the input side. And in 4 manner, I can leave the states. So now just let me know one thing. does it depend on the number of flip-flops? Does it depend on the number of output, that how many outgoing arrows you will have? No, it only depends on the number of input. If number of inputs were 3, that means you could have combination 0 0 0 0 0 1. In that manner you could have 8 combination. So you could have left the state in 8 manner: 0 0 0 0 0 1 0 1 0 0 1 1. In this manner, in this way you could have left the state in 8 manner. So now you are having 2 input, so I will leave the state in 4 manner. So now I am left with these 2 options. So first one, number of transition arrow leaving would be 4. Maximum number of transition arrow leaving the state would be 4. Now next, what they are asking, the number of transition arrow entering the state. So let's talk about this entering the state. So again I will take the smaller example. Which example I will take? You are having 2 flop, 1 input and 1 output. So I am having 4 state: S0, S1, S2 and S3. So what they are asking, number of transition entering the state. So from what I am thinking is that how much arrow I will receive entering into S0. This is what I am saying. Okay, what I am thinking now, how much arrows I will see entering into S0. So what S3 can do, that if my applied input is 0, then I will go to S0, giving the output anything. Output could be 1 or 0, anything. Let's just say output is 1. If my applied input is 1, then also I will go to S0, giving the output 0 or 1, whatever it is. What S2 can say, that if my applied input is 0, still I will go to S0. And S2 can say that if my applied input is 1, still I will go to S0. This can give output 1 as well. This can also give output 1 as well. What S1 will say, that if my applied input is 0, then still I will go to S0, giving the output 1. If my applied input is 1, then also I will go to S0 only. What S0 will say, that if my applied input is 0, then also I will come back to S0 only, giving the output anything. Output I don't care about that. What do we mean by that is that this is just to confuse you. 6 output doesn't matter. No, whatever the output you can receive, that doesn't matter, right? So this 6 output is just to confuse you, because with respect to 1 input you can have 1 output only. No, like if I apply x equals to 0, so can I say that my output will be 0 as well, my output will be 1 as well? With respect to 1 input you can have only 1 output. No, so that doesn't matter, only the number of inputs matter, right? Yeah, so what I was saying, that if my applied input is 0, then also I will come back to S0, and if my applied input is 1, then also I will come back to S0 only, giving the output anything, that I don't care. Okay, so in S0 how many arrows are entering? 1 arrow, 2 arrow, 3 arrow, 4 arrow, 5 arrow, 6 arrow, 7 arrow, 8 arrow. So 8 arrows are entering from 4 states. So all 4 states are contributing in the arrows entering into S0. The same thing could have happened with S3 as well. The same thing could have happened with S2 as well. And the same thing could have happened with S1 as well. Is this a valid diagram? Yes, this is a valid diagram. So all 4 states are contributing in the arrows entering. So all 4 states are contributing. That means if 2 flip-flops were there, that means there were 4 states. If 4 flip-flops are there, then how many total states will be there? 16. So total state will be 16. Now here from each state 2 arrows we could see. Here from each state there were total 4 states, and from each state we could see 2 arrow. 1 arrow, 2 arrow, 1 arrow, 2 arrow, 1 arrow, 2 arrow, 1 arrow, 2 arrow. Why is that so? Because the number of inputs, input combination were 2. Basically the input was only 1, x. The input was only 1, but the combination were 2. But now the inputs are 2. Inputs are 2 here. X, Z, 2 inputs are there. That means there are number of combination 4. So from one state we can see 4 arrows now. Basically there will be total 16 states, like this. There will be total 16 states, and from one state there will be 4 arrow. 1, 2, 3, 4. From same goes for this one. 1, 2, 3, 4. So from each state there will be 4 arrows. From each state there will be 4 arrows, and total states are 16. So 16 into 4, total 64. So 64 arrows could be entering into one of the state. Are you getting this point or not? 64 arrows could be entering, and how many arrows could be leaving? So leaving arrow can be decided by the number of inputs only. Here how many arrows were leaving? 4. Here also 4. Here also 4. Why here? Why 2? Why 2 arrows were leaving? Because the input combination were 2 only, either 0 or 1. So 2 arrows would be leaving, but entering would be more, because from each state you would get 2 arrows. So the total number of states are 4. So 4 into 2, here the answer was 8. But here total states are 16, and from each state you can get 4 arrows. So 16 into 4, 64. So these kind of question I can expect in future from FSM. Okay. So this is the correct answer. Well and good. I hope you would have understood the concept. And a very important point that I wanted to deliver here was that whenever you feel like that you are stuck, no matter whether it is aptitude, no matter whether it is examination of EC or it is any examination, it could be SSC, CGL, it could be anything. Whenever you are stuck in the language, always take a smaller example. Okay. Yeah. So that's it. Let's move to the next one. Yeah. So let's solve this question. This is a very straightforward problem. So you can either solve it using the options as well. You can solve it using the options as well. Look, options are very easy. X, Y bar, X bar, Y. So these are very straightforward. So you can solve it using options as well, or otherwise you can solve by the conventional one. So let's solve it using conventional method. So what is the conventional method? What you need to do? You need to make XY flip-flop using JK flip-flop. So you need to go from JK to XY. You need to go from JK to XY. JK flip-flop to XY flip-flop, right? So for how do we write which one we will make for excitation table, and for which one we will make a characteristics table? So how do we write that? So what did I tell you? You need to go from JK to XY. And who is your teacher? Me. And I am from EC branch. You can think of electrical as well. I am from E branch. So that means first you will write down excitation table, and for this one you will write down characteristics table, right? So from where to where you need to go? From where to where you need to go? So JK to XY I need to go. So JK excitation and XY characteristics table. Okay. So do you know the excitation table of JK? Yes. Zero 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 one one zero 1 0 1, don't care, don't care, don't care, don't care, 1 0. This is the excitation. Characteristics table is already given here. Characteristics table is already shown here, but this is not the characteristics table actually. Characteristics table is written in a longer format: x, y, qn, and then qn plus 1, right? Okay, here really sorry, this was the mistake. This would be qn plus, and this would be jk. Really sorry, just in a hurry I wrote down opposite. So qn plus, this would be jk 0 0 0 1. Now for xy, what you are writing? You are writing down the characteristics table. So all the input combination you will write. Although this is something that you should not be doing in the examination, because like here the options are very straightforward. You can solve it using the options as well. So but here I need to tell you the conventional method, because this is the only question which we are going to solve from this particular topic. This is known as flip-flop conversion. So this is a very straightforward topic. So in the whole test series there is only one question, which is this one only. Okay. So that's why I am telling you the method as well, so that you can revise it, because people would have forgot the method. So now from here you can revise the method, and then later on you can solve by your intuition as well. Which intuition I am talking about? I am talking about the intuitions of options. Okay. So what will be your qn plus 1? When applied input is 0 0, qn plus 1 is blindly 1. When applied input is 0 1, then qn plus 1 is equal to qn only. So what is qn here? 0 1. When applied input is 1 0, then it is equal to qn bar. Applied input is 1 0, then it is equal to qn bar. And when applied input is 1 1, then it is equal to 0 only. 0 only. So now you need to determine jk. So when qn plus 1 is 0 1, then it would be 1 don't care. So better I should copy this one. Yeah. So for 0 1 you get 1 don't care. For 1 1 you get don't care 0. For 0 0 you get 0 don't care. For 1 1 you get don't care 0. For 0 1 you get 1 don't care. For 1 0 you get don't care 1. For 0 0 you get, here why it was 1 care, don't care 1. For 0 0 you get 0 don't care. For 1 0 you get don't care 1. Okay, so what is your j and what is your k? So here I can directly see that if this don't care is 0 and if this don't care is 0 and this don't care is 1 and this don't care is 1, so that means 4 times 0, 4 times 1, that means this is equals to x only, k is equals to x. What about j? J, if this don't care is 0, now what about j? So in the options if I check, what is my k? K is becoming x, k is becoming x, so j has to be y bar, j has to be y bar. Yeah, so this don't care is 1, this don't care is 0, this don't care is 1 and this don't care is 0. So y 0 0 y, sorry, 1 1 0 0 1 1 0 0, so this is equals to y bar only. Otherwise what you would have done is that you need to make xy to jk, right? Xy to jk you need to make. So you just verify these options, that you make the characteristics table of jk flip flop and then you match with xy. Are you getting this point what I am saying? Here I will write down, instead of xy I will write down jk. So jk can have 0 0 0 1 1 0 1 1. Now you need to think, if jk is 0 0 then it should be hold state, but that means j is not equals to x and k is not equals to y. If jk was 0 0 then it should have been hold state, no, but it is not being held here, it is being set, it is being set here. So what will be my first intuition? My first intuition would be that it might happen that x is equals to x bar is equals to j. It might happen, this is what I will be thinking, because if this is j bar, if this is j bar, that means here j would have been 1, right? If x is 0, that means j would have been 1, 1 0 would make it set. But then I will go to the next option, if this is 0 then this would have been 1, so 1 1 would make it toggle, 1 1 would make it toggle, but it is being held, that means it is at hold state, so certainly j is not equals to x bar, so this will be gone from my side. Then I can check other option, that what if j is equals to y bar? So j equals to y bar, if j is equals to y bar, that means my j here would have been 1, this would have been 0, this would have been 1, this would have been 0. Now if k is equals to x, that means if this is k, that means this will be set only, it is being set. If this is k, 0 0 hold, if this is k, that means it should be toggling, and if this is k, then it should be reset. Yes, it is reset. So if you have good amount of aptitude, that what is the role of jk, that at 0 0 holds, at 0 1 reset, at 1 0 set, and at 1 1 toggle. So in that manner you can compare. Okay, so when I saw this question for the first time, I solved by the options only, not by this conventional way. Otherwise you can solve by conventional way as well. So this is the answer. Okay, let's move on to the next one. This was a very straightforward. Yeah, so what they are saying, this function of following state diagram is similar to what? Okay, so now like this is the output, q is known as output only, and input we are applying as x. So this is your q and this is input x. So what this state diagram is saying, that if your current state is 0 and applied input is x, then you will come back to this state only. That means if I apply input as x and your current state is 0, this current state is 0, and if I apply the input x equals to 0, then your output will be 0 only. But what is happening here? 0 1 0 1, so output is changing. What will be the state diagram of this one? That you are currently in 0 state, but if the applied input is 0, then I am going to state 1. This I am making for option A. This diagram I am making for option A. Now let's just say if I was at a current state 1, and now my applied input is 0. So where I will go? 0 1 0 1. That means if my applied input is 0, then I will come back to this state. Are you understanding this point? My current state is 1. Now if my applied input is 0, then I will come back to 1 only. Now if my applied input is 1, my current state is 1 only. But if my applied input is 1, then 1 0 1 0, then I will go to 0. If applied input is 1, then I will go to 0. Now if my current state is 0, and applied input is 1, then where I will go? 1 0 1 0. Applied input is 1, then I will go to 0 only. So this is the state diagram of first option. Similar diagram you will have for this one as well. What about this one? This is your x. X nor x. What that would be? 1 only. So here always your output will be 1. Always your output will be 1. You cannot even go to x equals to 0 state. Let's just say initially I was at x equals to 0 state. So no matter whatever the input you apply, it will always go to x equals to 1 state only. It will always go to x equals to 1 state only. Even if the applied input is 0 or applied input is 1. And if I was already at state 1, then always it will be at x equals to 1 state. No matter whatever the input is. So this is the state diagram for this one. Since this is also a single inverter only. This is NAND gate using inverter. So this is a single inverter. What is this? This is also a single inverter only. This is a single inverter only because there are odd number of inverters. So this acts as a single inverter. So this is also inverter, this is also inverter. So they are having the same characteristics. That means option A and C are having the same. What about option B? So option B is having this one. So you can check on your own. This I am leaving up to you. Or I should tell it. I will tell only. So if my current state is 0, applied input is 0, then what will happen? This is acting as a buffer. Even number of inverters are there, no? So that is acting as a buffer. So if your current state is 0 and applied input is 0, then you will come back to 0 only. Right? You can see here, come back to 0 only. Current state is 0, but applied input is 1. Applied input is 1. Then you will go to 1. Yes, you can see. Current state is 0, applied input is 1, I am going to 1. Because if here I apply 1, the next state would be 1 only, no? Now, if my current state is 1, and applied input is 0, current state is 1, applied input is 0, then what will happen? This 0 will be, since this is a buffer, so 1 will be going towards 0. So this 1 will be going towards 0 with applied input is 0. And if you are currently, your state is 1 and your applied input is 1, then you will come back to 1 only. So this is the answer, which is option B. So this is the state diagram given for option B. For A, C and D, I have made all these state diagram. Okay, this was the state diagram for D as well. Let's go to the next one. Yeah, let's see this question. So this is a question based on ADC. So they have given the range of output that your range of output will be from 0 to 13 volt. Okay, and the smallest change that you can see is that is 0.2 volt. 0.2 volt is the smallest change. So you can see that this is the resolution and this is the VREF value. 13 volt will be the VREF value because that is the maximum you can go, and resolution is given. They are asking the number of bits now. So forget about applying the formula. Did you understand the concept? That your output is going from 0 to 13 volt. 0 volt to 13 volt. And in between you are having ranges of 0.2 volt. That means at 0 volt you can detect something. At 0.2 volt you can detect something. At 0.4 volt you can detect something. 0.6 volt you can detect something. Are you understanding this point? Right? So how many bits you would be requiring for that? Like for 0 volt, you are representing 0 as 0, 0, 0. For 0.2, you will represent 0, 0, 1. For 0.4, you will represent as 0, 0, 1, 0. In that manner, you can represent. So how many bits you would be requiring? So what I will do is that I will divide 13 by 0.2. Say yes or no. That means I am getting 65. So I need at least 65 bits. Sorry, I need at least 65 combinations. That means I will represent 0 by some bits. I will represent 0.2 by some bit. I will represent 0.4 by some bit. I will represent 0.6. And in that manner, I will keep on going and I will reach till 13 volt. I am not giving you the formula here. Formula you would have already studied. You can apply it. But I am giving you the concept that this is how I am going to represent. Now, I can represent 0 as 0, 0, 0, 0 something. Now, I need 65 combination like this. I need 65 combination. So, using 1 bit, you can generate 2 combination. Using 2 bit, you can generate 4 combination. Using 3 bit, you can generate 8. Using 4 bit, you can generate 16 combination. Using 5 bit, you can generate 2 to the power 5, that is 32. Using 6 bits, you can generate 64 combination. And using 7 bit, you can generate 128 combination. So, 6 bits you cannot use. Because if you use 6 bits, you will only have 64 combination. But how many combination I require? I require 65 combination. That means I need to use 7 bits. So from here, what did I get to know from all these analysis? Like otherwise, people would have applied the formula. Like what is the formula? The formula is VREF by R is equals to 2 to the power n minus 1. I could have taught in this manner as well. What is VREF? 13 divided by 0.2 plus 1 also you can do. Here you will get 2 to the power n equals to 66 you will get here. So again here also you will require 7 bits only. And from here as well you will require 7 bits only. So how many bits you require? 7 bits. Okay. So you are requiring 7 bits. Now what they are asking? if you are using flash type ADC, so how many comparators you need to use? So in flash type ADC, if you remember, we have studied 3-bit flash type of ADC. There we used 7 comparator. Like this is how I remember it. I remember the example of 3-bit flash type ADC. I remember the example of 2-bit flash type ADC as well. Try visualizing the diagram in your brain. That 2-bit flash type ADC, we were using priority encoder there, and there were 3 comparators. So that means for n bit, we need to use 2 to the power n minus 1 comparator. So here how many comparators will be required? 2 to the power 7 minus 1. What is 2 to the power 7? 128. So 128 minus 1, that would be 127 comparators. A very easy question. So just I wanted to give all the concept here, nothing else. Okay, let's go to the, let's solve this question. These kind of questions are pretty good. Okay, so SAR type ADC is given, reference voltage is 1 volt. Reference voltage Vref is given as 1 volt. So in SAR type ADC, certainly you would be requiring the resolution. So here I am calculating the resolution. So that would be 1 volt divided by 2 to the power 5 minus 1. So roughly around 1 by 32 you can say, or roughly around 1 by 31 you can say. Okay, 1 by 32 also you can write down. After 3 clock cycles, what will be the content of SAR if your analog input is 0.67? So this is what we are measuring. Basically, we need to convert this guy into digital output. This is a ADC. So analog to digital conversion. So after 3 clock cycles, what you will get? Here, so let's start. So we will begin from 0, 0, 0 only. After first clock cycle, what will be the scene? So after first clock cycle, I know what is the decimal equivalent of this, 0. So this 0 will be going to the comparator. Basically, do you remember the diagram? There is one comparator, there is SAR block. The output of SAR block is going to a DAC. Then DAC converts it and then it gives to the comparator. So this is the simple diagram of all kind of ADC. Be it counter type. In counter type, there is a counter here. In SAR type, you use SAR device here. Right? So what will happen? Initially 0, 0, 0 is there. Resolution of DAC is 1 by 31. 1 by 31, what is the decimal equivalent of 0, 0, 0? That is 0 only. So 0 into 1 by 31, that would be 0 only. And at one end of a comparator, what is written? 0.67. At positive end, you are having 0.67. At negative end, you are having 0. That means what you will get? You will get plus 1 as output. If you are getting plus 1 as output, that means SAR will work now. SAR will work. What does that mean? That it will tell that bit into action to be 1. From where you will start from here. This is the bit into action. So 1, 0, 0. So let me make it a bit upward. So all these we have seen in the concept only. We are just revising it now. So this will be the bit into action. This will be always 1. Now this first step is universal. This will always work. After first clock cycle, always this will be the condition. So while solving the problem, you don't need to think about first clock cycle, but for second clock cycle, you need to think now. So what will be the scene after second clock cycle? So what is the decimal equivalent of this number? That is 1, 2, 4, 8, 1, 2, 4, 8 and 16. So decimal equivalent of this is 16. Again, let me check. 1, 2, 4, 8, 16. Yeah. So decimal equivalent is 16. Now this 16 will be going to the DAC. It will multiply it with the 1 by 31. It will multiply it with the resolution. So what will be the analog output you will be getting? It would be roughly around 0.5, you can say. Roughly around 0.5. So here you will be getting roughly around 0.5. Again 0.67 is greater than 0.5. So again you will be getting one output. That means what it will say? Now the next bit will be into action and it will tell it to be 1. Since the output was 1 here. Here also the output was 1. Here also the output was 1. Or you can say the input of SAR was 1. Now let's check what will be the input of SAR. So what will be the input of SAR? Let's check now. So what we are going to do, this 11000 will be going to the DAC. What DAC will do? First it will convert into its decimal equivalent. What will be the decimal equivalent of this guy? That will be 16 plus 8. That would be 24. So 24 into, now it will multiply it with the resolution. So that would be certainly greater than 0.67. No? You can see 24 by 32. 24 by, let's take 24 by 32. So that would be right, 3 by 4, am I right? Yeah. So 0.75. So roughly around it would be greater than 0.67 only. So now the SAR is receiving 0 input. So what it will say? The bit into action will be 1. The bit into action will be 1, but the previous bit will be 0. So previous bit will be 0 and this bit will remain as it is. So now with each clock cycle, every bit will come into action. This is the first one. then this bit will come into action, then this bit will come into action. So at the first cycle this bit came into action, then this bit came into action, then this bit came into action. So always the bit into action will be 1, right? If your applied input at SAR is 1, then you don't do anything else. But if the applied input at SAR is 0, if the applied input at SAR is 0, then you will make the bit into action 1, but the previous bit as 0. So previous bit as 0. So in that manner we need to receive. So after third clock cycle we are receiving this one, 1 0 1 0 0, 1 0 1 0 0. So this is the correct answer. And you can check at fourth cycle as well, you can check after fifth cycle as well. In that manner you can proceed, right? So these kind of questions we have seen in our lecture series in a very good manner. Let's go to the next. Yeah, let's see this one. This is a good question. 10-bit counter type ADC is there, having a clock frequency of 1 megahertz. Then the conversion time for the input 224.8 volt would be. Okay, so the input is 224.8. Resolution is given. So do we have any formula for conversion time? The formula for conversion time, usually we apply 2 to the power n minus 1 into t clock. But this is the maximum conversion time, right? This is the maximum conversion time. This is not the conversion time for a particular input. If they are asking for a particular input, then you need to analyze the circuit. And do you remember the circuit of counter type ADC? In all the ADC, like all the ADC have a general circuit that there would be one comparator. In counter type and SAR, there would be one comparator. At the positive node, what will be applied? 224.8. And here, the output would be coming from VDAC. This output will be coming from the VDAC. Now this 1 or 0 will be fed to the counter. Now the output of the counter will be fed to the DAC. And this DAC will be feeding this VDAC here. So this is a general way, right? Then there are control units as well that they will stop, and those are not important for us. For analysis, this is the only diagram that is important, and I told you this should be there in your brain. Same goes for SAR as well. Here there will be SAR device or SAR logic, you can say. So in SAR type of ADC, here there will be SAR logic, right? So now what we need to do? So initial state of counter is not given, but certainly it will be 0 0 0 only. There are how many bits? 10 bits are there. So certainly the initial state would be 1 2 3 4 5 6 7 8 9 10. This will be 0 0 0 only. Now this 0 0 0 will go here. What is the resolution of the DAC? That is 0.5. Resolution of ADC means the DAC that you are using, that is having the resolution of 0.5. So this DAC is having a resolution of 0.5. So this will convert, what is the decimal equivalent of this guy? That is 0 only. So 0 into 0.5, this will give 0 volt output only. Here 224.8 will be compared with 0. What we will get? 1. 1 means counter will count again. So now counter will count, and in that manner it will count. It will generate 0 0 0 0 0 1. Then this 0 0 0 0 1 will be going to the DAC, and how much analog output it will generate? 1 into decimal equivalent is 1 into resolution. So it will generate 0.5 volt of output. So that will be the 0.5 volt of output, which is lesser than 224.8. That means here also you will get again 1. Again counter is asked to count. In that manner it will keep on counting. So you received this guy after t clock time. Then after 2 t clock, after 2 t clock, what will happen? The counter will generate 0 0 0 0 1 0. That means decimal equivalent is 2. It will go to the DAC, 2 into 0.5. What it will receive? 1 volt it will be received. Again it will count. It will keep on counting. Till what point it will count? It will count until you get 225 volt here. Say yes or no. If you get 225 volt here, then this will be 0. And if it is 0, that means counter will stop counting. So after 2 clock cycle, you are getting 1 volt. After 4 clock cycle, you will get 2 volt, right? The output of DAC is 1 volt after 2 clock cycle. After 4 clock cycle, the output of DAC will be 2 volt. After 6 clock cycle, output of DAC will be 3 volt. You can understand, right? Because the resolution is 0.5 volt. So after 6 clock cycle, your output will be 3 volt. That means if you need output 225 volt, that means how many clock cycles it will be required? 450 clock cycle will be required. 450 clock cycle. 450 clock cycle will be required, right? Because 225, double of 225 will be 450 clock cycles will be required. And now you require 450 clock cycle. So that means after time 450 t clock, this bit will be 0 and counter will stop counting, and just as the counter stops counting, whatever the bit that you are receiving, that is your final output. So whatever the bit you will receive, that I don't care. I don't care about the bit that I am gonna receive here, but that will be my final output. right? So how much time I will require? 450 into t clock. What is t clock here? Since f clock is given, what is f clock here? 1 megahertz. So what is my t clock? 1 microsecond. So my conversion time is 450 microsecond. If you had blindly said that the conversion time would be 2 to the power 10 minus 1, that would into t clock, so it would be 1200 microseconds. So that is absolutely wrong. That is just blind answer, right? Why that is a blind answer? Because that is the maximum conversion time. That is the conversion time for 1. For this guy, that is the conversion time. But they are asking for a particular input. The input is 224.8, right? Okay then, well and good. Yeah, so the answer is 450 microsecond. This is the answer. This was a good question. Let's move to the next. So this is an easy question only. The resolution is given. They are asking the analog for analog input of 2.15 volt. They are asking the digital output. So you can either analyze it, or for this one I have told you a formula. If they ask you the digital output of a DAC, so what is the formula? What is the formula that I have told? If you remember it, then you can apply the formula. Otherwise, you can analyze it as well. Analysis also I have told, and formula also I have told. So the formula was analog input divided by resolution. So this formula you need to apply in all kind of ADCs. But remember one thing, in case of counter type ADC, what we are going to do? We are going to take least integer function. There are counter type ADC, there is SAR type ADC, right? In counter type ADC, what you are going to do? This is counter, this is SAR, and then there is dual slope. So this is having C, this is having D, and this is having S. As for super, if you are already super, then you can go down. If you need to go down, that means you can take greatest integer function. If you are getting grade C, that means you can get grade A as well, you can get grade B as well. So there is high chance of going up. That means you need to take least integer function. And if you are getting grade D, then also you need to take least integer function. But here you will take greatest integer function. What do I mean by that is that, what is the analog input? 2.15 volt. What is the resolution? 0.6. So if you perform this operation, what you are getting? 2.15 divided by 0.6. 2.15 divided by 0.6. So what I am getting? 3.58. 3.58. What kind of ADC is it? Counter type C. Counter type C. So I will perform this operation first. I am getting 3.58. So what I will think now? Okay, counter type C. C is there. That means I can get better grades. I can go up. So from 3.58, I need to go up. That means I will go to 4. If it was SAR type ADC, so from 3 to down I will go. That means I would have gone to 3. If it was SAR type ADC. But if it is counter type ADC, or if it is dual slope type ADC, I will go down, because I will go up from 3 to 4 for counter type ADC and for dual slope ADC. But I am already super, then I will go down. So my answer would be 4. What is the answer? 100. So this is just a way to remember in the examination. If number of bits are more, then you would be able to solve it quickly with the formula. Otherwise, you can do by the analysis as well. What is the analysis? Analysis is, this I have already taught in the previous questions as well. You can do the analysis, right? The analysis I am leaving up to you, because in the theory as well, I have taught this analysis like 4 to 5 times. So very easy, very easy analysis. 0.6 is the resolution. So we will start from 0, 0, 0. Then next will be 0, 0, 1. So what will be the decimal equivalent? That would be 0.6 only. 0.6 volt will be applied to the comparator. 0.6 is lesser than 2.15 volt. Then again it will count up. Now what will be applied? 1.2 will be applied. Then again it is less than 2.5 volt. Then again it will count up. Next count will be 0, 1, 1. What is this? Now 1.8 will be applied. Now 1.8 will be applied. So again it is lesser than 2.15 volt. So again it will count up. It will go to 100. Now what will be applied? 6 into 4, that is 2.4 volt. 2.4 volt. Now this 2.4 volt is greater than 2.15 volt. That means now the input will be zeros. No next count will be there. So this will be the final count, 100. So this is how you could have analyzed it, or you could have analyzed it using the formula as well. So formula is also very easy. This is not tough. So I have told you the trick as well. C, D and S. C, D is there. That means you need to go to the next count. And if S is there, you are already super, then you will go down. That means you will go to 3. Okay, let's go to the next one. Let's see this one, very easy. Error they are asking. So in error, there are 2 kind of error are there. One is the offset error, which is given already, plus minus 1 millivolt. Other one is there is error in accuracy, that is 0.1% of the full scale value. 0.1% of full scale value. What is the full scale value? 2.5 volt. 0.1% of full scale value, that means it will be 1 millivolt is already there. Now 0.1% of full scale value, that means plus minus 2.5 volt, because here 1 by 10 it would be 10 to the power minus 3, so plus minus 2.5 volt, so that would be plus minus 3.5 volt. So the error will be plus minus 3.5 volt, plus minus 3.5 millivolt actually. So here the answer would be 3.5. So that is the answer. Very easy. Let's go to the, yeah, so 8-bit SAR type ADC is there, resolution is 30 millivolt, and you need to find the digital output. Now if you can analyze this as well, you can do by the analysis as well, but there are 8-bit. If you do by the analysis, then it will take a lot of time. So what we will do, we will apply our formula. What is the formula that I have told you? That analog input divided by the resolution, 30 millivolt. 30 millivolt means 30 millivolt. Yeah. Okay. So this is the value we will get. Since this is a SAR type ADC, so what I will take? I will take the lower value. So I will divide 2.86 divided by 0.03. What I am getting? 95.33 I am getting. I am getting 95.33. Since it is SAR type ADC, I am already super. So I will go down now. So answer will be 95. Now I need to convert 95 into our binary equivalent. That I can do very easily. So 95 into binary equivalent, what that would be? 247, 223, 11, 1, 2, 1. So what I am getting? 1 0 1 1 1 1 1 1 0 1 1 1. This bit is also 0. So that's the answer. Okay. So if you had analyzed it, then you need to go to 8 cycles. Then you will always take bit into action. Then you will take the resolution into action. Then you will multiply the number. So that would take a lot of time. That's why I gave this formula. If you have the formula, you will be able to solve it very quickly. Right? Let's go to the next one. But if they ask somewhere in between, let's just say they ask after 4th clock cycle, what will be the output? So at that time, you need to do the analysis. There is no shortcut. At 5th clock cycle, what will be the output? So at that time, you need to do the analysis. Right? Let's go to the next. So this question you can either assume from analog electronics, or you can say it is from digital electronics as well. Both you can say, right? So here the concept of analog electronics only will be used. Here no concept of DAC or ADC will be used. So what they are saying, you need to find the VREF value. You need to find the value of R such that the maximum current that you can take from VREF, that is limited to 10 milliampere. How much current you are taking from VREF? Can anyone tell? Because here there will be negative positive. This is very obvious. So this node is at 0 only. So from VREF, how much current is going out? From VREF, this resistor R is taking VREF by R current. This resistor 2 to the power 6 R is taking VREF by 2 to the power 6 R current. In that manner, there are these resistors. There are total 8 resistors are there. So VREF divided by 2 to the power 8, 2 to the power 7 R. In between, there are other resistors as well. So basically, how much current is being taken from VREF? Current drawn from VREF. Current drawn from VREF. That is equals to IREF. And how much current is being drawn? VREF by R plus VREF by 2R plus VREF by 2 to the power 2R, in that manner till VREF by 2 to the power 8R, right? 2 to the power 7R. And this should be less than 10 milliampere. This should be less than 10 milliampere. Less than or equals to 10 milliampere, you can say. So this is the scene. VREF value is given. VREF value is given, that is 5 volt. R value we need to find. VREF value is given, that is 5 volt. 5 by R into 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 to the power 7. Should be less than 10 milliampere. So let's solve this one. So can I solve it? Yes. A 1 minus R to the power n upon R minus 1. or 1 minus R into 5 by R should be less than 10 milliampere. 10 into 1 minus 1 by 2 to the power 8 should be less than R. But certainly there is milliampere. Look, 2 into 1 minus 10 to the power 1 minus 10 to the power 8 divided by 10 milli. So R should be greater than what? This is what we are getting. So 2 to the power minus 8 you can say, or 0.2 to the power 8 minus 1 into 10 into 10 to the power 2. So 99 point, R should be greater than 99.09375. So R should be greater than this particular value. So which values will be there? 998 and 1099. So 3 and 4 are correct. Well and good. Okay then. Yeah, that's it. Thank you. Yeah, let's see the solution of this question. So here I have already written the next state equation. What they are asking, number of unused state. So total states are 8, right? Total states using 3 flip-flop you can get total 8 states. So let's see how many states are there in the counter. So let's begin from 0, 0, 0. So next state equation you can write down, right? Next state equation will be j q bar plus k bar qn. So here j is q1 into q naught into q2 bar, and here what is the k? K is q naught only. So q naught bar q2. In that manner I have written for q naught plus, that is, this is in toggle mode only, so toggle answer is there, and for q1 bar I have written q naught into q2 bar dot q1 bar plus q naught bar into q1. So this is how I have written. So what will be your q naught plus? Q naught plus will simply be q naught bar. So let's take it here. Q naught plus will simply be q naught bar. So this is just in toggle mode, so it will keep on toggling. What will be your q1 plus? Q1 plus will be here q2 bar into q1 bar, q2 bar into q1 bar, multiplication of these two, and then multiply with this one. So it would be 0 only, 0. This would be 0. What about this one? q1 into q naught 0, q2 is already 0, 0. This will again toggle. What about now? q1 plus. q1 plus will be, this is 1, this would be 1, and this would be 1. So this would be 1. And what about q2 plus? q2 is 0, here q1 is 0, so this will be 0. So in that manner we are going, this will toggle. Now what about q1? Since q naught is 0, this guy is 0, and q1 plus we are talking about now. So q naught is 0, so this term is gone. Now next term q naught bar q1. So 1 into 1, 1. It would be 1 only. What about q2 plus? q2 plus q naught bar into q2. q naught bar 1 into 0. This term is 0, and this term will be again 0. So this is again 0. This is again toggling. q1 plus, what will be q1 plus? q naught bar is 0. This term is gone, and this term will be gone. So q1 plus is 0 now. What about q2 plus? q2 plus will be q2 0. This term is 0, and q2 bar 1, 1, 1. So this will be 1. So in that manner we are going. Again it is toggling. Now what will be your q1 plus? q1 plus will be q naught bar into q1, q naught bar into q1, 1 into 0, and this is 0, so this will be 0 only. And what about q2 plus? q2 plus is q1 q naught q2 bar. So q naught is there, this is 0, this is becoming 1, right? Let's check back again. q1 into q naught, this term will be 0, but q naught bar is 1, and then q2. So this is becoming 1, 0, 1. Now next state, this will again toggle. What about q1 plus? So q1 plus, q1 is 0 here, here q2 bar will be 0, so this term is 0. What about q2 plus? q2 plus, q1 is 0, so this term is 0, and q naught bar will be 0, so this will be 0. So now you can see these many states are there in the loop. That means these many states will be there in the state diagram. Rest of the states will be unused. So 1, 2, 3, 4, 5, 6. So 6 states are there in the loop. 2 are unused state. So how many states are unused? 2 states are unused. This was a very straightforward. Just during the calculation, you need to have a good amount of patience. You need to put a good amount of concentration, then only you will be able to solve it. So it would take roughly around, I guess, 3 to 4 minutes it would take to solve in the examination. But it is an easy question. Let's go to the next. Yeah, so timing diagram is given. RS input, RS latch is given. The timing diagram is A, B, C, D are the points at point A, at point B, at point C, and at point D. You need to tell what will be your output. So when S and R both are 0, you cannot comment hold state. When S is 1 and R is 0, at that time Q will be 1. Now when at point A, what is the condition? This is the output Q I am writing. At point A, what is the condition? S is 0, R is 0. That means it is a hold condition. So at point A, your output will be 1. Then after that, R is 1 and S is 0. So again it will be in reset state. After that, what is happening? At point B, again 0, 0. That means again hold. So at point B, you will be having 0. What student would have done is that they would have directly looked at A. They would have ignored this condition. Then they will say that, sir, at A, 0, 0 is there. That means it is hold. Now what is the previous condition? Previous condition you will determine from here, no? Right? So at B, it would be 0, 0. At C, so before going to C, there would be these conditions. Before going to C, there would be these conditions. That it will be here, it will be, this is the reset button. So here it will be reset. Then it will be hold. Then again it will be set. So at this point, it will be again set. Then here, 1, 1, again 1, 1 is there. That means it will toggle. But here at point C, what do you see? R is 1 and S is 0. That means it is reset. Right? At point C, it is reset. And what about at point B, D? Now it is reset. Then going ahead here, this is 1, 1 toggle. Now here at this point, 1, 0. At this point, at 1, 0, it has been set. And at D, it will be hold. So it has been set here, no? Right? It has been set. At D, you are holding. You are holding what? You are holding the previous state. And what is the previous state? Previous state is S being 1 and R being 0. That means set state you are holding. So at A, you are having 1. B, you are having 0. C, you are having 0. And D, you are having 1. So this is the answer. Okay. So always you need to look at the previous state. Here hold state was there. Here also hold. Here also hold. So you need to look at the previous one. Okay. Let's go to the next one. Yeah. So what is this equivalent to? So this is a good concept. Here A XNOR B XOR C XNOR D XOR E XNOR F. So I told you one thing. If one dot goes out, it will be going out as a bar and dot will be replaced with a plus. Basically, A XNOR B. If this dot goes out, so what I can do? If I am replacing this dot with plus, then I need to take bar. You can try it in any other options as well. If I am replacing this dot with plus, then what I need to do? I need to take the whole bar. And in XOR operation, you know one thing, that whole bar can be taken on one variable as well. Right? Whole bar can be taken on one variable as well. This whole bar, these two are equivalent only. Right? We have studied these kind of things. So similarly, we will do this analysis here as well. What we can do is that, if I take this dot outward, this dot outward, and this dot outward. So what I will do? I will take this dot as plus. Then I will take next dot as plus as well. And then I will take this dot as plus as well. So I am taking 3 dot outward. That means 3 bar will come here. Basically 1 bar, 2 bar and 3 bar will come. So 3 bar will cancel out and it will be equivalent to 1 bar only. A bar, then another bar and then another bar. So what is this? This is equals to A only. So answer would be A bar. So 3 bar will be cancelled out and it will be equivalent to 1 bar only. So option 4 you can see. This is correct. Now here, if you take this dot outward, this dot outward, this dot outward, this dot outward and this dot outward. So you are taking 5 dot outward. That means 5 bar will be coming. And if 5 bar comes, then 4 will be cancelled out and only 1 bar will be left. Are you getting this point? So if I replace all the dots with plus, then only 1 bar will be left. So you are getting the same option. And this option is equivalent to this guy. That means certainly this option is also correct. Here you check. If I take this dot outward, then what will happen? If I replace this dot with plus, then how much bar will come into action? Only 1 bar will come into action. So certainly this is also same and this is same to this one. So this is also correct. And here if I take 3 dot outward, then how many bar come? 3 bars will come and 3 bar is equivalent to 1 bar only. So this and this is also same. Certainly this is also correct. So this is the one trick that I have already told you, that if you are replacing dot with plus, then bar would come, and that bar can be taken on any single variable. What I mean to say is that I can write this as like this as well, or I can write this as well, that this complete bar can be taken on any of the variable, right? Well and good, fine. Okay, so like these equivalence example can be asked in the examination. Let's go to the next one. Here I removed the solution. Why did I do so? Oh, forget about it. You have the video, so why do you need the written solution? Now that's a good question. Like what I feel is that you guys would have clicked on this 3 answer. You guys would have clicked on this 3 answer. A lot of guys would have clicked on this 3 answer. Here what they are asking, you need to generate this sequence, right? So what people would have thought that, sir, I need to generate 1, 1, 1 and 0. Okay. So sir, these 3 ones are same. And if I use a asynchronous counter, that means if I use a binary counter or non-binary counter, if I use asynchronous counter, that means I need to differentiate these 3 ones, and to differentiate these 3 ones I need to use 2 bits. What I mean to say is that this one I am giving 0 bit, this one is given as 1 0 bit, and this one is given as 1 0 bit, and this 0 can be given any of the bits. Basically using only 1 bit I could not differentiate it. What I mean to say is that 1 1 1 0. Now I am saying that differentiate these 3 ones. So can you differentiate it using 1 bit only? If I use only 1 bit, that means 0 I can give to this guy, 1 I can give to this guy, then again 0 I will have to give 0 to this guy only, or I will have to give 1 to this guy. So I need to use 2 bit at least. So total 3 bits are required now. Total number of bits required are 3. And if total number of bits required are 3, that means you need to use 3 flip-flops. So answer should be 3. No. Why is that so? Because I told you this is not the only way of generating a sequence. If you remember the sequence generation video, there I told you there is another way of generating the sequence, and that is using synchronous counter. Luckily in the examination till this date, all the questions that has been asked, luckily we have got the correct answer using this concept, 1 1 1 0 and then 0 0 here. But that is the lucky thing. What if in the examination this question is asked? Then what you will do? So here what you need to generate? Here you need to generate a sequence of length 4. Basically you need to generate a sequence of length 4, 1 1 1 0. So what I will do? I will design a mode 2 counter. What I am doing? I am designing a mode 2 counter using asynchronous counter, using synchronous counter, anything. What I am doing is that I am designing mode 2 counter. Mode 2 up counter I can design, mode 2 down counter I can design. So what will be the output of mode 2 counter? 0 0, 0 1, 1 0 and 1 1. Now this output of the counter can be fed to a combinational circuit. Now this combination circuit will generate an output in a manner that when the applied input is 0 0, this combination circuit will generate a single output. This combination circuit will generate a single output, and it will generate the output in a manner that when applied input is 0 0, then output should be 1. When applied input is 0 1, then output should be 1. When applied input is 1 0, then output should be 1. And when applied input is 1 1, output should be 0. Are you understanding this point? You are having a clock. And you have designed mode 2 counter. Let me give you the design. Okay, it would be very easy design. Roughly only I will give you the design, but I hope a lot of guys would have already understood that what I mean to say. So this is, let's just say this is your D flip flop only. This is Q, this is Q bar, this is D, this is Q, this is Q bar. Okay, and this is going here like this, and this is the clock we are using. Okay, this is the clock we are using. So this I am calling as Q0, and this I am calling as Q1. So this will be your MSB, and this will be your LSB. So now here what I will receive, I am saying that my initial condition is 0 0. So what kind of counter it is? It is a binary up counter. So here initially I will receive 0 0. Then after another clock cycle I will receive 0 1, or opposite I am saying. Initially here I will receive 0 0, then I will receive 0 0 I will receive, then I will receive 0 1, then I will receive 1 0 and then I will receive 1 1. Now what I'm going to do is that I'm going to connect a combination circuit here. Now I will design this combination circuit in a manner that, how I will design? Q1 Q0. This combination circuit has an output Y. I will design it in a manner that when applied input is 0 0, it should give me output 1. When applied input is 0 1, it should give me output 1. When applied input is 1 0, it should give me output 1. And when applied input is 1 1, it should give me output 0. So what will be the logic Y? Logic Y would be simply Q1 bar plus Q0 bar, or you can say Q1 Q0 whole bar. So basically this is a NAND gate. So here at the output I can use a NAND gate. Right? So this will be my final output. So now what I'm going to do is that I'm going to keep all these thing in a box. And now I will go and I will tell the user that you apply the clock. Just as you apply the clock, what will happen? Here 0 0 will come. 0 0, what this will generate? 1. Then I will tell the user apply another clock. Just as he applies another clock, what will come here? Here what will come? 0 1 would come. So 0 1, what it will generate? 1 again. Then I will tell the user apply another clock. Then what will happen here? Here another 0 1 would come. Then again it will generate 1. Now I will tell the user apply another clock, and just he applies another clock. What will happen? 1 1 will come. 1 1 0. Then I will tell him again apply the clock. Then what will happen? 0 0 will come. Then again 1. In that manner the sequence will keep on coming. So how many flops you used here? 2 only. But here the extra thing that is required is a NAND gate. So here I have written it. You are free to use any combination circuit. So in the examination, if these kind of questions are coming, so don't go by this concept, because 100% of the educator in this field, I have seen their notes. So all the educators teach in this manner only, 1 1 1 0 and then differentiate it. But that is not the concept. That is the way when you don't need to use any other combination circuit. But we can use any combination circuit. So if we can use any combination circuit, then just by looking here, just by using 2 flip-flops only, I am able to generate it. So if I say one statement, okay, now I'm gonna say one statement. To generate a sequence of length S, listen to me very carefully, okay, listen to me very carefully. To generate a sequence of length S, you need log 2s flip-flops. Say yes or no. What do I mean by that? To generate a sequence of length 4, this is a sequence of length 4. Why length 4? Because after 4 it is being repeated. So this is a sequence of length 4. I need log 2 4 flip-flop, and that is equals to 2 only. Let's just say I need a sequence of length 6. I need to generate 1 0 1 0 1 0. Okay, and then again this thing will be repeated. So what I need? I would need 3 flip-flop. What I mean to say is that sir, when your output is 0 0 0, that means your counter is giving you 0 0 0. At that time you generate 1. When your counter is giving 0 0 1, at that time you generate 0. When your counter is giving you 0 1 0, at that time you generate 1 again. When counter is giving 0 1 1, then you can generate 0. When counter is giving you 1 0 0, then you can generate 1. And when counter is giving you 1 0 1, then you can generate 0. Then I will design in a manner that again it will go here. I will design the counter in a manner that it counts from 0 to 5 only. Then again it goes to 0. Then again 1 0 1. In that manner I will design my counter. So I will take out these outputs of counter. And will connect it to a combination circuit. And that combination circuit I will design in a manner that at 0 0 0 it is giving me 1. So that combination circuit also I will design. So how many flip-flops I require here? 3. So what will be the answer? Log 2 6. So this answer would be somewhat 2 point something. But you know 2 point something flops you cannot use. So you have to use the larger number. So answer would be 3. So to generate a sequence of length S, I would require log 2s flip-flops. Okay, and if you are getting any number, which is in the decimal, then you need to take the larger number. That means you are taking your least integer function, right? What we need to take? Least integer function. What do we mean by least integer function? That means you need to take the larger value. What is the value of 2.33 here? The value of 2.33 least integer function is 3 only. Okay, so in that manner we need to proceed. So I hope you would have got this concept, and those who have studied sequence generation, for them this concept would have been clear, and those who haven't studied sequence generation, those who did not study from PrepFusion, they would have also understood this concept. Okay, so sequence generation, FSM, sequence detection, these are very good concept. I don't know why these are not taught in a great manner in this field, but certainly a lot of questions has come. There is a question on traffic light in GATE 2018, that question came. So like there has been n number of solution from different people. Some are saying this question is from FSM, some are solving in the which manner, like there are n number of solution. But that question was not from FSM, that question was from sequence generation. There you need to generate a particular sequence. That's it, nothing else. So that solution also I have given on YouTube only. You can go and check out. So yeah, okay. Let's go to the next question now. So this question is based on 5 variable K-map. So 5 variables are there. You need to make the K-map. K-map I have already drawn. You can draw it on your own. So 3, 4, 6, 3, 4, 6, 11. Where is 11? 11, 12, 14, 17, 20, 22, 25, 28 and 30. So this is the scene. Okay. Now what you can see is that here you are getting one quad. The same quad you are getting here as well. That means these 8 points can be mapped. This will be mapped to this guy. This will be mapped to this guy. This will be mapped to this guy. And this will be mapped to this guy. Although this example is there from our class note only. Right. So 8 guys can be mapped here. So A is also changing. A is certainly changing. Here what is changing? 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Okay. So here I can see that these are the 8 guys. So here C is constant and E bar is constant. So CE bar I am getting. Right. CE bar we are getting plus 1 pair, this pair we are getting. So here A is constant, that is A bar. What else is constant? Certainly here DE is constant. DE is constant. And what else is constant? C bar is also constant. Plus this also pair we are getting. Here A is constant. What else is constant? 0, 0, 0, 1. And this is 0, 0, 0, 1, 1, 0, 1, 1. Sorry, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. So here A is constant, D bar, E is constant, and C bar is constant. So A, C bar, D bar, E, C bar, option 1 is correct. So a very simple example of 5 variable K-map. If you have studied it, then you will be able to solve. If you haven't studied it, then you might not be able to solve it. Let's go to the next. Yeah, let's see this question. This is also very conceptual question, and I know a lot of guys might have matched it up. So here 2 mod 3 counter are in cascade. So you would say that, sir, final output will be mod 9 counter, and it would be mod 9 up counter. You are correct. It would be mod 9 counter. Till this statement you are correct. It would be mod 9 counter. And how the sequence will be going? You will be saying, sir, this is also up, this is also up. So mod 9 up counter. So this is how it should go. 0, 0, 1, 0 till 9 it should go basically. Absolutely wrong. Doesn't make any sense. So that's why I always say, if the question is coming from sequential circuits, or if the question is coming from digital electronics, always analyze the given block. If the question was like what is the total mode, then you would say mode 9, that's it. But here they are asking like a duty cycle, output frequency, then always analyze it. Better than like rather than mugging up some formula, better analyze it. How will we analyze? So this is mode 3 up counter, this is also mode 3 up counter. So first, just as the clock comes, so it will count up 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0. In that manner it will keep on counting, right? 0, 0, 0, 1, 1, 0. In that manner it will keep on counting, it will keep on going like this, right? Now this guy will also count up, this guy will also count up, but that will depend on this output. On this output it will depend. Are you getting this point or not? This would be the LSB of this guy, no? So yeah, here it should have been mentioned. Here it should have been mentioned that output of like LSB is going or MSB is going. So here I will mention in the question. So this is the LSB of the output. This should be mentioned. Okay. So if this LSB goes from 0 to 1, what kind of edge triggering you can see here? Positive edge triggering. So if this bit goes from 0 to 1, then only it will count up. Otherwise it will be on hold state. So basically, if we start from 0 0, so now if this is going from 0 to 1, then it will count up. Now it is going from 1 to 0. So at negative edge it will not count up. It will be there in the same state. 0 0 it will be there in the same state. Now again it is going from 0 to 1. Then again it will count up. 1 0. Going from 1 to 0, same state. Going from 0 to 0, same state. Again going from 0 to 1, again it will count up. So 0 0 0 1 1 0, again 0 0. 1 to 0, same state. 0 to 0, same state. 0 to 1, again it will count up. So how it will count up? 0 1. Right? And now you can see that this state is being repeated. So now you can see this is the mode of your counter. 1 2 3 4 5 6 7 8 9, mode 9. Now what they are asking? They are asking the output frequency. What they are asking output frequency. So since this is a mode 9 counter, so you can say that frequency will be f clock by 9, or better how you can see is that this sequence is being repeated. No, this sequence is being repeated. So in this sequence there would have been 9 clock cycles. Are you getting this point? This is the time period of the final bit. No, this is the time period of the final bit. This is the time period of the final bit, and that is equals to 90 clock. Here this bit will be there for 1 T clock, this bit will be there for 1 T clock, this bit will be there for 1 T clock, this bit will also be there for 1 T clock, 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 1 T clock. So these all bits will be there combined for 90 clock time. So what will be the time period? Time period will be equals to 90 clock. So what will be the frequency? Frequency will be f clock by 9. So this was the easy part. F clock by 9. What will be the answer? F clock is 12 by 9. So 1.33. Right? But now what about what they are asking? Duty cycle. So here you can see there are total 9 state. Total 9 state. Out of these 9 state, only for 3, there are total 9 time instant you can say, or total 9 state also you can say. Out of these 9 state, only 3 times it is 1, otherwise it is 0. So how will I calculate the duty cycle? Basically it was 0, then it was 1, 1, 1, then 0, 0, 0, 0 in that manner. So total state were 9. Out of these only 3 bits it was high. That means this is the duty cycle. So duty cycle is 33.33%. So answer is 4. A very good question. So this is how you need to solve it. Although it should have been mentioned that LSB is going to the next state. Okay. Yeah, let's move to the next. Yeah, so let's see this question. Which of the states could be reduced? So this is the question based on state diagram reduction in FSM. So what we need to do? Here we will write down the current state. Current state is S0, S1, S2, S3. With respect to input, what will be the next state? This is what we are writing. And with respect to the input, what will be the output? This is what we are writing now. Okay. So if current state is S0 and applied input is 0, then next state will be S0 as well and giving the output 0. If current state is S1 and in S0 only. If current state is S0 and applied input is 1, the next state will be S1 giving the output 0. If current state is S1, applied input is 0, the next state will be S2 giving the output to be 0. If current state is S1, applied input is 1, the next state will be S1 giving the output to 0. If current state is S2, and applied input is 0, then next state will be S0 giving the output to be 0. If current state is S2 and applied input is 1, the next state will be S3 giving the output to be 1. If current state is S3 and applied input is 0, then next state will be S2 giving the output 0. If current state is S3 and applied input is 1, the next state will be S1 giving the output to be 0. So what you can see here is that this row and this row both are same. S2, S1, 0, 0, S2, S1, 0, 0. That means S1 and S3 are equivalent to each other. S1 and S3 are equivalent to each other. Very straightforward problem. Very, very straightforward. Okay, let's go to the next. So here what they are asking the expression of output Z they are asking. So one thing is that you can solve it conventionally. How will you solve it conventionally? expression of Z they are asking in terms of Q1, Q2, Q3 and X. So what you are going to do, you will write down here Q1, Q2, Q3 and X. So 16 input you will write down, and with respect to that you will write down your output Z. That means if Q1 is 0, 0, 0, 0, 0 is denoted by A. So if Q1, Q2, Q3 is 0, 0, 0, that means if you are currently in state A and your applied input is X equals to 0, then what is your output? 0. And let's just say you are in state A only and applied input is 1, then what will be your output? Output will be 0 only. In that manner you need to write. So when you are receiving your output to be 1, here you are receiving your output to be 1. Where you are receiving your output to be 1? Here. That means you are currently in state D. D is represented by 1, 1, 0. You are currently in state D and your applied input is 0. Your applied input is 0. You are currently in state D and your applied input is 0, then your output would be 1. So we can make the K-map. What we can do is that we can make the K-map and then we can denote all these numbers. Basically, better than making the table, directly I will make the K-map. How will I make the K-map? So here I am writing down Q1, Q2 and here I am writing Q3X. So I am just looking at all those possibilities when I can get 1. So when I can get 1, when I am in state D and my applied input is 0. What do I mean by state D? State D means 1, 1, 0. So 1, 1, 0, 0. 1, 1, 0, 0 is the condition when I am getting 1. 1, 1, 0, 0. When I get 1, 1, 0, 0, let's check that out. 1, 1, 0, 0. So here I am getting 1. Next, when I am getting 1, when I am currently in state E and applied input is 1. Currently in state E, that means 1, 0, 0. So 1, 0, 0, 1. 1, 0, 0, 1 is giving me 1. Did you understand this point? Q1, Q2, Q3, X. And this is my output Z. So when I am in state E, what is state E? 1, 0, 0. And my applied input is X equals to 0. When my applied input is, X equals to 1. When my applied input is X equals to 1, at that time my output will be 1. So 1, 0, 0, 1. 1, 0, 0, 1 is giving me 1. Let's check the next one. This we have seen. This. Although you can check by option as well. Like you can put the value in option as well, or you can make the K-maps as well. It's up to you. Okay, I am making the K-map now, as of now. But in the examination, I would have checked by option. I would have just put these values. If I put Q1, Q2 equals to 1, 1 and rest all 0, 0. So 1, 1, 1. Here Z is becoming 1. But here 1, this is 0 and this is also 0. So this option is 1. Like by looking at this possible option only, I have eradicated this option. Because answer should be 1. If I put all these values, then answer should be 1. But here I am not getting answer to be 1. And here also I am getting answer to be 0. So this option is also 1. Only this option is left. Or you can make the K-map as well. So making K-map I am leaving up to you. Will you be able to make it? Right? From here can you make the K-map? I am currently in state F. That means I am in 1, 1, 1, 1. And my output and my applied input is 0. Then I will receive 1. That means I am currently in state 1, 1, 1, 0. Next you see for this one. You are currently in state G. G is written as 1, 0, 1 and applied input is 1. Okay, applied input is 0 here. Let's check for this one again. If I am state in F, so 1, 1, 1, 0. 1, 1, 1, 0. Okay, yeah. In G, you are currently in state 1, 0, 1. 1, 0, 1 and applied input is 1. 1, 0, 1, 0, 1, 1. 1, 0, 1, 1. And what about the last two? H. H is saying 0, 1, 0, 0, 0, 1, 0, 1. 0, 1, 0, 0, 0, 1, 0, 1. So this is the condition. So here what we can see is that 3 groups we can make directly. I can very easily I can see 1 group, 2 group and 3 group. So from there you will get this expression. Okay, you will get this expression. Very easy question. Let's move to the next. Yeah, so this is a very easy question. 16-bit serial in parallel out storage is there. Serial in parallel out. Let's take example of 4 only. So how many clock cycles will be required to take out the complete input? So from here we are applying the input. Let's just say the applied input is 1, 1, 1, 1. So one clock cycle, this one will go in. Another clock cycle, this one will go ahead, another one will come in. Another clock cycle, this one will go ahead. Sorry, this one will go ahead, this one will go ahead, another one will come in. Another clock cycle, all three will go ahead, another one will come in. So one clock cycle, two clock cycle, three clock cycle, and four clock cycle. So in four clock cycle, you have inserted all the input, and since it is parallel out, that means it is already available. So how many clock cycles are required? 4. So 4-bit shift register. For 4-bit shift register, 4 clock cycles are required. So for 16-bit, 16 clock cycle will be required. So time required will be 16 T clock. And what is T clock? 1 by 8 megahertz. So what will be the answer? 2 microsecond. So answer is 2 microsecond. Very easy, very straightforward. And we have solved a lot of problem on shift register now. So you should be comfortable with that. Let's go to, yeah, so this is a good question, and I don't think anyone would have been able to solve it. Because here there is a arithmetic shift right operation. There are two kind of operation, arithmetic and logical. So even in my notes as well, this was not there. Why is that so? Because this is a topic of COA. Okay, this we study in COA, and since COA is there in your syllabus, that's why these kind of questions can be asked. And this question I got from NPTEL. So if it is there on NPTEL, then certainly it can be coming in your examination as well. So the thing is, what they are saying, there are two different terms. You can see that. Which terms are there? Arithmetic shift left. Okay. Then arithmetic shift right. Then logical shift right. These three terms are there. So let's understand the meaning of all these three terms. So arithmetic shift left or logical shift left, both are same thing. Shifting left means both are the same thing. Shifting left. Left is this and this is right. Okay. This is left and this is right. So arithmetic shift left or logical shift left, both are the same thing. What you need to do, you need to shift all these bits to the left side. That means all these bits will be shifted to the left side. So this one will be going down. Let's just assume this as a room. Just assume this as a room. Have you guys seen the web series named Squid Game? So in that game, what happens? Everyone dies. If you disqualify the game, that means you are dying. So basically, let's just say this is here. There is a let us say there is something. So this guy will jump. So one will be dying. Now this guy will move ahead. This 0 will move ahead. This one will move ahead, and this one will move ahead. Right? So this one will move ahead, 0 will move ahead, 1 will move ahead, 1 will move ahead. Now this space will be blank. So this place will be filled with 0. Let's take another example. 0, 1, 1, 0, 1. So what will happen? This guy will die and all these will shift. And the blank space will be filled with 0. So this is the meaning of arithmetic shift left or logical shift left. Right? So arithmetic and logical shift left both are the same thing, and it is very easy as well. Okay. Now let's talk about logical shift right. So in logical shift right, what will happen is that you will shift all these operation to, logical shift right. So in logical shift right, what will happen? You will shift all these bits to right side. So what will happen? This guy will fall. So this guy will die. Then what will happen? This 0 will be shifted here. 1 will be shifted here. 0 will be shifted here. Another 1 will be shifted here. Another 1 will be shifted here. And here there will be vacancy. So this vacancy will be filled with 0. Let's take another example. 1, 0, 1, 0, 0, 1, 0. So what will happen? This 0 will die. 1 is shifted, 0 is shifted, 0 is shifted, 1 is shifted, 0 is shifted, 1 is shifted. Okay. Now arithmetic shift right operation. What will happen here? Here also you need to do the same thing. Ditto same thing you need to do. Basically you need to shift right. That means this guy will die. This guy will fall off. This guy is falling off a building. This number is standing on a building. So this guy has fallen off. So this guy is gone. 0, 1, 0, 1, 1. This is how you will shift it. This guy is gone. So 0, 1. This 0 is shifting ahead. 1 is shifting ahead. 0 is shifting ahead. 1 is shifting ahead. And 1 is shifting ahead. So this is what you are getting. Now the blank space will be filled with the same number. This first same number. Because here in arithmetic shift right, this one number represents the sign bit. So we are not going to change the sign bit. We have performed the arithmetic shift right operation. So this sign bit will be there as it is. This one will be there as it is. Are you getting this point? we are going to perform the sign bit, we are going to perform the shift right operation only, but in the blank space the sign bit will be remained. Here what will happen? This 0 will fall off, 0 will die. So 1 1 0 1 0. Now in the blank space what will come? The sign bit will come, this bit will come, so that would be 0. Let's take this example 1 0 1 0 0 1 0. So what will happen? This 0 will die. So 1 0 0 1 0 1, and in the blank space 1 will come. This sign bit will be remained. Now you can solve this question. Now try solving this question. I hope you know the meaning of this thing. That means this is a BCD code. Basically 8-bit shift register is there. So in 8-bit shift register the content is 0x58. What is the meaning of this? How 5 will be represented in 4 bits? 5 in 4 bits will be represented as 0 1 0 1, and then 8 1 0 0 0. Basically 4 bit total 8 bit. So in the first register of 4 bit 5 is there, in the second register of 4 bit 8 is there, and both combined is making 8 bit register. Now for this particular input you can say, or anything you can say, for this particular register you perform first what we need to do. First arithmetic shift left operation is performed. Shift left, left means we need to shift this side. So this 0 will die. So 1 0 1 1 0 0 0, and blank space will be filled with 0. So this is the first operation. The next operation, arithmetic shift right. So in arithmetic shift right means this 0 will die. So normal operation we will perform 0 0 0 1 1 0 1. Now the blank space will be filled with the sign bit 1. Now what they are saying, followed by logical shift right. Logical shift right. So in logical shift right what will happen? Again this 0 will die. 0 0 1 1 0 1 1. So blank space will be filled with 0. Blank space will be filled with 0. So this is the final answer. Okay. First we performed arithmetic shift left, arithmetic shift left. Okay, left is here. Arithmetic shift left. So that is same as logical shift left. So that is very simple. Blank space will be filled with 0. Then we performed arithmetic shift right. So that is also simple only, but the blank space will be filled with the sign bit. And then we performed logical shift right. So that is also similar only, but the blank space will be filled with 0. Okay, so this is the final answer we are getting. So you take 4 bits, you take 4 bits. What is this? This is 1 2 4. This is 6. And what is this? This is 12. So this is 0x6, and how do you represent 12? 12 as C, 6C. Okay. So these kind of questions like arithmetic shift left has not been asked in the examination, but who knows, it can be asked. Okay, so this is something new concept which was not there in my notes as well. So now I have given this in test series. Okay, let's go to the next one. Yeah, so let's see this one, shaded portion. So how much this portion is representing? Here A is also there and C is also there. And how much this portion is representing? Here A is also there, B is also there, but C is not there. So this is how it represents. So AC plus ABC bar. So this is the first option only. Now from these options only you can get the other option as well. What is the next option? A B bar C plus AB. So A B plus B bar C. What you are getting? A B plus C. What is this? AB plus AC. So these two options are same. Now from first option only I can get AB plus AC. How will I get? A as common, C plus BC bar. So from here what I am getting? A B plus C. So what I am getting? AB plus AC. Which kind of law I am applying? I hope you are understanding, right? Like this is the full length test series we are writing down, so we know these basic laws. So this option. Similarly, you can get this option as well. Or how you can think that you need to get this option A B bar C. How will you represent A B bar C here? A is there, C is there, but B is not there. That means A is there, C is there, but B is not there. You are talking about this option. You are talking about this portion. A is there, C is there, but B is not there. And then AB. That means A is there and B is there. This portion we are talking about. So again, shaded portion we are getting. Let's talk about this option. Let's talk about the final one. So in the final one, what do we see? A is there, B is there, but C is not there. A is there, B is there, but C is not there. This one, right? Second one, A is there, C is there, but B is not there. A is there, C is there, but B is not there. A is there, C is there, but B is not there. What is the final one? A, B, C, all three are there. A, B, C, all three are there. So again, you are getting the complete shaded portion. So this option is also correct. So any way you can solve it. There are n number of ways. There are n number of ways of solving this question. Okay. So this was easy. Only 1, 2, 3, 4. All are correct. Let's go to the next one. Yeah, let's see this question. This is a very good question, and we have seen four level of problems or four type of problem on this particular concept. Like in binary parallel adder, in n-bit binary parallel adder, we have seen the delay concept, right? So what they are saying here, the full adders are made using two XOR gate, two AND gate, and one OR gate. That means what does that mean? It is made from two half adder and one OR gate, right? The delay of XOR gate is mentioned, that means some delay is 3 nanosecond. Sum of half adder. For half adder, some delay is 3 nanosecond and your carry delay is 2 nanosecond. Why is that so? And OR gate delay is 3 nanosecond. Why I am writing so? Because in half adder, this is my sum bit and this is my carry bit, right? A, B, A, B. This is my sum bit. So sum will be delayed by XOR gate delay 3 nanosecond and carry bit will be delayed by 2 nanosecond. Now the final stable output of a binary parallel adder, of n-bit binary parallel adder, I am receiving at 108 nanosecond. That means then what will be the value of n? This is what they are asking. Okay, a very good question. You need to think about it. So this is how the full adder will be made. Half adder, and then there is a OR gate. And I told you, you should have enough practice to make this kind of circuit within 15 to 20 seconds. I told you again and again that you need to draw it 3 to 4 times. And again you draw it, then you will build up good practice. Because if you need to solve good problems on delay, then you should have a good enough practice of making this kind of circuit. So after how much time? Now this is one stage. Now there will be these kind of state will be there, and these kind of state will be there, no? Like this would be the final sum and this would be the final carry. Now this carry will be fed to the next stage. That means this carry will be going here in the next stage. This carry will be going here in the next stage, right? And all the operations will start at t equals to 0 only. So after that, when you will receive sum at 3 nanosecond, you will receive sum, and this carry you will receive at 2 nanosecond only. So this thing is common in all the stages. Basically, in this stage as well, this thing is common. At 3 nanosecond, you will have this bit. At 2 nanosecond, you will have this bit. But what about the next stage now? 3 nanosecond. For first stage, this is I am making only first stage. So for first stage, your carry has been received at 0 nanosecond only. Now this operation will start at 3 nanosecond only. So 3 nanosecond plus 3 nanosecond sum will be received after 6 nanosecond. This first sum will be received after 6 nanosecond. And now this carry here, this operation started at 3 nanosecond. So carry will be received after 3 plus 2, 5 nanosecond. So final carry will be received after 5 plus 3, 8 nanosecond. Now after 8 nanosecond, this carry will be fed back to this guy in the next stage. In the next stage will also be same. So this carry after 8 nanosecond will be fed here. So this carry will be fed here after 8 nanosecond. So I am making only in one stage. This we have already studied, right? I have taught this concept in roughly around 2 hours. So there I spent a lot of time. So now I will make in one diagram only that at 8 nanosecond this has been fed. At 8 nanosecond this has been fed. And in the next stage, this operation would have already done at 3 nanosecond and this operation would have been already done at 2 nanosecond only. So now at 8 nanosecond this carry is coming. So 8 plus 3, next output you will receive at 11 nanosecond. Now 8 plus 2, here you will receive after 10 nanosecond, and 10 plus 3, 13 nanosecond. So this is the output of the second stage. Now at 13 nanosecond, this will be again fed. This is the output of, now this we are talking about third stage now. Now we are analyzing third stage, but we will make the diagram only once. So 13 plus 3, sum will be received at 16 nanosecond. Now 13 plus 2 plus 3, that means another 5 will be added. So at 18 nanosecond you will receive the another carry. So if there were only 3 stages, let's just say if n was 3, if it was 3-bit binary parallel adder, then you would have received your output at 18 nanosecond. Now if n was 4, then when you would receive your stable output? If n was 4, so at 18 nanosecond this guy would go. So 18 plus 3, that means at 21 nanosecond you will receive your sum bit, but your carry bit will be received after 18 plus 2 plus 3. That means 18 plus 2 plus 3, what that would be? 23 nanosecond. So if n was 4, you would have received it at 23 nanosecond. So in that manner it is going, starting with 8 nanosecond, then 13 if n was 1, then 8 nanosecond. If n was 2, then 13 nanosecond. If n was 3, then 18 nanosecond. If n was 4, then 23 nanosecond, and it will go in this manner. They are saying that you are receiving your final output at 108 nanosecond. Can you see it as an AP? For this one, n equals to 1. For this guy, n equals to 2. For this guy, n equals to 3. For this guy, n equals to 4. What will be n equals to for this guy? Right? For this guy, n was 1. For this guy, n was 2. For this guy, n was 3. And 4. For this guy, what will be the value of n? This is what you need to find. What will be the value of n for this guy? Okay. So if I write down this as a plus d, again write down this as a plus d. This would be a plus 2d. Why I am writing this as a plus d? Because when we study AP, our first term is a, and that is the first term only, no? So why I am writing as a plus? No, sorry. This would be a only, no? This is the first term. So this I will write as a only. This I will write as a plus d. So what will be the nth term? Nth term will be a plus n minus 1 into d. That would be 108. So 8 plus n minus 1 into 5. 108. So n value is coming out to be 21. So this will be the 21st stage, right? 8 plus 5, 8 plus 5 into 1. So similarly 8 plus 5 into 20, that would be 108. Yeah. So n value is coming out to be 21. So at the 20, if there was 21 stages like this, then you would have received your stable output at 108 nanosecond. Look, I know I am being a bit fast here, because in the theory itself I have spent a lot of time, and this has been uploaded on YouTube itself. So you can go and check out on YouTube as well. That the title would be like in digital electronics playlist, you can find it. It would be like a delay problem in adders. This would be the title. So there you can find it. So this concept I have already taught. The only new thing was that you need to think here that we are getting an AP. If you are getting an AP, then your problem can be framed in this manner as well. So this was framed by me only. Okay. Yeah. Let's move to the next one. Yeah. So that's a very good question. And here I have hidden the answer as well. So let me know what will be the answer. So what is this? Y is equals to A XOR B XOR C XOR D. So this is completely XOR gate, right? Now, how XOR gate is known as? XOR gate is known as odd number of ones detector, right? XOR gate is known as odd numbers of ones detector. That means if number of ones are odd, 1 XOR 1 XOR 1. If the number of ones are odd, then your answer will be 1 only. So that's why XOR gate is known as odd number of ones detector. So you would say that, sir, this answer would be correct. That is correct. XOR gate is not known as even number of zeros detector. So this answer is wrong. You will feel like that. But no, this is also true. So this question is not about XOR gate. This question is about this Y expression. This question is about this Y combinational circuit. That this combinational circuit, can this combinational circuit work as an even number of zeros detector? Yes, this combinational circuit can work as even number of zeros detector. Why is that so? Because if your number of zeros are even, if your Y can be used as even number of zeros detector. What do I mean by that? If your number of zeros are even, that means 2 zeros are there. Let's just say 2 zeros are there. Rest all bit is 1. Rest all bit are 1. So what is the output? 1 only. So if number of zeros are even, here what was the scene? Number of zeros are even. If number of zeros were odd, let's just say only 1 zero was there. If number of zeros were odd, that means rest all bit will be 1. So what is the answer? If number of zeros were odd, then answer is 0. So certainly it is working as even number of zeros detector as well. Why it is working as even number of zeros detector as well? What do you think? Because here if you are putting in this expression, if you are putting even number of zeros, that means either you can put 2 0 or you can put 4 0. Your Y is becoming 1. That means at the input, if I apply even number of zeros, even number of zero means odd number of ones. Even number of zeros means odd number of ones, right? If I apply 4 zeros, if I apply 4 zero, then only one would be there. So even number of zero is equivalent to odd number of one. So if it is odd number of ones detector, then certainly it is even number of zeros detector as well, no? Are you able to understand this point or not? A very good point. I know people would click on this, but they will not click on this one, because they will think it is XOR gate. So why it would be even number of zeros detector? XOR gate is not even number of zeros detector. XNOR gate is even number of zeros detector. But for 5 bits, this can be replaced as XNOR gate as well, right? So it feels like that it is XOR gate, but it is XNOR gate as well. So along with odd number of ones detector, it is even number of zeros detector as well. Okay. So option 1 and 2 both are correct. Now the next question, third option, the number of inputs combination for which y is equals to 1 is 16. So when you can receive y equals to 1? When I can receive y equals to 1, do I have the page? Y is A XOR B XOR C XOR D E. So I can receive y equals to 1 if number of ones are either 1 or 3 or 5. Basically, if A is 1, rest all are 0. A is 1, rest all are 0. This is one desirable condition, or this is also another desirable condition. This will give me output 1, this will give me output 1, or this will also give me output 1. So 3 combination I can already see here, but these are not the only 3. Here I talk about only A, but what may happen is that B is 1, rest all are 0, or what may happen is that C is 1, rest all are 0, or what may happen is that D is 1, rest all are 0, or what may happen is that E is 1, rest all are 0. These things can happen, no? So basically, from 5 you need to choose 1, or from 5 you need to choose any 3. Here you choose these 3. I may choose these 3 as well, I may choose these 3 as well, or I may choose these 2 and this one, or I may choose this one, these 2, these 2. So 5C3 or 5C5. So 5C1 is 5, this is 10, and 5C5 is the total 16. What is the total number of input combination? It could have 0 1, it could have 0 1, it could have 0 1. This is the concept of PNC. It could have 0 1, it could have 0 1. So 2 into 2 into 2 into 2. So total number of combination is 32, or you can say 2 to the power 5. Out of these, 16 combination will give me 1, and another 16 combination will give me 0. So the number of combination for which y equals to 1 is 16. The number of combination for which y equals to 0 is 16. So what is the answer? 1 2 3 4. So this was a very good question. I hope you would have enjoyed it. Let's go to the next one. Yeah, so this is something which was not there in our notes. So this I am only teaching in the test series itself. So for a n bit multiplier, like let's just say if there was 2 bit multiplier, then you could have found out the value of AND gate, full adder and half adder, right? If 3 bit multiplier was there, then also you could have found out. These questions we have seen, right? A2, A1, A naught, B2, B1, B naught. Then we do the calculation and then we see how many half adders are there, how many full adders are there. So that is easy. But if n bit multiplier is there, n bit multiplier is there, n bit multiplier is there. So how many AND gates will be required? So number of AND gates required will be n square. How many full adders will be required? So full adders required will be n square minus 2n. And how many half adder will be required? That would be n. So you remember n square, then you remember n, then n square minus 2n. In that manner you can remember. This n square is very easy to remember. Why is that so? Because let's just say I am taking an example of 2 bit multiplier. So how I will multiply A1 B1, A naught B1, then A1 B naught and A naught B naught. 1 AND gate, 2 AND gate, 3 AND gate, 4 AND gate. So you require 4 AND gate. If it was 3 into 3, then you would require 3 into 3 AND gate. It was 2 into 2, that means you require 2 into 2 AND gate. If it was 1 into 1, A naught into B naught, so only 1 AND gate you require, right? So this is very easy to remember. Are you getting this point? But half adder, full adder. So half adder you would require n. Here you can see which half adder you would require. Here no half adder is required. Here one half adder is required. Then another half adder is required here. So two half adders are required here. So half adders required are n, and full adder required are n square minus 2n. So in this case, no full adder is required. You can see 2 to the power 4 minus 4, that would be 0 only. So these you need to keep in mind. Okay. So for our given example, AND gate required are 64 and half adders required are 8, right? Half adder required are 8, yeah, and then 64 minus 16, 48. Answer is 2. Okay, let's go to the next one. So even parity checker indicates a parity error for which of the following received data and parity bit. So first we will transmit a data to a parity generator. So based on this input, it will generate a parity, and then this data and the parity is given to the parity checker, and then it will give whether there is error or not. So if there is an error, then it will be 1, otherwise it will be 0. So this is what they are asking. This concept also we have seen in our class notes only. So an even parity checker indicates a parity error. Even parity checker. Which parity checker? Even parity checker. So if there is even parity, then your output will be 1. Otherwise it will not be 1. So in this case, is there any even parity? Yes, there is a even parity, because number of ones are 5. Number of ones are 6, then there is no issue. If number of ones are 5, that means E will be 1. Here number of ones are 3, 6, so error will be 0. Here number of ones are 5, because these are 4 and number of 1 is also there. 4 is there and parity is also there. So here also error will be 1. And what about this case? 1, 2, 3, 4. So number of ones are even only, so error will be 0. So 1 and 3 is the answer. Okay. So this is the job of even parity checker. Odd parity checker will give error in these cases, right? Let's go to the next. Yeah, so let's solve this question. This is easy only, just you need to read the question. Okay. So tank has 4 switches that will monitor temperature, pressure, fluid level and weight. You need to design a system that will notify the microprocessor to activate an alarm when any of the following condition is arising. That means if high fluid level will be there and high temperature is there and high pressure is there. If these three are there together, then your light will be lit up. That means alarm will be lit up. So how many inputs are there? Temperature, pressure, this fluid level and weight. So I need to add a page. So inputs are temperature, pressure, fluid level and weight. And based on that you will receive your output Y. So I'm not going to write down all 16 input. Better I would solve with the K-map in the examination, but here since I am explaining it, so I will write down some inputs as well. Otherwise I will directly make the K-map in the examination. How will I make the K-map? This is how I will make the K-map. Temperature, pressure, fluid level and weight. 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay. So high fluid level, high fluid level, high level, high temperature and high pressure and high pressure. And this is don't care. They do not talk about weight here. So this is don't care. Then your alarm will be lit. So condition is 1 1 1 0 and 1 1. Basically this could be 0 or 1 anything. So at 1 1 1 1 1 1 and 1 1 1 0, this will be lit. Are you getting this point? Okay. Let's see the next one. Low fluid level with high temperature and high weight This is don't care now. Sorry. With low fluid level with high temperature and high weight. So this is don't care now. So 1 0 0 1 1 0 0 1 and 1 1 0 1 1 1 0 1. Low fluid level low temperature, low temperature, high pressure, and this is don't care. So 0 1 0 0 0 1 0 1. Low fluid level with high temperature, and low weight. This is don't care. So 1 0 0 0 1 0 0 0 and 1 1 0 0 1 1 0 0, sorry, 1 0 0 0 and 1 1 0 0. So these are the condition for making it 1. Okay, so what I can see is, do I need to make 4 group of 4? Yes, you need to make 4 group of 4. 1 2, sorry, 3 group of 4, sorry, 3 group of 4. So what you are getting y as? If I go to the first one, so p is constant and L bar is constant, plus if I go to this one, so here Tp is constant, plus if I go to the last one, T is constant and L bar is constant. So this is what we are getting. Tp plus PL bar plus PL bar plus TL bar plus TL bar. So this was a very simple question on combination circuit. Just you need to read it and solve it. Let's go to the next one. Yeah, so a latch is given, but this is not a standard latch. This is neither SR latch, this is nor JK latch, it is not even D latch, it is not even T latch. This is a random latch. The mechanism of this random latch we don't know, but I told you how to solve it. You don't need to write down the equations. You just need to solve it the way I have told. So what did I tell you? First you will write down, first you will make the table A, B, and with respect to that, what will be your PQ? So how your AB can vary? AB can take any values because this is what user will apply. So 0 0 0 1 1 0 and 1 1. So first find out these conditions where you are getting the certain output. What do I mean by that is that if I put A equals to 0, then this bit will be 1 and B will be 0 here. So now in this condition you cannot tell what will be 100% output of this gate, this AND gate, and what will be 100% output of this OR gate, because this 0 has to wait for this guy. No? This 0 has to wait for this guy to come, and then you can tell the output. So first I will find out that condition where I can 100% tell my output. So if this bit is 1 and this bit is 0, then 100% I can tell what will be the output. So if this bit is 0, that means this bit has to be 1. So if A is 1 and B is 1, so if A is 1, this bit will be 0, then output will be 1 only, 100%. Why is that so? Because 0 into anything would be 0 only, and 0 not gate, that would give output 1. And if this is 1, then anything would come here, anything added with 1 will be 1 only, and Q will be 0. So this is the output. Okay. Now let's keep A as 1 only. So A is 1, then this is 0, then this will be certainly 1. And let's change B as 0 now. So B as 0. So A is 1, then P is 1. Now B is 0. So B has to wait for this guy. So previously you have seen that P is 1. So now this 1 will be carried here. 1 NOR with 0. So that would be 0 only. How did I write this 1 0? Did you understand this point? Here you cannot tell what will be your Q, because you don't know what is the input here. You have applied 1 here and 0 here. So this 0 has to wait for this input, no? But if I have applied 1 here, that means here you are having 0. So certainly here you will be having 1. So certainly here I can tell it will be 1 only. So 100% it will be 1. So this 0 can take this one. So 1 NOR with 0, that would be 0 only. So this is how I write down 1 0. Are you getting this point? Now what do we do is that we keep B as 1. And A as 0. B as 1 and A as 0. So what this guy will be? This guy will be 1. So now this gate has to wait. But this gate, what is this? 1. Anything OR with 1 will be 1 only, and 1 not, that would give you 0. So Q is 0. So Q equals to 0 I have got to know now. That means in this condition, when A is 0 and B is 1, this guy is not waiting. So Q is certainly 0. So now this 0 can travel here. So 1 NAND with 0, what that would be? 1 only. So here also you are receiving 1 0. Are you getting this point? So this is how we analyze it. This method I have already told. Now the last condition, A is 0 and B is 0. So if A is 0, this guy will be 1, and if B is 0, this guy will be 0. So here both guys needs to wait. Here both of them are waiting. This guy is also waiting and this guy is also waiting. So in this condition, what do we get? We get the hold state. What do we get? We get the hold state. Are you getting this point or not? When both are waiting, that means we will get the hold state. Okay. Yeah. So let's check how the input is transitioning. How input is transitioning. 1 0. When input is 1 0, that means output will be 1 0 only. When input is going to 0 1, 0 1, output will be 1 0 only. When input is at 0 0, that means it will be hold state. When input is going to 1 1, again output is 1 0. So always output is 1 0 1 0 1 0 1 0. So which is the option? First one. So this is how I have told you to analyze a random latch. Okay. Standard latch we know how to analyze, but any random latch also you should know how to analyze. So first try to find out the condition where both of the guys are not waiting. If both of the guys are not waiting, then you wrote down the answer. Then you vary the things. Like if this is 1, this is 0, then you would know that one guy has to wait, another guys don't need to wait. If both guys are waiting, that means that will be hold state. That's it. This is how you need to analyze it. Well and good. You can think of the standard latch as well. Do you remember the standard latch? Using NOR gate. Right? These were the feedback there. So here this was A and this was B. So here if I apply both to be 0, so now both guys needs to wait, no? Basically, if here also you are applying 0, here also you are applying 0. So 0 nor with anything you cannot tell. You have to wait for this guy. Here also you have to wait for this guy. That's why this condition was hold. Here answer was if A is 0, B is 0, that means this is the hold condition. If you remember it. Right? So this was the hold condition. Why it was the hold condition? It was the hold condition because both guys has to wait. So similarly here, if A is 0 and B is 0, that means both guys are waiting. So this is the hold condition. Okay. You can check by any example. You can check the example of active low, active high, JK you can take, SR you can take. When both of the gates are waiting, that means that is the hold condition. Well and good. Let's go to the next question. Yeah, so this circuit is given and the state diagram is also given. So you need to relate JK with XY. Although you can go by option as well, but what will be the conventional way? Conventional way here, based on XY value and the current state, you can define the next state, right? Based on the XY value and the current state, you can define the next state. Basically, what do I mean by that? If my current state is 0, you can look here. If my current state is 0 and my applied input is 0 0, then I will go to the 0 state only. Are you getting this point? If my current state is 0 0, if my current state is 0, did I say 0 0? No. If my current state is 0 and applied input is 0 0, then I will come back to 0 only. If my current state is 0 and applied input is here, let's first write down all the possible input combination. So that would be 0 1 0 1 0 1 0 1. This would be 0 0 1 1 0 0 1 1. This would be 0 1 0 1 0 1 0 1. Now I can better analyze. Now, if your current state is 1 and applied input is 1 0, then you will go to the next state. That is 0 only. Next state, that is 0 only. Now, if your current state is 0, and applied input is 0 1, then you will go to the next state. If your current state is 1 and applied input is 1 1, then you will come back. If your current state is next is if your current state is 0 and applied input is 0 0, then you will come back to 0 only. If your current state is 1, and applied input is 1 0, then you will go to the next state. If your current state is 0, and applied input is 0 1, then you will go to the next state. And if your current state is 1 and applied input is 1 1, then you will come back here. Okay. Now let's write down for JK. Now using these guys, using only these two terms, can I write down the expression of JK? Then if I have the expression of JK, then I can relate it with XY as well. So do you remember the characteristics table? Q plus and then JK 0 0 0 1 1 0 1 1. So 0 1 don't care, 1 0, right? So if 0 0 is there, 0 don't care. If 1 0 is there, don't care 1. If 0 1 is there, 1 don't care. If 1 1 is there, don't care 0. If 0 0 is there, 0 don't care. If 1 0 is there, don't care 1. If 0 1 is there, 1 don't care. If 1 1 is there, don't care 0. So this is just the XOR operation, you can see. This don't care. Now you can make the K-map if you want to make the K-map, or you can check from the options as well. Better solve using the K-map. Okay, you can solve using the K-map. So J will be just the XOR operation of X5. 0 XOR 0, 0. 1 XOR 0. This is don't care. I can assume it to be 1. 0 XOR 1. This is 1 only. 1 XOR 1. This will be 0. Okay, this is I don't care. I can assume it to be 0. 0 XOR 0 will be 0. 1 XOR 0 will be 1. I can assume it to be 1 since it is I don't care. 0 XOR 1 will be 1. 1 XOR 1 will be 0. I can assume it to be 0. Same goes here as well. 0 XOR 0 can be 0. 1 XOR 0, 1. 0 XOR 1, I can assume it to be 1. 1 XOR 1, 0. 0 XOR 0, I can assume it to be 0. 1 XOR 0, 1. 0 XOR 1, I can assume it to be 1. And 1 XOR 1, 0 only. So what we are getting? These are your, both are J and K, both are X XOR Y and X XOR Y. Or you can go by the option as well. This is a very common state diagram. Here what do you see in this diagram? What do you see? If applied input is 0 0 or 1 1, if applied inputs are 0 0 or 1 1, that means you are getting back into the same state. That means you are at hold condition. If your xy was 0 0 or 1 1, that means you are in hold condition. This is just a way of solving it. Like if a big question is coming with different data, then you will go with this analysis. But here in this one, options are very easy, no? So what do you see here? If applied input is 0 0 or 1 1, applied input is 0 0, you are coming to the same state. 1 1, you are coming to the same state. 0 0, you are coming to the same state. 1 1, you are coming to the same state. That means you are in the hold condition. That means here if you are having 0 0 or 1 1, you are in hold condition. And in JK flip flop, when you are in hold condition? When you are having 0 0 here. Right? Say yes or no. That means X XOR Y will be 0. X XOR Y will be 0 only. So that means X XOR Y and X XOR Y are the option. So this is how I could have checked with the option as well. Well and good. Let's go to the next one. Yeah, let's see this question. You need to tell the value of n, you need to tell. V output is given 9.375, magnitude is given. So this is the maximum value of V out, that is 9.375. That is the maximum value of V out. So when you can receive maximum value of V out, what will be your V out? First, let me know. This is your I1, right? This would be your I2. Let's just say this is your I3. And one thing you know that this op-amp will be in negative feedback, so this node will be 0. So this complete all the summation of this would be IN. So summation of all these current, let's just say that current is I. So that will be flowing through this resistance. So what will be your V naught? V naught will be equals to minus I into R. And what is your I? I is your I1 plus I2 dot IN into R. So that means all these currents should exist. If all these currents are finite, current will be a positive quantity, no? This will be a positive value, right? If all these currents are non-zero, then you are happy. Then you will receive the maximum V out. For maximum V out, for V naught to be maximum, all these currents should be non-zero. Right? Now let's just say if this bit is 0, assuming this bit is 0, B2 is 0. So here also there is 0 voltage, here also there is 0 voltage. So what will be the current I3? That would be 0. So there is only two chances. Either B2 could be 0 or B2 could be 5 volt. If I apply B2 to be 0, then 0 minus 0 divided by 4R current would be 0 only. If I apply B1 to be 0, then 0 minus 0 divided by 2R current would be 0 only. So if I want the maximum V out, that means I want maximum current. And if I want maximum current, that means I want all the currents to be non-zero. And if I want all the currents to be non-zero, that means all the inputs should be 5 volt. Do you agree to this point? Say yes or no. Although I could have directly say that this is a DAC. And in the DAC, if you need highest output, that means all the bits should be 1. But what if in the examination this word is not given? That this is a DAC. This is just a simple circuit. This is a question on analog electronics. Then you wouldn't know it is a DAC. You would solve it using your simple concept that what you would want your bits to be. You would want your bits to be at the highest potential. And what is the reason behind that? The reason is because it will drive maximum current. and if it is driving maximum current, then output will be maximum, right? So you want all the bits to be at highest potential, that means 5 volt, 5 volt, 5 volt. So this was the one good point which I guess a lot of people would have missed. So like since DAC was given, so you would have already written down that all will be 5 volt, but without DAC also you could have thought about it, right? You need to find the value of n. This is a very easy question now. So magnitude of V out, what that would be? That would be equals to I into R. What is my I? I is 5 by R plus 5 by 2R. V out max we are talking about. So that means all are finite plus 5 by 4R. In that manner 5 by 2 to the power n minus 1 into R, right? So let's add a page. Okay, I am already having the page. So mod of V naught max is equals to 5 plus 5 by 2 plus 5 2 square divided by 5 to the power 3, in that manner 5 2 to the power n minus 1. Okay, so this V naught max is equals to 9.375. 9.375 is equals to 5 into 1 plus 1 by 2. In that manner, how many terms are there? This is the first term, right? So how many terms are there? N terms or n minus 1 term? There are n terms, right? This is the first term, this is the second term. So n value is 2 here. So 2 minus 1 if you put, yeah, this is the second term. So there are total n terms. So total terms are n. This total terms are n. So what you are getting? 5. Now if you do the summation, 1 minus r to the power n, a r to the power n minus 1 upon r minus 1, that would be 1 minus 1 by 2. So what you are getting? 0.9375 is equals to 1 minus 1 by 2 to the power n. So if you solve it, what will be the value of n you will be getting? 1 minus 0.9375 and log base 2. So n value equals to 4 we are getting. N value is equals to 4. So answer is 4. Okay. So this was a decent question if you think with respect to analog electronics. But if you think with respect to DAC or with respect to data converters, then it is straightforward. Let's go to the next. Let's see the solution of this problem. So this problem is based on STA. So to avoid any timing violation, what should be the maximum allowable clock frequency? This is what they are asking. So we need to write down that T clock equation. So you know how to write down the T clock equation. First, what you need to see? You need to see the inputs of the flip-flops. So this input of flip-flop, this is also not constant. This is also not constant, and this is also not constant. You can go from flop 1 to flop 2. You can go from flop 2 to flop 3, and you can come back from flop 3 to flop 1 as well. So there are 3 paths, right? What all are the 3 paths? I have uploaded a 3 hours of video on YouTube. You can just go and type static timing analysis by Himanshu Agarwal. So in that 3 hour of video, every single concept will be cleared if it is not clear. Okay. So this is just the problem solving. So you are going from flip-flop 1 to flip-flop 2 first. So what should be your T clock? So your T clock should be greater than or equals to delay of the clock, that is 0. Delay of this one 3 nanosecond plus 3 nanosecond, and then the setup of this guy, that is also 3 nanosecond. So 3 nanosecond plus 3 nanosecond plus setup of the other guy minus skew. What is the skew of this clock? Skew of this clock, you are going to this path, then you are taking the setup, and then you are subtracting the skew. So skew of this clock is 2 nanosecond minus 2 nanosecond. So this guy is saying that your T clock should be greater than 7 nanosecond. Okay. Now if you are going from flop 2 to flop 3, because that is the other path, so what should be your T clock? Flop 2 to flop 3. So total delay, you are going in this path, 2 nanosecond plus 4 nanosecond plus 4 nanosecond, 2 nanosecond plus 4 nanosecond plus 4 nanosecond. This is the delay, right? Then setup margin. What is the setup margin it is requiring? 3 nanosecond. 3 nanosecond minus the skew. Skew of this clock. Skew of this clock. What is the skew of this clock? 3 nanosecond. No. Here the clock is reaching after 2 nanosecond. So you took the delay to be 2 nanosecond here. You took the delay to be 2 nanosecond. Here at this point, the clock is reaching after 5 nanosecond, no? From here clock is working. So the skew of this clock is 5 nanosecond, not 3 nanosecond. The skew of this clock is 2 nanosecond plus 3 nanosecond, that is 5 nanosecond. The skew of this clock is 5 nanosecond. Okay. So this guy is saying that your T clock should be greater than 8 nanosecond. Okay. Now you can come back from flip-flop 3 to flip-flop 1 as well. So what should be your T clock? So your T clock should be greater than, so this delay, total delay, then you need to go to till this point. So how you are going? 5 nanosecond plus 2 nanosecond. Clock delay is 5 nanosecond plus 2 nanosecond. 5 nanosecond plus 2 nanosecond plus 1 nanosecond minus the skew of this clock. So this clock is not having any skew. So minus 0. So this guy is saying that, wait a second. Oh, sorry. I forgot to add the setup time. You are working from here and you have reached till this point. Then you need to add the setup margin as well, no? So what is the setup margin? That is 2 nanosecond and minus the skew. The skew is 0. So what you are getting? 10 nanosecond. So this guy is saying that your T clock should be greater than, 7 nanosecond, 8 nanosecond and 10 nanosecond. Now I say a statement, okay? I am telling you a statement that I will be happy if Virat scores more than 7 runs. I will be happy if Virat scores more than 7 runs. I will be happy if Virat scores more than 8 runs. And I will be happy if Virat scores more than 10 runs. So if Virat scores 9 runs, then this guy will be happy, but this guy will not be happy. So Virat needs to score more than 10 runs so that all 3 guys would be happy. So this guy is saying you need 7 nanosecond, this guy is saying you need 8 nanosecond, and this guy is saying you need 10 nanosecond. So to make all of them happy, your T clock should be greater than 10 nanosecond, right? So your T clock should be greater than 10 nanosecond. T clock should be greater than or equals to 10 nanosecond. So your F clock should be less than or equals to 1 by 10 nano, or your F clock should be 10 nano means 100 megahertz, right? So maximum allowable frequency is 100 megahertz. Okay. Some guys would be stopping here, like some guys will solve and they will be stopping here. Some guys would be stopping here, but this is the exact answer. All 3 analysis you need to do: flop 1 to flop 2, flop 2 to flop 3, and flop 3 to flop 1. Okay. And skew is also very important. This clock is having 0 skew, this clock is having a skew of 2 nanosecond, and this clock is having a skew of 5 nanosecond, right? Okay. Yeah, that's it about this question. Let's move to the next. So here you need to avoid the hold violation. They are not talking about setup violation. Setup violation can be there. You need to avoid the hold violation. So you need to write down the TH equation. That means you need to write down the equation for hold time. And clock frequency is given. T clock, F clock is given, that is 1 gigahertz. F clock is given, that is 1 gigahertz. So what will be the T clock? T clock is 1 nanosecond. Okay. T clock is 1 nanosecond. You need to find out TH. So how do you find out TH? So what is the path here? You can go from flop 1 to flop 2. That's it. You cannot come from flop 2 to flop 1. No. Because there is no path, no? In the previous question there was path available. But now here there is no path. You can go from flop 1 to flop 2 only. So only one equation will be there. Flop 1 to flop 2. Flip flop 1 to flip flop 2. Okay. So how will you go? 2 nanosecond plus 2 nanosecond. Delay of 2 nanosecond plus this delay 2 nanosecond. So TH should be less than. For T clock we write down T clock should be greater than or equals to, but for TH we write down TH should be less than or equals to. This is how you will start working. From here to here you will reach 2 nanosecond plus 2 nanosecond. So here you will reach 2 nanosecond plus 2 nanosecond. Will you add setup time here? Will you add the setup time here? No. When we write down the hold equation, we do not need setup time. We don't do anything with the setup time. Now I will directly subtract the skew. So if I subtract the skew, that means if I do minus 3 nanosecond. So my answer would be TH should be less than or equals to 1 nanosecond. Answer is wrong. Why is that so? Why this answer is wrong? Sir, I followed the method that you told me, that you write down the delay and subtract the skew for whole equation, and for t clock you need to add the setup margin as well and then you subtract the skew. But the important point here is that you missed something. What did you miss? This bubble you missed. This is positively edge triggered and this is negatively edge triggered. That means if you take out this bubble, that means inverter can be taken out. Basically, this thing can be replaced with inverter being out. So you could have made this positive edge triggered only, but inverter is out now. And what does this inverter does? This inverter provides you a time shift of plus minus t by 2. So now I am modifying my error. When I taught you that 3 hour of video, in that 3 hour of video, I told that this inverter gives you a time shift of minus t by 2 only. But no, it will give you the time shift of plus minus t by 2, because if it is shifted by t by 2 or if it is shifted by minus t by 2, both are same thing. What I mean to say is that, let's just say this is my clock and this clock goes through an inverter. So what will be the output? 1 will be replaced with, 0 will be replaced with 1, 1 will be replaced with 0. In that manner we will receive the output. So this is the output of the inverter and this was the input of the inverter. And this point is t by 2. So either you shift this waveform here by t by 2 or you shift this waveform here by t by 2. Both waveform will be same only, no? What I mean to say is that if I shift this waveform t by 2 on this side, so what I will get? If I shift this waveform by t by 2 on this side, so what I will get? This 0 will be coming here, this 1 will be going ahead, this 0 will be going ahead, this 1 will be going ahead. In that manner it will be shifted. So now these two waveforms are same only. So that's why I say that an inverter provides a shift of plus t by 2 and minus t by 2 as well. If I shift this waveform to this side, what will happen? This 0 will come here, this 0 will come here, this 1 will come here, so 1 will come here, then this 0 will come here, so 0 is coming here. So all three waveforms are same only. This waveform, this waveform, this waveform only. So if there is a positively edge triggered flip flop and the other flip flop is negatively edge triggered, so you can say that the clock that is received by this guy and the clock that is received by this guy, so the clock that is received by this guy is time shifted by plus minus t by 2 from this clock. Are you getting this point? Or you can say the inverters gives a time shift of plus minus t by 2. So this thing you need to remember. The final conclusion is this inverter will give you a time shift of plus minus t by 2. So here I will write down both of the equation. I will write down the t clock equation as well. So if I write down the t clock equation, what that would be? So t clock equation would be, it should be less than, t clock should be greater than or equals to 2 nanosecond plus 2 nanosecond plus the setup margin minus the skew is 3 nanosecond. So here also skew will be subtracted, but along with the skew there is another time shift as well. Basically there is another delay. This inverter is giving you a delay. This inverter gives you a delay of plus minus t by 2. This inverter gives you a delay of plus minus t by 2. So what you will write here? Plus t by 2 you will write here. Here you will write plus t by 2 or minus t by 2. That you need to think. So let me know what I will write here. Because of this inverter, you are getting plus minus t by 2. So in one of the case you will write plus t by 2. In one of the case you will write minus t by 2. So think about it. How I will write t by 2, or you can say t clock by 2. So here I will write plus t clock by 2 or minus t clock by 2. So think about it. Here what is the sign? Less than or equals to. This point we have already discussed. Although this point has been already discussed in our that 3 hour of video, but again I am discussing it. So TH, let's just say my TH is, one guy is saying that your TH should be less than 1 nanosecond and other guy is saying that it should be less than 0.5 nanosecond. Now I say that I will be happy if Steven Smith scores less than 10 runs. If Steven Smith scores less than 10 runs, I will be happy. And other guy is saying that I will be happy if Steven Smith scores less than 5 runs. So to make both of them happy, how much runs Steven Smith need to score? So maximum he can score 5 runs. If I should be happy and this guy should also be happy. If Smith scores 6 runs, then this guy will not be happy. I will be happy. But if Smith needs to satisfy both of the guy, that means he needs to score maximum 5 runs. So value here should be minimum. If there is a sign of less than, that means value here should be minimum. So you want this value to be minimum. Are you getting this point? You want this value to be minimum. Here Steven Smith is looking for this guy. He is not hearing this guy, because he knows that if I satisfy this guy, then certainly this guy is already satisfied. So that means he is looking at the condition where this value is minimum. So you need this value to be minimum. And if you need this value to be minimum, that means you need this value to be maximum. Right? You need this value to be maximum. This is 4 nanosecond. 4 nanosecond minus something. So if you need complete value to be minimum, that means you need this value to be maximum. Right? So here what you will add, here what you will write, 3 nanosecond plus t clock by 2. Right? Because here I want it to be greater. And just the opposite scenario you can take in this manner as well. Here we saw no. Here in the previous example only we saw. He is looking at the 10 nanosecond guy. That means you need this value to be maximum. And if you need this value to be maximum, that means you would need this value to be minimum. And if you need this value to be minimum, so here you will write minus t clock by 2. And what is t clock given? T clock is already given in our question. Although in our problem t clock is already given. So this will be the equation of t clock. Okay, this will be the equation of t clock. So from here, to avoid any setup violation, this will be the answer for t clock. So what will be the answer? Here I can see that this minus it would be plus, here it would be t clock by 2 should be greater than 6 nanosecond minus 3 nanosecond. 6 minus 3 and this is plus, yeah. So t clock should be greater than 6 nanosecond. Okay. But f clock and then f clock should be less than 1 by 6 nanosecond, or you can say 10 to the power 9. So f clock should be less than 1000 by 6 or whatever it is. 1 by 6 is 0.167 gigahertz. This is the answer to avoid setup violation. But what is your f clock? That is 1 gigahertz. So here this is the condition to avoid setup violation. But your f clock, but your actual f clock is greater than 1 gig. F clock given, that is 1 gigahertz. So that means in this condition there is setup violation. But in this particular question, what they are asking? They are asking you the whole time. What they are asking? Maximum allowable whole time they are asking. Although in this question setup violation is there, but this is not something that is asked. This is just for your understanding. This analysis is only for your understanding. So this they did not ask. They asked the whole time. So TH should be less than or equals to 4 nanosecond minus 3 nanosecond minus t clock by 2. What is your t clock? T clock is 1 nanosecond. That is given. So this analysis was not asked. So I will just keep that in a box. This was not asked. Okay. So t clock is 1 nanosecond, that is given. So TH should be less than 1 nanosecond minus 1 nanosecond by 2. So TH should be less than 0.5 nanosecond. So this is the answer. Okay. It was a good question. So this is the answer. That the maximum allowable hold time is 0.5 nanosecond. So I am expecting that this kind of question is coming in near future in your examination. You can solve it using timing diagram as well. If you have seen that 3 hours of video, then you will be able to solve it using timing diagram. Okay. Yeah. So yeah, that's it. That's it about this question. Let's go to the next. Yeah. So using CMOS, you need to implement this transistor. Okay. Y is equals to C, A, D, B, C, D, A, B. Now it is very tough to think. Okay. Very, very tough to think. But I will just tell you an intuition that how I would be thinking in the examination. So what is my Y bar? Because I will be using NMOS and PMOS. So usually we design the PMOS side. Basically, we design the pull down network. We design this NMOS side. Then here we collect our output. Then we say that we can make the PMOS side by our own. This is our VDD. This is our ground. And then here we apply the input. And this is our output. So this is how we design. So usually we design our NMOS side only. Then from there we can design our PMOS side. Right? And I have uploaded the CMOS implementation on YouTube itself. You can go and watch. So what is your Y bar? Y bar is CEA plus DE plus BCD plus AB. So I will design this Y bar only. My target is to design this thing. Okay, right? So CEA, DE, BCD and AB. Here there is two terms which contains two variable, and here there are three terms which contains here there are two terms which contains two variable. Arey yaar, what I am saying? Here there are two terms which contains two variable. Two terms which contains two variable. And here there are two terms which contains three variables. Two terms which contains three variables. Right? Now in these three variables, CEA plus BCD, what do I see is that C is common. C is common. Okay? And now then this is DE plus AB. DE plus AB. So how do I design that? DE plus AB I will require. So what I can do is that this is my D, this is my E. This is my D, this is my E. Both both NMOS will give me D into E. And what else I require? I require AB as well. I require AB as well. So A into B. A into B. Okay. Here I collect my output. So from here what I am getting? DE plus AB bar. This is the output I am getting if I design in this manner. Now what do I do is that in between I connect C. In between I connect C in this manner. This is how I have connected my C. Now what will happen? So what all are the paths to get V0 to 0? If D and E both are on, DE. Or if A and B both are on. Or if E is on, C is on and A is on. If E is on, C is on and A is on. Or if B is on, C is on and D is on. B is on, C is on and D is on. So this is your V0 now. And certainly since it is connected to ground, so bar will also come. So DE plus AB plus CEA plus BCD plus CEA plus BCD. So how many you required here? 5. Here you required NMOS 5. So certainly PMOS also you require 5. So total transition would be 5 plus 5 equals to 10. So did you understand how did I thought of it? First I saw that two variables I require DE plus AB. DE plus AB. Then in the three variables C is common. So C should be coming right in between. So this is how I thought of it. So 5 plus 5, 10. Okay. So 10 is the final answer. Yeah. So that's it. This was the final question of our digital electronics. Okay. Thank you very much. I hope you enjoyed all this analysis. And if you enjoyed it, you can share it with your friends. Thank you. Yeah. So this is the question from logic families. So in logic families, what do we do is that the output of NAND gate is connected to a certain number of NOT gates and its output is shown as a figure. This is the question on figure of merit, right? So each NOT gate is drawing a current of 3 milliampere. Each NOT gate will take a current of 3 milliampere. So 3 milliampere, 3 milliampere and 3 milliampere. Everyone will take the current of 3 milliampere and the NOT gate and NAND gate can drive maximum current it can give is 3 milliampere. So to work properly, a NOT gate will require 3 milliampere current. So from 10 milliampere, this guy will get some current, this guy will also get some current, and this guy will also get some current. So 3 plus 3 plus 3, 9 milliampere. And one guy will get only 1 milliampere current. So now this NOT gate cannot work properly. And rest of the NOT gates will get 0 milliampere current only. So they will not get any current. So these guys will also not work properly. So only this guy, and this guy. Only 3 guys will work properly. So what is the answer? How many gates we can source? That is 3. So answer is 3. That's it. Okay. Very easy question. These kind of basic questions are there from logic families, but the thing is nowadays these questions are not asked. These kind of questions can be coming in ESC, but in gate examination these has been asked in 90s, like way back. But since this is mentioned in your syllabus, so who knows, it can be asked. So that's why we framed this question. Okay, yeah.